still only got about 50% renewables on the grid. And if you really want to put more in, you've got to have a way of storing it. And yet, if you contrast these sort of numbers with the numbers of current redox flow batteries, which are these large batteries that enable storage on a massive scale. So this is a large battery park here in China. You know, we're still talking about gigawatt hours. So the question is, how do we do this? So that's interesting. It's me messing around with this. This is my own fault for using my own computer and messing around with the, oh, here we are. So I'm going to stand here, then I won't. So most of you would have not. It's okay now. I'm okay now. I'm okay. So I'm sure that many of you in an inorganic class will be taught what the Sony rocking chair battery is, but it's the battery that I really want to focus my talk on. So on the left, you have lithium cobalt oxide. It was invented by John Goodenough all the way back in 1980. I like this presentation because it's from Matt Res-Bull. It shows you that you can win a Nobel Prize and not publish in Science and Nature. And also, he was 55 when he published this paper, so there's sort of hope for some of us slightly older in the audience. Not that I'm implying anything, but anyway. So, and on the right hand side, you have graphite. And so what you notice is you've got two layered materials where you go backwards and forwards. And Sony, when they put the battery together, called this the rocking chair battery because the lithium ions rocked backwards and forwards. So one of the sort of most efficient ways of presumably the battery ran out on the other one. I have no idea. So one of the most efficient ways of improving and making things more sustainable is to think about how things operate. And the challenge in this field is issues of things that happen at the level of atoms. So how do ions go in and out of structures? How do the electrons move in and out? How do the particles respond? And how does degradation happen in the timescales of electron transfer, which is sort of sub-seconds, so milliseconds, femtoseconds, all the way through to processes that might then manifest themselves, first of all, at the particle level, shown here, all the way through to the pack level, shown here, happening over multiple days and years. And so I lead the UK's activity in battery degradation via this institute called the Faraday Institution, and we combine a whole series of different metrologies and theory to understand how batteries degrade. And specifically, we look at something called crosstalk. So crosstalk is, you think about not just how the graphite operates and the cathode operates, but how, for example, the gases that might come out or the acidic species as these materials degrade go through the electrolyte and affect the graphite and cause more degradation processes. And the material I want to sort of end up talking about is this material NMC 811. It's a layered material, isostructural lithium cobalt, and it has 80% nickel, 10% manganese, and 10% cobalt, and that's why it's imaginatively referred to as NMC 811. And so where possible, we should do as many battery studies in situ so that we can watch and catch things that are happening on the fly. It's a much more efficient way. We don't have to make lots of little batteries that we charge to different states of charge. And we can also try and catch the species that might not survive if we took the battery apart. But it's not so simple as taking our little battery and putting in an NMR probe, because a battery is covered by or surrounded by a can to hold the components together. And of course, those who do NMR spectroscopy know that you can't get RF through to the can, so you've got to redesign your cells. You can't do X-ray diffraction so easily because you can't get X-rays through the battery can. And so over the years, we've developed a whole series of metrologies to deal with that. The next thing we need to deal with is that the many components that are in your battery resonate over a whole variety of different chemical shift ranges. So if you have a lithium metal, it has a night shift and it has a peak at about 250 ppm. Sodium is even bigger. And then in contrast to the electrolyte and the degradation product called the SCI, that's at close to 0 ppm. So that's the scale for lithium. So lithium has a chemical shift scale that's very similar to that of protons. But if you have a paramagnetic material, that could span over about 2000 ppm. So we need to develop the metrologies to understand that. Then we need to deal with the fact that if you put a battery in your coil, well, it can catch fire if you operate it badly. But also these 2 points here are the electrical contacts that we're feeding wires down. And these wires can act as antennae, picking up radio signals. So we do NMR spectroscopy in FM, which of course is where you might pick up, I don't know where Radio Italia is, but it's BBC Radio 4 is about the right frequency. So we've developed these different little bespoke cells. So we use so-called plastic bag technology, the same technology that you would use to seal smoked salmon. We seal our batteries in them. So this is the current collector. Here's the plastic laminate, and you can see the separator there. And you can then put this in your NMR spectrometer in your coil. Or we can make other ones made out of plastic to hold things together in a much more airtight way. And then we've built probes now together with NMR services where we can put not only the leads inside, but we can also tune the probes automatically so that when the batteries cycle and the susceptibility changes as things maybe become metallic, we can tune these things on the fly from the desk. So the question is, what can we learn? So I just sort of give you a brief flavor of the sorts of things. What you're looking at here is a supercapacitor. So it's a carbon material where, as you charge positively and negatively, the anions are going in and out of the pores. And so this shift here is the pore ions going in the pores and the ions going out. And the shift we're seeing is actually a nuclear-induced chemical shift coming from difference of aromaticities in the carbon sheets as you're pumping the ions in. And these very simple experiments were used to work out how you take up ions in the pores. And so if you do a little thought experiment and you say, I'm a supercapacitor, I've got these layered carbon sheets, and I want to take up charge to go from 0 volts to plus volts, so positively charged, I could either kick out positive ions to balance charge, or I could bring in negative ions, or I could swap them around. And that swapping around I call ion exchange. And by just simply quantifying the cation concentration and the anion concentration by magnetic resonance, we were able to separate the mechanisms. And this on the left-hand side is an example of silicon. So silicon has a capacity 10 times that of graphite, because the end compound is about Li15Si4. But when you form it and you leave it, actually the battery degrades, and you can see the degradation process as this is gradually just sitting there in time. And so what's happening is the fully reduced silicide is reacting with the electrolyte and itself being passivated, but not sufficiently well passivated for the battery to survive. And so this was published about 15 years ago now, and it was probably the first paper to recognize that this was the major problem preventing commercialization of this anode material. And just sort of moving on to beyond lithium, one of the good other nuclei that we can use is sodium. And so we can also study sodium-ion batteries. Sodium-ion batteries are obviously more sustainable for the obvious reason in that the Earth abundance of sodium versus lithium is much higher. And the other thing that's less obvious to most people is that you can replace the copper current collector by aluminium because sodium doesn't react with aluminium, unlike lithium. And so using sodium NMR, we were able to study how the hard carbon that was used, so you can't intercalate sodium in graphite, so you have to use these more amorphous carbons. So we could follow that mechanism, and we could also look at reactions of sodium and tin. So I want to now tell you some longer stories, and I'll see how far I get in this talk, starting with how we can look at local structure and dynamics by ex situ NMR, and then move that through from these local levels to mechanisms at the particle levels and then the full cell levels. If I have time, I'll tell you about fast charging and bigger batteries. So over my career, one of the things I've tried to do is to develop the whole metrology of lithium NMR of paramagnetic materials. And this relates maybe to more people in the audience interested in magnetism, in that I try and use the lithium hyperfine shift, in other words, the measure of how much unsped spin density moves from the lithium through the oxygen sorry, moves from, this is early in the morning, moves from the paramagnetic ions through the oxygen to the lithium that we're going to observe. And depending on the relationship between the paramagnetic ions and the oxygen and the lithium, you get different shifts. And we can separate so-called 180-degree interactions with 90-degree interactions. And using, for example, the Goodenough-Kanamori rules, I was able to rationalize why you got different shifts depending on the different transition metals and different oxidation states and environments. And so, for example, manganese 4+, and it's nice being an inorganic chemist audience where you don't have to say manganese 4+, D3, 3 T2G orbitals. So you get a nice and believe me, in a battery audience, I'd have to go through, it's like, there's a D orbital that splits with the crystal fields, no, stabilization energy, blah, 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 blah. Anyway, we all know that there's a T2G orbital here, and it gets a very nice 90-degree interaction, and that's why you get this very large shift. But a 180-degree interaction, there isn't a direct interaction. You actually have to go via an exchange interaction, and that gives you a negative shift. Anyway, the point of my story is that we can rationalize the fact you have very large shifts for the pristine material. So this is the material I've taken none of the lithium out. It's a mixture of nickel 2+ and 3+. And when I oxidize the nickel 2+ and 3+, it goes to nickel 4+, T2G6, low spin, S = 0. And all you get left are the shifts due to lithium trapped near manganese 4+ ions. But what about in the middle? Why is there suddenly this broad, sharp broad? Okay, again, this is an inorganic audience. It's got to be motion. How do we test motion? We just simply heat the sample up. And so if you go and you remove 10% of lithiums from the sample, you introduce vacancies in this layers. The lithiums can hop from octahedral site via this tetrahedral site intermediate to octahedral site. But if there aren't enough vacancies, this motion is slow. You pull out more, you pull out 25%, and you can see now you have narrowing by the time you've got to above 60 degrees, and at 50%, even close to room temperature, the lithium ions are moving. So because you know where the shifts are, you can develop a model to extract the hopping rates. And so basically, you get line narrowing when you have hopping on the time scale now of the hypervine interaction. And so if you have rapid hopping of that rate, you have hops of about 100 kilohertz between 0.25 and 0.75. And then, of course, with temperature, you can extract an activation barrier. And these are moderately low activation barriers, and a reason why these materials can operate for high rates in electric vehicles. And so another sort of thing that underpins it is that if you pull the lithiums out, the repulsions between the layers decrease, and so the layers expand. And then at the end, when you've got mostly nickel 4+, you have a nickel-oxygen bond, which starts to become more covalent. So you reduce the repulsion between the oxygens and the layers, and then you get this layer collapse. And so that then pins these lithiums in place, and they can no longer move. The other thing that's interesting, and this was something we'd recognized years ago with collaborator Gerd Sader, was that if you have hops from octahedral sites to octahedral sites via a tetrahedral site, you've got a very short contact with the metal below, and as the oxidation state changes and it becomes higher, that repulsion changes, and so the activation barrier goes up. So the question then is, how does this lithium mobility affect the intercalation mechanism? So in order to answer that question, I want to introduce a new technique that we and my colleague Akshay Rao have been developing over the last few years. So typically, if you look at a particle and you want to understand how it operates, you've got to go to a synchrotron to get a high intensity and focused X-ray source to focus it on your particle. It's possible, and people have done some very nice science around this, but you often have beam damage, challenges of getting time at synchrotron, and you can often only do one experiment, maybe 2 or 3 times a year. And so my colleague Akshay Rao was inspired by work of Phil Kukura in Oxford, who developed optical microscopy methods to look at fluorescent problems in biology. And so what Akshay did was to use this technique, rather sort of with a horrible name, ISCAT, to look at movement of polarons or holes in solar-based materials. And so together we asked the question, can you use optical light scattering to quantify how ions move in solids? And so the basic premise of this is that the scattering is proportional to the polarizability, which is then going to be a measure of the difference in a medium. And so we have resolution of 100 to 300 nanometers, depending how we do it. We come in with an LED, a little bit like this laser pointer, or it would be a laser pointer if I was using a laser pointer, but I'm not, I realize now it's a pseudo laser pointer. Anyway, the contrast between the media and the particle will give you some contrast in this experiment. And so we thought we'd start simple. We'd use this typical Raman cell that's used for batteries. We'll come in with an optical inspection window. And I said, well, let's use lithium cobalt oxide. We know we can make it. We can make big particles, and these big particles have nice facets. So this is the top of this plane of oxygens in these structures, and this is an edge. When you take the lithiums out of the structure, you get very characteristic processes. The first one shown in the derivative is this metal insulator transition, and this is an ordering transition. And so we looked at the images of our particles, and you can see we're focusing on the flat parts of these particles. So this is the image, and this is the SEM of the same particle. And so this was our first iSCAT image of a particle that we collected literally the week before the pandemic, and we spent the pandemic analyzing it. And so it meant that I had plenty of time to really think about what was going on. And so we're going to, what you see here is a phase transition going through the structure. Now it's a solid solution, so ions are gradually coming back into the structure. And what you're going to see here is a nucleation event as the lithium ions move through it. I'm going to play it one more time. So this is the voltage curve here, that you're pulling lithiums out of the structure, and you can see that ions are coming in or being pulled out from the edges. Then ions are going in, coming out gradually, and its particles getting lighter. And then you see this phase transition rush through the structure. Now I'm putting lithiums back in the structure, same thing. You'll see a nucleation event. So what is going on? So what you're seeing in that phase transition is this insulator to metal transition that occurs when you start from a lithium-rich phase and you go to a lithium-poor phase. But what was interesting was that you have two types of mechanisms. When you delithiate, you're actually pulling the lithiums from the edges, and you're forming a so-called shrinking core as more lithiums are being pulled out. But on the way back, you nucleate on one side of the particle, and the ions move through like this. And you can see this nicely in the differential images that are shown below. And these terms were inspired by a paper by Yang-Xiao Horn and Martin Besant, published a few years previously, or a year previously. And so the question is, why does it do it? And the reason for it comes directly from the difference in the mobilities of the phases that I was talking about a few seconds ago. So when you're in this lithium-rich phase, there's so much lithium in the structure, the ions can't move. If you go to the lithium-poor phase, the metallic phase, now you've removed 25% of the ions and you can move them. And so if you start thinking about this, let's take this stuffed phase. I pull some lithium out from the edges, and I've got no problem pulling out lithiums from the edges, and so the core shrinks. Well, as on the way back, I'm in my phase where the lithium ions can move. I nucleate the stuffed phase, and I can't put lithiums through the pink phase because they won't move. So instead, I have to bring the lithiums in through the blue phase and add to it so that it grows out in that direction. And so it's the differences in the conductivity, the ionic conductivity of these two phases, and also how fast ions get in and out of these materials that dictates this very different performance on charge and discharge. And so interestingly enough, the other phase transition I showed you very briefly is at Li 0.5, and this is an ordering transition that comes from the fact that you form ordered rows of lithium, vacancies and lithium. And so you can see you remove the rhombohedral structure or rhombohedral symmetry of the particle, and you can form these phases that have multiple domains in them, shown there. And so just very briefly, talking about the NMCs that I started out, I just want to show you how we've now moved from lithium cobalt oxide, which of course, although it's still in your phones, is not the current generation material. We used our method to ask a question in terms of how do these processes happen at the particle versus the electrode level. So the specific question in the field was, people often observed a two-phase reaction when you pull lithium out of the structure. Now, this material has a flat voltage versus capacity curve, which actually implies it's a solid solution. So there's one energy associated with getting the lithium out. But people saw these splittings in the diffraction pattern suggestive of a two-phase reaction. And one paper, we suggested that this was associated with differences in lithium mobilities, and we opened up a kinetic phase. This other paper by Martin Bazant suggested this was an electrode problem. So we said, let's use our method. And so now we're back after the pandemic. We've made a microscope better. We can see lots of different particles, and you can see certainly a lot of heterogeneity. And if you just focus on one particle, again, you can see this heterogeneity and this shrinking core model. And by now you're sort of, so the question then becomes, is this kinetic or is this thermodynamic? To test whether it's kinetic, you can just rest, you can stop your particle after 10 minutes. And if you wait long enough, then you get full delithiation. So this suggests it's a kinetic process. And so the sort of same reason it does it is as you start pulling lithium out of the structure, the red areas of the particle have higher lithium mobility. It's easier to keep on pulling out of them. And so you create this shrinking core. Now, if you humor me for 2 minutes, I just want to show you one result that comes from my colleagues, or in collaboration with my colleagues Vikram Deshpande and Norman Fleck, who are mechanical engineers. And what the beauty of this part is that we're able to take our NMR our NMR measurements of lithium hopping. So we know how fast the ions hop from octahedral sites to octahedral sites because we did the NMR of this. We can then relate this to the diffusivity, which is simply the hopping rate times the distance squared divided by 4 because it's 2D. We also know the cost or the energy associated with pulling lithiums out of the structure because we have a voltage curve. And so we know directly from the Nernst equation that this directly then relates to the delta G of the reaction. And so we can then put this into a continuum model simulation and see if this matches our experimental results. And so this is our experiment, and this is the model, beautifully showing you that it's this distribution or change in the diffusion coefficient as a function of delithiation, which is what's shown here, that drives these metastable two-phase reactions. Okay, I want to go from the cathode now to the anode and show you something about graphite. So this is a material that's been studied for so many years, and you might think, well, what is there left to study? So just let me remind you of how lithium is thought to be removed from graphite or put into graphite. So you start with graphite, you go through a series of so-called dilute stages, and then you form the dense stages. And so in dense stage 2, you have alternating lithium vacancies, and these are meant to be layers. And LiC6, everything is lithiated. In the dilute stages, you have fillings. So stage 4 has got lithium, 3 vacant layers, another filled one, but they're not as closely packed as in the dense stages. And so this mechanism is the one that's believed operate for the graphite in your phones, but still it's not obvious how it happens. And so if you think about it, how do you go from a stage 4 to stage 3 mechanism where you've got alternating 1 filled, 3 vacant, 4 to something where you've got 1 filled, 2 vacant? You'd have to pull all the lithium out of one layer and put it back in another. And these particles are micron size. And so the Domas-Herold model is one that sort of gets around this issue by saying, let's have little domains in the same particle, and we'll just shuffle the lithium between the domains to resolve this problem. So we thought this must be a good ISCAT problem. At the same time, we do NMR. And just to sort of summarize this slide, without looking at the data, the bottom line is when you have dilute stages, there are fewer lithiums in the layer, and so the lithium ions hop much faster than they do when they're packed in the dense stages. In fact, they hop very, very fast in the dilute stages. And so here is the ISCAT thing of a particle. So we're now in the dense stages, and what you're seeing now are these movement of fronts as you're filling now from stage 2 to stage 1. So this is the intercalation wave that you saw already for lithium cobalt oxide. So just to watch it on the way back, you can see now we're delithiating, coming through, and then we've got, again, the next stage. But something very different is happening in the dilute stages that I'm going to unpick in a few minutes. So just warning for, I'm going to have some flashing images coming up. So this is now the ISCAT image, and this is the SEM image. And so you can see that this particle is made up of multiple domains. And that sort of explains why the whole thing is not acting as one large particle. It's dividing up into subdomains. The next thing is to ask, why do we get these changes of intensity that are so different? So this is the scattered intensity in the dilute versus the dense stages. And this simply comes from the differences in conductivity. So graphite is poorly conducting initially, and particularly then in the dilute stages, but when you add in the dense stages, it becomes metallic, and then you get very different scattering in a semiconductor versus a metal compound, explaining the differences here. And this has been studied by many people, including Millie Dresselhaus, for years. So the dense stages are these intercalation fronts that I was showing you, and that we can explain by the model I just talked about earlier. But what about the dilute stages? Well, these are amazing. They actually are multiple little events. And so if we look at our intensity versus capacity, it's not on close inspection a smoothed continuous curve. And these are not noise bits. What each of these little bumps are is the filling of different parts of that particle. And so that particle is being lithiated by this domain goes, then this domain, then this goes, and each of them corresponds to one of those little steps. And so you have independent filling one layer at a time with domains that are acting semi-independently. Now this is reminiscent of something called an avalanche behavior. So I know this is not very relevant to Naples, but were you in the Alps and it's getting warm, which it does increasingly in global warming, an avalanche is a process where something builds up and then suddenly it releases and it goes very, very suddenly. And this is what you're exactly seeing here. And so these are differential images on the right-hand side of domains going boom, 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 one at a time. And what's interesting is you can repeat that experiment again, and the flashes happen in the same place, pretty much cycle to cycle, which tells you it's not random. It's associated with specific domains and defects that happen. Anyway, so we can now model this. This is with my colleague Rob Jack, where we can develop a model to explain it, and we can also start to explain the hysteresis loops that you get as a function of temperature. And so just to sort of summarize this, despite graphite being studied for many, many years, and the stage 1 and stage 2 pretty well understood, we now have an explanation for how you actually start filling these layers one at a time in the dilute stages. Okay, so I want to ask the question, why can't we charge faster? Why would we want to charge faster? Well, of course, we all want our phones charged faster, so we want our cars charged faster for convenience, but I'm also interested in it for sustainability reasons. So if you could charge your car in 5 minutes, you wouldn't need a ton of batteries. If you had the charging station and infrastructure, which is another whole debate, and you knew it could be done very quickly, you could get away with a smaller battery. But why can't we do it? I've talked about the cathode. The cathode is good enough. This just shows you the challenge. So this is a Samsung battery that we put in a 10 amp current for 1 minute, heats up very, very quickly to above 60 degrees. Above 60 degrees is where lots of degradation processes happen. Specifically, the cathode is metastable. It loses oxygen. It's that oxygen that drives the battery fires and makes them so difficult to put out. It also results in degradation of the anode, and at the 60 degrees is when this passivating layer called the SEI starts to degrade. There's another problem that happens, and that's associated with dendrite formation. So you put lithium, and if it goes across too quickly, it can no longer intercalate inside the graphitic layers, and you form these dendrites, which are very beautiful, but can also result in short circuits. This is the Dreamliner battery that was grounded a few years ago because of what were thought to be lithium dendrite fires. And we love dendrites. We can do in situ NMR on this, and I could give you a whole talk about how we understand that. And this is a dendrite that's growing, and you'll see it go. And you'll also see the signal at 0 ppm grow as it's being covered in a passivating layer. But this is not what we want. We can see this also in our NMC materials. So here's one where we've taken NMC graphite battery in situ. And if we go down to low temperatures, you can see the formation of lithium metal. So how do we design for fast charging? So we find a battery material that operates above 0 volts to avoid the lithium plating. We want the one that has high lithium mobility. And one of the archetypal structures in solid-state chemistry is the so-called perovskite structure, or if it's missing the A site, it's called the rhenium trioxide structure, and it's got some lots of nice tunnels for potentially lithium. But the trouble is, once you put a lithium in there, you also change the oxidation state of the metal. It's the wrong size, and you end up with the whole structure distorting and clamping the lithium in place. And so lithium rhenium oxide, if it is a terrible lithium-ion conductor. And so you really can't use those types of structures. And so what we thought was, well, let's try and design materials of pillars. How do you do that in these structure types? What you do is you remove oxygen from these materials. And then when you remove oxygen from the materials, you can shear them. And then that shear then fuses the octahedra together so they can no longer rotate. You put lithium in and it can no longer move, and the channel is still open. You can do this in 2D via a material HNB205, and now you form blocks. And again, the lithium is in there, and it's pretty much rigidly held, or the lattice is rigidly held. And so my former student, Kent Griffiths, he cranked through every single material with niobium and tungsten and titanium and identified this material NB16W5055, abbreviated as NWO for obvious reasons, as the best in class. And he showed that you could get very high rates. So 20C means you charge your battery in 1 hour divided by 20, so that's a 3-minute charge. And there's a very little decrease in capacity, and then actually that's coming not from this material itself, it's coming from the lithium that we were using on the other side. And so Yumi Kim and others showed very easily that you could cycle this for many, many times with very little degradation. So why does it, or how fast do the ions move? So you can measure this with pulse field gradient NMR spectroscopy. Because these ions move so fast, we can use this technique, which we couldn't use, for example, for NMCs. And we end up with diffusion coefficients of about 10 to the minus 11 to 10 to the minus 13. So let's put this in context. If I have a diffusion coefficient of 10 to the minus 10, which is a typical liquid electrolyte, and I'm going to charge in 3 minutes, I can move about 1/3 of a millimeter, which is more or less the thickness of your battery. If I have a 10 to the minus 15 diffusion coefficient, and that's typical for graphite that I just showed you previously, I can only move a micron. But if we have our material, I can move about 33 microns. And why do I care about that? It means that I can use big particles and I can still move rapidly through them. And the bigger the particle, the less degradation and junk you form on the surface of these materials, and the safer it is. You need good ionic transport, but you also need good electronic transport. And again, this is the nice thing about inorganic conferences. What you have in these materials are nice overlap of the T2G orbitals down the tunnels, and this gives you the metallic conduction that you need for these structures. You also, when you've put the first electron in, form these really interesting so-called block orbitals, where you have overlap of the T2G orbitals in a plane, and at low temperatures, they actually order antiferromagnetically. And so we've now put this into a small company called Niobolt, which our chair mentioned, and this is our Niobolt battery that's heating only up to 38 degrees before it goes off in its Dyson vacuum cleaner, and other robots are available. And specifically, we now have robots that are hopefully running around in warehouses, stocking shelves. This is a rescue charger, and this is the CEO, Sai Shivareddy, who I co-founded the company with. This is a concept car. Not exactly a cheap version of the car, I can tell you. That is me. it's not licensed to go on the road, so this is the warehouse, and it has actually a cheaper technology. But the point of this car is it could be charged in 5 minutes, has a very small battery in it, so not sure that's going to be the cheapest way to do it. But anyway, that's another whole conversation. Chair, should I finish or have 2 more minutes? Okay, so I just want to think about bigger systems. So I started this conversation by saying we really need to deal with grid problems because that's where the challenges are. And it's very difficult to do if you're just going to use batteries and you're going to wire lots of them up together. And so at least conceptually, the way to do it is to try and decouple the materials from the electrochemistry. And you can do this in these so-called redox flow batteries where you have an electrochemical cell that does the electrochemistry, and then you have tanks of oxidized and reduced materials, and you flow them in when you want the electrons or the power. And this is done in these so-called vanadium redox flow chemistries where you have vanadium 2,3 on one side and 4,5 on the other side. And the nice thing about that is that you have a membrane that isn't that good at stopping transport of vanadium across, but you have less problems of cell balancing if it's still the same thing. But vanadium is toxic and it's a finite resource. So can we do something with organics? And so Michael Aziz's group at Harvard put out this molecule DHAC a number of years ago, but it has multiple degradation issues. And so I said, let's look at this by NMR. And this is a really easy NMR problem because we can take our redox flow probe and we could, redox flow battery, and then we can just take the things out of the battery and we can flow them directly through a spectrometer and we can do NMR. And we can flow in this case, it's a DHAC on one side, the quinone on one side, and the ferricyanide on the other side, but we're going to look at the quinone. And so the quinone we're looking at has got 3 proton sites, and you can see that very nicely in the proton NMR. But then we start to reduce this material through the semiquinone to the doubly reduced form. You see multiple things, but the most noticeable one is that we lose the signal of A and C almost immediately, but we also get a shift of the water resonance. So we're running this in D2O just to simplify things. And so we can understand why one of the resonances survives for longer by looking at how the unpaired electron density is spread through that molecule with DFT. So that makes sense. Then the next thing I recognized was that this shift of the water resonance is exactly what people use in the Evans method, where you plonk your liquid, your molecule, you want to know its bulk susceptibility in the NMR, and you use the bulk magnetic susceptibility to convert that to the susceptibility of your material, and you can quantify the radical concentration. So very simply, we were able to show that the water shift correlated to the formation of about 50% of these semiquinone radicals. And so when I started this naively, I thought you would go A to B to C, but why do you only get 50% radicals? And that's because the 2 1-electron processes are very close in energy. In fact, they're only about 33 MeV apart. And so you get these comproportionation reactions that control the concentration of the semiquinone. And we can extract that very simply from the Evans effect and the concentration of radicals. So why do you get a loss of signals very quickly? This comes simply from these electron transfer reactions. So when a diamagnetic quinone bumps into a radical, it exchanges electrons and you get a wiping out of the signal. And so if you introduce only 2% of these radicals, you can lose all the signals. And we can then study this as a function of temperature and start quantifying the activation barrier of these processes. And so we understand that. And then once you've done NMR, why stop there? You can just flow your tube into an EPR spectrometer. You can flow your tube into a UV-Vis spectrometer and track what's going on with multiple methods. And the EPR is nice because you can watch the hyperfine interactions in real time. And so you can start to see the hyperfines coming from the interactions with the protons. And when they're dilute, they're nicely resolved. As the concentration of radicals increases, you get exchange broadening. And you can prove that, again, that this, or you can quantify the extent of the hyperfine interactions in these systems. So why were we doing this? We were actually doing it because we were interested in studying degradation. And so we were able to show that the major degradation reaction is an electrochemical one by looking at when it happened at different voltages. And with Michael Aziz, we're able to propose that if you went down to low voltages, you could actually the degradation mechanisms involves hydrogenating these oxygens, and you could reverse that process by going down at low voltages. And with that, I think I will end this talk by just giving you some conclusions. I hope I've shown you that you can look at processes at a local level to try and look at both local oxidation environment changes in my NMCs. I can quantify how fast the ions hop. And then together with these optical experiments, I'm able to relate that to different intercalation mechanisms in these battery materials. These fast charging, this ability to move lithium ions fast were then exploited to develop some fast charging batteries, which we then put out into the marketplace. And our NMR approaches have been extended to redox flow. So this wouldn't be possible without my great research group shown here in Pembroke College the other day, at Christmas, in fact. And funding mostly comes from the Faraday Institution. I should really mention Barish and Ollie for in situ NMR, and Young Jay for the robot. Chow and Katerina were the NMC people. Kent and Lauren were the niobates. And really the work on ISCAT was pioneered by a great PhD student who was joint between me and Akshay, Alice Merriweather, and postdoc Chris Steneban. And thank you very much for listening.
Thank you very much, Professor Gay. Very inspiring, very broad. Is there time for a couple of short questions from the audience?
Thank you very much. Very fantastic presentation. I'm Cristiana Di Valentin from Milano. I just wanted to ask you a curiosity about this intercalation mechanism in graphite. I imagine that your sketch is very simplified. So how do you expect these lithium ions to get into the layers from the edges or from defects in the layers? Do you expect some migration also through the Z-axis or just diffusion along XY plane?
Personally, I don't think there's much evidence for diffusion through holes in the graphene sheets, but you will get defects. You have in these domains, you'll get some transport down the domain edges, and it'll mostly come through the edges. So you'll see if you humor me and allow me to play the movie one more time. I'm not going to be able to play the movie one more time, but you can see here that they're coming in this immediately through the edges, or through the gaps and the domain walls. And so the first process and almost the defect is to put the first lithium in so that you open up the layer slightly.
Yeah, then diffusion must be very quick.
Then it goes in very, very fast. And that's what this says. The diffusion has to be so fast that once you've opened up the layers, it's almost, and it goes.
Thank you.
And I just don't think it would be fast enough if you had defect, if you had transport through pinholes, basically, which is what the other mechanism might involve.
Your movie, when you show the delithiation process, I suppose that the contrast of the image is proportional to the polarizability or something.
Which change in the polarizability.
The change in the polarizability.
Yeah.
So the change in the polarizability? Okay, so my question was, where does the lithium go? Because at the end, your image is completely dark after delithiation. But it's because the polarizability is not changing anymore.
Just remember that we do the differential images where it's a change, but it is that contrast in polarizability between two media. So, just the color or the black-white doesn't really matter. And in this, for graphite, it's very dominated by the changes in the electronic conductivity, which give you changes in scattering, basically.
I see.
And so
in
some cases, you can see it's going here, for example. when you're in the dilute stages, you can see the scattering intensity is going down, and then suddenly it goes conducting, and so it's going in the opposite direction. So, in the NMCs, it's almost linear with lithiation, but to be honest, it could have gone the other way around. It's literally just differences in electronic conductivity, and again, it's the difference between the particle and the medium that
So
gives you
when at the beginning, at the end of the delithiation, when nothing happens, the image is anyway dark.
well, then you
because
don't. If nothing
yeah.
happens, then it just
Okay.
doesn't
Yeah.
change.
Thank you.
Yeah.
Thank you very much. It's fantastic talk. You had this very nice example on the flow battery system where you couple the NMR and DPR to get to explore the full magnetic resonance capabilities. I was wondering, in the solid state, is this approach feasible? What are the challenges? And can you explore the different timescales of the two spectroscopies to
You
monitor?
mean the doing NMR and EPR?
Exactly.
Yeah, we're trying to. There was a bit of set talk I didn't talk about. So the redox flow was easy because we were flowing things out, and then you can do things in parallel. And so we have a setup for solid state batteries where we can flow the electrolyte out. So for the solid systems, we can flow the electrolyte out and do similar things. And we can also do in situ. You can build in situ EPRs, but they're not so easy to sort of combine them in the same spectrometer, you know. So the closest we're actually trying to do is this technique, dynamic nuclear polarization, where you radiate the electrons and then you polarize the NMR. But our stuff have a lot of metals in it, so you're getting a lot of heating, and so you can do EPR in situ if you sort of tap into the right point, and you can, but you would have to take the compromise of the poorer resolution of the EPR experiment to do the NMR on it. You could probably do it on a benchtop system, but you would have compromises.
Yeah.
And I think often you have to ask, what would I be trying to get out of it? You know, I mean, it would be elegant, but yeah, so there are challenges, but happy to discuss more afterwards. But as I said, we are trying to do it with the DNP, and most of the time we just end up melting the battery, so, which is not that useful.
Thank you.
Okay, thank you. I will have also some questions later for the coffee break. So thank you very much again to our plenary. Thank you. And we move now to the keynote speaker of this morning, who is Dr. Daniela Galliani, holding a PhD in physical chemistry from the University of Milano Bicocca, where she specializes in organic electronics. She's currently program manager for emerging technologies at Industrie De Nora, where she leads a strategic R&D program focused on developing a next generation electrochemical solution to accelerate the energy transition. Her specific role involves translating market needs into innovative technologies, ensuring a strong connection between scientific advancement and industrial impact. Daniela brings hands-on experience in electrochemistry and a deep understanding of the technical challenges and opportunities in this field. And today she will speak about the role of De Nora, which is a very known industry in Italy, in the energy transition. Please, Daniela. Thank you.
Thank you. Thank you for the kind introduction. Okay. So thank you to the organization for having me today. My talk will be maybe a little bit different from, let's say, more scientific and in-depth analysis, but I hope you can take some messages and some interesting overview on a different perspective on chemistry and its role on the market. So I'm talking about De Nora, Industrie De Nora, which is an Italian multinational company based in Milan. And today I will talk about the journey of the company, where we started from and where we are at, with a specific focus, as was mentioned, in energy transition and how we want to play a role in build a cleaner future. So we will start with the brief history, which I think it's quite anecdotic and interesting. So De Nora was founded, everything started back in 1922. So we recently celebrated the 100 years birthday. And the founder, Oronzio De Nora, was an engineering student and researcher at Milano Politecnico. So he started to work in a lab and working on electrolysis of alkali chlorides. And he had the opportunity then to move on the industrial field. So he had the possibility to check how an hypochlorite production plant actually worked, and he could connect what he was doing in the lab with what it was needed by the industrial process. And that was the beginning of it. So he started to understand and work on how we could improve the industrial process with new cell design in the hypochlorite and production. So he started to sell this kind of design and moved then to the mercury chloralkali cell design and to water splitting, even back then in the 30s. After the Second World War, he was able to introduce his cell design, and that actually spread quite fastly in the chloralkali field. And it ended up being the widely used design in the 50s and in the 70s, and 40% of the chlorine in the world back then was produced with De Nora technologies. Then the team at that point, because the industry started to grow, looked at one of the most weak component within the whole process, not just the design, but we are talking about, okay, sorry. Okay. Just a sec, I guess. Okay. So the component I was talking about was the graphite anode, which was widely used, which was at the same time effective, but consumed during the operation due to the fact of the oxidative potential. So they started quite an exquisite chemical research on which kind of material could fulfill this complicated role to be active in the process and be durable. And they ended up, after research, to find, of course, the titanium as in the metal, but to find a particular mixture of metal oxides to be both active and stable in this process. And it was the birth of the DSA, so dimensionally stable anodes. After many trials, they ended up in focusing on titanium dioxide and ruthenium dioxide mixture, studying the crystalline structure and putting it on the titanium as a thin layer that could fulfill the process. So the DSA is kind of what make the company big, because the technology was very breakthrough for the time, and it's still widely used today, because from there we could expand this concept to several different processes. And this is what we've done. So this is a bit of a history. In the 60s, there was the breakthrough knowledge on the DSA and exploitation of that. And then we started to diversify to very different applications, electrochemical applications. This helped out also in growing globally with acquisition in different countries, and then start also to expand to different business arenas in water treatment in 2015. And as of the last 20 years, roughly, 20 years. For the last 10 years, roughly, we started to focus also on what we think is the future for the company, so the energy transition. And that started with, of course, DSA, so the study of electrodes for a particular process for hydrogen evolution, and then expanded to different fields. This is where we are today. And this is a bit of a, let's say, identity card of the company itself. So we are now spread across the world quite evenly, I would say, in the 3 areas depicted. We are 24 operating companies, but the focus has always been on the innovation and bringing new solutions to the market. And this is testified by the fact that we own almost 280 patent families at the moment. So getting a bit into what we actually do. So we build this, let's say, new knowledge, new innovative solution. In which field we bring that? What we do as a product at the end of the day. So we have 3 business arenas I already mentioned during the depicting you the history: electro technologies, which is our core business; energy transition, which is our new business and in which I'm working in; and the water technologies. So these 2 main businesses, let's say the original one, the older ones, just to give you an idea, for electrodes, we are component providers. So we work on anodes, cathode, catalytic coatings, gas diffusion electrodes, and cells. Well, for water technologies, we apply electrochemical processes to water treatment. So we sell actually system for water treatment. And the final one, the one I'm going a little bit more into deep dive today, we started from DSA electrodes for alkaline water electrolysis, and then we moved also to gas diffusion electrodes for fuel cells, and expand finally to sell a full system, electrolysis system for the market, the Dragonfly. So give you an idea on which sectors are we impacting with our products. The sectors are many, so actually the research is focusing on very different materials for the very different processes and operational environment. So there is a lot of diversification to be studied here. Chlor-alkali is quite a core business still, but then there is electronics, metal refining as major businesses, but we're also into pulp and paper, steel galvanizing, automotive chrome plating, plumb and furniture, and steel concrete corrosion protection through cathodic protection. So quite a large, I would say, impact on the market and on the possible technical solution. For water, we have water treatment from pools up to municipal to industrial, and as you will see on the line below, we sell actually the full system to the market. Getting to the energy transition, which I think it might be a little bit more interesting also to understand which is the market now, because the energy transition is ongoing, but we are not talking about very spread market already. So where the hydrogen, for instance, is needed. At the current status, the closer market to fulfill, let's say, the promise of energy transition through green hydrogen are the so-called hard-to-abate sectors. So we are talking about sectors in which you cannot easily use electrification to let's say, decarbonize or at least reduce CO2 emissions. In steel industry is quite common, but also cement industry, ceramic, glass. So usually high temperatures are involved. And to reach those high temperature, you can use green hydrogen as fuel. For steel industry, you can use green hydrogen also as DRI, so direct reduction of the iron. Then we have the green chemicals. So also for that, we have large, let's say, quite a good amount of processes that use hydrogen as a reactant. The most commonly cited is the ammonia production through Haber-Bosch. If you use green hydrogen in that process, you heavily decarbonize ammonia, which is then at the base of production of many chemicals. Here's the picture means the fertilizers, which is quite a large market. And finally, mobility. So we are aware that light mobility is quite bound to electrification, but there is a part of the mobility which the batteries cannot reach yet. And that part is a good target for the hydrogen. We've seen some examples in the past months and years. So we're talking trucks, but mainly ships, and also with, let's say, more forward-looking aviation. For these kind of markets, the products I already mentioned are electrode cells, the Dragonfly system, and gas diffusion electrodes for fuel cells. So to let you understand a bit more how De Nora is located in a value chain. So we provide components that needs to fulfill the desires of the very final client. So we need to understand which are the final operative condition, the final process, but there are a few steps for us because then we are the components inside that. And for instance, this is the value chain depicted for the hydrogen. You can see that for apart from the joint venture with ThyssenKrupp nucera, for which we provide both electrodes and cells, we always provide electrodes. And in the case of the Dragonfly, we are expanding not, let's say, globally or for a business area, but in our offer. So we extended the offer of the electrodes to the full system to get to the EPC contractors. And this is true also for the new arenas in which we are developing electrodes, which we are developing products, yeah, they are electrodes, to get to the market. So I'm talking about AEM, water electrolysis, so an ion exchange membrane water electrolysis electrodes, liquid organic hydrogen carriers, which is a different way to approach hydrogen utilization, and also CO2 electrochemical reduction, which is quite a new field, more than new, I would say, not so industrial yet, but we see a lot of potential in this application to transform CO2 in actual valuable products. Get into what we do, how we think about material research and development. So as I showed you, we are at the very beginning of the value chain, but we need to fulfill the requirements at the very end. And for instance, for hydrogen, the very final requirement from the customer is to have it that is cheap. So they want cheap hydrogen. They want a low levelized cost of hydrogen. And the whole market actually is based on the fact that we can reduce the price of the green hydrogen to make it actually competitive. And so we need to go back to the very beginning and understand how our electrodes can play a role, how the material we develop can play a role in fulfill this very final target. And it's depicted in this graph here. So we can develop materials that are very efficient in making hydrogen. And this means basically both on the anode side on the top and the cathode side on the top. If you can save over voltage through good activation, you can reduce electrode, contribute to specific energy consumption. And this has a double effect. On one side, of course, you can reduce the energy that you need to produce the same amount of hydrogen. And at the same time, you can go up in the current density, which means going up in specific hydrogen production. So if you can go up with your system to higher current density, this means that you can repay your initial investment in a shorter time. And this is not just it. This is the main, let's say, aspect we need to keep in our, let's say, as our feet for the development. But of course, there are many final aspects that we need to take into account. For instance, if you use an atmospheric or pressurized alkaline water electrolysis, this strongly impacts how your electrodes behave, how your materials, your catalytic coating behave. And you need to keep that in mind when you develop a new electrode. And also which kind of connection you have, which kind of feed you have for your electrolyzer. Is it with renewable sources? So you have, let's say, in constant current feed. And so this is a particular stress on the electrode. Or is a continuous operation? You have it on the grid, you have a certain amount of current served. And so you have a different kind of impact on your electrode. This means to keep it very at the beginning, this kind of feed of information, you need to keep it at the very beginning of your research and development. Just a sneak peek on the Dragonfly system, just because it's our newest product and let's say the most intense one in terms of development and you know, newness of in comparison with other products. So everything started with the concept, okay, we know the electrodes, we know which condition we can make around them to make them work better. So why not build around a premium product with our electrodes to make, you know, the full system? And this is it. So we make this containerized system which is a high capacity and high efficiency electrodes, but has minimized installation costs because it's a container that can be plugged and play by the customer. So just getting a final look here, the R&D. So I've been talking about what we do as a product, the approach that we have, the difficulties of starting very far from the end of the value chain. So R&D for us is core, is a core part of the company. Really, it's started with Oronzo Nonora being a researcher, and it still is on right now. So we have it as a corporate function with many people working in it in 5 sites, actually 6 sites around the world, because we have 2 sites in Japan, in Italy and US. In Germany and China, we have the R&D within the production. And this is very important for us because otherwise you lack the connection with the actual possibility to produce the product that you develop, the material that you develop. You might have very interesting ideas, very interesting concepts, but then you need to face the fact that it has to be produced in a sustainable way for the production. So it's important to have this connection for us. And R&D is focusing on both optimizing the existing technologies and explore the new ones. On the optimizing of existing technologies, we have, I think, a privilege in terms of the kind of feedback that we can obtain, because we sell the product and we know exactly, so we have a continuous feedback because we have the services for our client. So we have in-field operation of our product, and from there we can get much information on how to optimize it, how to push the boundaries of what is needed. And it is a very, very strong feedback that we have, and I think very important for R&D. Well, for exploring new ones, we understand that, let's say, we are in some markets, we have some knowledge built through time, but of course we need to keep on the edge. And this is usually quite difficult for a company because profit is, of course, the top list of the agenda. But we found that having also low TRL project, low TRL development is key to bring new knowledge and innovation in our process. And for that, we actually found very useful to be in consortia with, I mentioned here EU-funded projects, but we have also consortia in the other countries, in the other continents. And this is because with collaborating with academics and research centers is really useful to have new perspective, new kind of approaches to the problems that being in an industry you might lack at a certain point. And this is, let's say, a very interesting collaboration for us, type of collaborations for us. So just to give you an example, I brought one of the projects that we are working on. So I didn't bring all of them because it would have been a bit boring. But you are free to go on our website and check in which finance project we are currently working. I brought this one because it's a low TRL, so it's a bit different from what we've been working on in terms of electrolysis, and address the problem in, I would say, a different point of view than what you can find commonly. The fact that in electrolyzer, a component, which is the membrane or the diaphragm, is mainly responsible of the safety of the whole process, because you want it to be very effective in separating hydrogen and oxygen, of course. And of course, if the membrane fails, is a big issue, is a big, but also not, let's say, a spectacular fail, but also degradation of the membrane itself, crossover of the gas. This is quite a problem that has not been much addressed, at least is less addressed from an industrial point of view. And in this particular project, what is aimed is to use intermediate. They are called CA-ROC and A-ROC, which stands for cathodic redox couple and anodic redox couple, for which you actually make the electrolysis. And once they are activated in the activated form, They are fluxed through separate tanks in which they allow the oxidation of water and hydrogen production by reacting with water on catalytic beds. And so it's interesting. As I mentioned, it's very low TRL, so we are starting to understand things now. But it's good how this kind of different approaches feeds into our R&D process. Another project that I wanted to show you today is on the completely different side. So we have low TRL, but on the other side, we need to understand how the production impacts. As I was mentioning before, you can have spectacular ideas, but if they're not feasible on a production level, for us, doesn't make any sense because there is no profit for us. It needs to be sustainable. Usually the hinders is that we are focusing much on the innovation on the product, innovation of the material, but we are not focusing enough on the innovation of the production. So you have this obstacle in which you have interesting idea, new concepts, and then you are blocked by the fact that you have old equipment, old machinery, and the things has always been this way in terms of industrialization. So we have this project, which is quite large because it's a factory. I'm sorry, I had only the rendering at hand. Actually, the construction is already there. There is the building. So feel free to go and check if you want to see some pictures of the building at the moment. It's in Cernusco sul Naviglio, which is close to Milano. And the aim for this specific factory is to produce products just for the energy transition. So the hydrogen-related products and other products that we are currently developing. The aim is also to have very advanced equipment and large innovation within how you make things and how you produce materials and devices for the market. So this is pretty much all from my side. I hope it was interesting, even though maybe with a different perspective. I wanted just to wrap up with what we think the macro trends that we want to address for the future, for future markets. So in the energy sector, I already mentioned the hydrogen economy, which involves also fuel cells, and carbon capture and CO2 reduction is also quite a topic for us. We are not currently offering anything for the battery technologies, but we do have internal research to work on a next generation lithium-ion, the solid-state batteries and flow batteries, mostly for ES. On the other side, we have the recycling of strategic raw material, which we think is a growing sector. So for the energy sector, it has been around for quite a while now. The strategic raw material is a bit of a new take for us, but still it's growing quite fast, both in terms of electrochemical recovery of strategic material, for which we have already metal refining approaches, the circular economy integration, so understand how to use our products to create sustainable processes for material use. And finally, the electrorefining and electrodeposition, which I already mentioned. So this is all from my side. I hope you enjoyed the talk, and yeah, I welcome any question.
Thank you very much, Dottoressa Galliani. Is there time for questions?
Thank you very much for the really interesting talk. I was wondering only one simple question. Which is the target of your CO2 electro reduction plant? Which is the molecule, the target molecule?
Okay. We have, in terms of finance project, we have a couple of them. So the largest one, which is named Eco2Fuel, is targeting liquid fuels. So a mixture of reduced CO2 let's say molecules. I would say that the market is not set yet. So from a technology point of view, CO is the most commonly targeted molecule. But from some markets, for instance, the US market, Formic acid is also very interesting. So we have activities on both of them.
Okay, thank you very much.
You're welcome.
Maurizio.
Thanks. I am curious about the position of your company in the field of carbon dioxide sequestration. What do you think? It is a reality, just a dream, or something that will never be accomplished in the proper way?
You mean
Capture.
the specific capture? This is a difficult question. I would say that for us, at the moment, it's very early stages. And as for the hydrogen itself, there's the need for, I'm talking about the market point of view, there's the need of, let's say, stronger policies, stronger financing to be sure that this is implemented in a profitable way also for the company to adhere to it. And this is true for, I think, CO2 electrochemical reduction. It's for us quite straightforward since we are an electrochemical based company, but it's lower TRL. For sequestration is, I think, actually very true. So we need that kind of policies also for hydrogen. All the energy transition needs still that push, because at this time being, we are not, hiding behind a finger. Is not a profitable way to make, let's say, products. We need that kind of drive from the society to be sure that the company can sustain itself by. I think that we are already going there, so we have a lot of financing, but it's not there yet. It's not so pushed yet.
Okay, thanks.
You're welcome.
Any other question? Okay. If not, I would thank again Dottoressa Galliani.
Thank you.
Forse dagli offset, da hardware based, filmmaking e quelle robe lì. And now we have the coffee break, so please enjoy and come back on time for the next session. Thank you.
Good morning, everybody. It's my pleasure to start this section on coordination chemistry and catalysis. I'm Daniela Pappalardo from University of Sannio in Benevento. I'm glad to introduce Chiara Costabile with a contribution entitled DFT Studies on Cross-Coupling Reaction Catalyzed by Gold 1,3 Complexes. Chiara, please.
This is open? Okay. Thank you very much. Thank you for the nice introduction, and I would like to thank the organizing committee for giving me this opportunity to share with you some of the results that we had on a computational study that we made on cross-coupling reaction catalyzed by gold. Actually, gold lately became quite popular for this kind of catalysis, thanks to the coupled gold 1, gold 3, that is able to give a catalytic cycle that generally involves an oxidative addition, an exchange, and then a reductive elimination with the formation of a new bond that can be a carbon-carbon bond or a carbon heteroatom bond. The problem with the gold is that actually gold has a very high reductive potential with respect, for example, to the traditional palladium that undergoes this kind of catalysis with the coupled palladium 0, palladium 2. And this means that for several years, this kind of reaction were done in the presence of sacrificial external oxidants, which is not really sustainable as a synthetic method. So in the past 10 years, many efforts were done to make some ligands able to stabilize the gold 3 species, and in particular to have ligands with a main bond to the gold, and then a donor able to stabilize the gold 3 during the catalytic cycles. And much of the efforts at the beginning was done by Bourissou, that ended up in 2017 with this metal phos gold chloride complex that is one of the most popular complexes in this kind of catalysis. But very recently, also Ribas and Russell developed other kinds of ligand, Ribas with a MIC with an N donor, and Russell and contemporarily Sozak, they published a complex that with a ligand containing an NAC moiety together with a nitrogen donor. We were quite intrigued by this catalyst because in our department there is a very large experience in the synthesis of NHC ligands, and also because this catalyst, as shown by Russell, was able to catalyze a very challenging reaction, that is the 1,2 oxyarylation of alkene. This reaction is quite important because you can start for a very simple molecule like, for example, ethylene or propylene, and you can functionalize this molecule in one pot with an aryl and an alkoxy group, ending up with a much more complex molecule. And this is a very challenging reaction, actually, there was no mechanistic study yet for this kind of reaction. So first of all, we decided to study the mechanism, the catalytic cycle, and also after we tried to understand why this catalyst works so well, and how can we also improve the catalysis in this field. So I show you here directly the energy profile that we found. Here there is the the conditions, the experimental condition used by Russell. If you see here, you used a silver salt as a more than as a co-catalyst, because it's actually is like 1.2 equivalent with respect to the substrate, and also a base. And this silver salt is very important because you have to precipitate the chloride and activate the catalyst, and also is the driving force for the precipitation of the silver iodide to go to the product. So we started with the active species, where instead of the chloride, we have the hexafluoroantimonate coordinated to the metal. This can be substituted by the aryl iodide that then give the oxidative addition with the transition state, giving the gold 3 intermediate. Then the iodide can be precipitated by the silver and can be coordinated, can be substituted by the coordination of ethylene, then undergoes the attack of the alcohol, giving a high energy intermediate that can be deprotonated by the base, and after reductive elimination goes to the product. And as you can see in this reaction, the rate determining transition state is the alcohol attack. This was quite surprising for us because we thought that oxidative, actually many studies, previous study were focused more on the oxidative addition than on the other steps of this kind of reaction. But this kind of mechanism is able, for example, to explain why if you have a very electron withdrawing group on the aryl iodide, you got very low yields. These are always results by Russell, because you have a very high energy barrier for this transition state, and also why when you have a very electron donating group, this can be even worse. You got traces of product because it coordinates to the metal, making a sort of catalytic poison. So we thought that we could understand better the electronic and steric effects of the ligand, and also try to suggest how to improve the ligand design to low the barriers of the reactions. And we decided to exchange the original nitrogen, which is the donor of the ligand, with other possible donors, starting from the hydrogen, there is not a donor actually, or substituting it by the oxygen or by a sulfur or by a phosphino group. And what we saw is that if you take away the donor, of course, this energy barrier goes very high. And also if you substitute with the oxygen, but with sulfur and phosphorus that are soft groups, soft atoms, then these barriers go down, especially with the phosphorus. And we found that this is directly correlated, linearly correlated to the ability of this atom to donate the lone pair to the antibonding molecular orbital of the gold carbon bond. So if this donation improves, this transition state barrier goes down, and hopefully the catalytic efficiency improves. Also, we try to substitute the group on the other nitrogen with other group. The blue line is always the original, let's say, catalyst, in this case with the diorthoisopropyl phenyl group. If we substitute it by the terbutyl, the barrier goes up, but with methyl and methyl, the barrier goes down. This is directly related to the percentage of V barrier occupied by the ligand, with the exception of, so big ligands, big substituents are worse, with the exception of mesithyl and methyl, because actually the mesithyl gives this pi-pi interaction in the transition state with the aryl bound to the metal, and this low down a little bit the barrier. So we imagine to change the architecture of the NHC ligand, because the ligand that you see here are also very easy to synthesize and to tune also. And you can also introduce, for example, steric center, chirality on the backbone. And so we try to simulate how this ligand could work in this kind of reaction. I want to point out that some of these ligands are already in the literature, but were used on other metals, like, for example, NHC with ortho-substituted allyls with phosphino groups or with thiolate. And what we saw is that, so when you substitute the backbone with the electron withdrawing group, the barriers goes up. For example, with phosphorus, the barrier increases, whereas if you have, for example, a saturated backbone, the barriers decreases. If you substitute the donor with, as in the other case, with the soft and electron donating groups like the phosphorus, the donation ability improves and the barrier goes down. So it's like the results we have with the other ligand design. And if you change the substituents on the phosphorus, for example, going to using methyls or phenyls or adamantyls, what we saw is that the best catalyst design is the one where you put phenyls on the phosphino group, because this is able to decrease the barrier of the alcohol attack, but also decrease the barrier of the oxidative addition in the beginning of the mechanism. And I would like to underline that this ligand actually exists, but it was used only on palladium complexes, not on the gold, but it can be synthesized. So I hope that I convinced you that in this kind of reaction, we can stabilize gold-3 by using a NHC phosphorus combination, better if we use a saturated NHC backbone, and better if we use a low steric hindrance aryl group. For these studies, most of the calculation that you saw were done by Gaetano Galdi, my PhD student, but I would also like to thank Dr. Arthur Broughton-Roofs, that is a postdoc in my group and and is now working on this gold project. Actually, also on another reaction that for reasons of time I didn't show you, that is a comparison between gold and palladium in the arylation of alkyl nitrides, where the two metals give totally different chemoselectivities. I would like to thank my experimental collaborators that keep me with my feet on earth, and especially Professor Fabio Agrisi, that is my colleague and friend, and that accepted, together with Assunta D'Amato, to work with me on this project, as well as Laura Schaffer, that also showed some interest on this gold project. And I would like to thank Fabio Ragaini. We are working with him on palladium catalysis. He gave a very nice presentation yesterday. And for founding mainly the university and the Ministry of University, as well as the CINECA for the high performance computing system. And of course, I thank you for your kind attention.
Thank you, Chiara, for the presentation. There is time for one question from the audience. No one? I have a question. Actually, you believe in this result? Are you going to synthesize the gold catalyst, or what is your idea?
Yes, we are actually trying to. Assunta already made the thiolate substituted ligand, and we are willing to synthesize the one with the phosphorus to check if actually the catalyst efficiency improves.
Okay, we are looking for the results. So, okay, thank you once again. And now we have time, perfectly on time. We have the next speaker. It is Gabriele Manca. And the title of the presentation is again on gold, and this time gold and platinum electron richer than commonly considered inverted ligand field cases. Please.
So much. So first of all, good morning to everyone. First of all, I would sincerely thank the organizer for giving me the opportunity to show you some results of our research of the inverted ligand field cases in gold and platinum complexes. After a brief description of introduction of what is inverted ligand field, I will show you when the inverted ligand field occurs in the gold and platinum chemistry, and how we can tackle this kind of tool in order to rationalize the reactivity of gold and platinum complexes. So a brief description. This is the classical view of the electronic structures of a square planar complex of 11th group metal. Square planar. So we have that the bonding is assured by 4 donation from 4 assumed fully populated ligands combination into 4 assumed empty orbitals on the metal. In particular, this model is based on the assumption that the ligands combination are lower in energy than the metal d orbitals. Thus, we have a 3 donation from a 3 ligands combination into 1s and 2p, very high energy, thus empty metal orbitals. But the 4th one, that is the crucial one, is between the B1G combinations on the ligands that is assumed to be populated into the empty d square minus epsilon square orbital on the metal. So this is the assumption. Through the combination between these 2 orbitals, we have 2 combinations. One sigma bonding at populated, obviously, and ligand-centered, while the anti-bonding combination counterpart, generally is the LUMO, is mainly localized on the metal center. The question is it possible to reverse this description? Are there any complexes where the B1G combinations of the ligands is higher in energy than the metal d orbitals? So in the last years, we checked and analyzed the electronic structures of a large variety of square planar complexes of the 11th group transition metal. In particular, we started with this square planar of the copper Ca3 4-, which according to the classic interpretation, we could describe as a D8 copper 3 surrounded by 4 anionic Ca3- ligands. But when we analyzed the electronic structure, we found that conversely of what we expected, the LUMO that is reported here as a very strong contribution from the ligands rather than on the metal. Otherwise, the sigma bonding combination, very low in energy, has the opposite feature with the strong contribution from the metal rather than the ligands. So this means that the B1G ligands combination, in this case, at least in this case, is higher in energy than d square minus epsilon square metal orbital. And this means that it is quite improbable to be populated. Thus, a more accurate description of the electronic structure is of a D10 configuration for the metal with the sigma back donation from the metal to the ligand. So also the electrophilic feature generally assigned to the metal is now transferred to the ligand. And this is the inverted ligand field. We found that this inverted ligand field is quite ubiquitous in copper chemistry. And the percentage of the contribution of the metal to the LUMO becomes like a fingerprint on how we can classify the bonding between the metal and the ligands in the different complexes. So if, for example, the metal contribution to the LUMO is less than 40–45%, we have the inverted ligand field. If it is close to 50%, we have the perfect covalent description. Otherwise, we have the classic description. So this is the copper. But if we go from the copper to the gold, we have that the d orbital energy is lower. So they are stabilized compared to the copper. So this means a more frequent occurrence of the inverted ligand field. Here, for example, I reported the plot of the LUMO for the parent compound of the gold Ca3–4-. And as you can see, you have also in this case a large contribution from the ligands rather than the metal to the LUMO. So understanding the electronic structure of this square gold complex is particularly important because this kind of complexes are used, for example, as catalysts or intermediate in catalytic processes, but also for the design of anti-cancer complexes. So understanding the electronic structure may help in understanding also the reactivity of these complexes. We focus our attention especially on the electronic structures of square gold complex where the metal is associated with the most electronegative elements of the periodic table, such as, for example, the halogens. Here I reported you the cases for the gold tetraiodide. So you can see here the populated molecular orbital with the large contribution from the d metal orbitals, and in addition also the LUMO. As you can see here, you have the contribution from the metal and the ligand. As you can see in the LUMO, we have a very limited contribution from the metal, is 20%. So we can assure that here we have the inverted ligand field occurrence. But this trend, the occurrence of the inverted ligand fields, is also recognized in gold tetrabromide and also in gold tetrachloride, because even though in going from iodine to chlorine, the electronegativity of the halogens increase, thus the B1G combination should be stabilized, this is not enough to have the change of the description of the bonding. So we have that also in gold tetrachloride, the most accurate description is of a gold or D10 configuration for the metal with the sigma beta donation from the metal to the ligands. The only exception is the gold tetrafluoride, so the most electronegative elements of the periodic table. And in this case, we have a contribution close to 50%. So here I reported to you the linear correlation that we found between the gold contribution to the LUMO and the sum of electronegativity of halogen around the metal. Also considering some mixed halogen complexes. The same trend is also obtained for the chalcogenides, except for the oxygen, once again, that is for which the most accurate description is a covalent bonding. So we conclude that the inverted ligand field is ubiquitous also in the gold chemistry, except when the gold is associated with 4-fluorine or 4-oxygen. So the problem is how we can handle this in order to try to rationalize the reactivity of the gold. And we focused, for example, to what we traditionally classified as oxidative addition of the halogen molecule to a linear complex of the gold with the carbene and chlorine. This is a work in collaboration with Rossana Galassi at the University of Cameroon. So from this reactivity, we obtain the square planar complexes where featuring 3 halides and 1 carbene. But if we look at the electronic structures of the products with the possibility of isomerism, we found that in all these cases, the metal contribution is very low, thus the inverted ligand fields occurs again. So this means that the metal is more electron rich than what we expected in the, according to the classic view. The system evolves through an initial halogen bonded adduct. After this, we have the formation of a tricationic T-shaped species, this one. And this is also just already in this intermediate, we have the occurrence of the inverted ligand field. So this may help, this is hardly to classify, that is an oxidative addition, but possibly the most accurate description is of an heterolytic system of the halogen molecule. Next step, is it possible to extend this description also to other metal and other, for example, geometries? And for example, like octahedral species, where we should consider two in place of one combinations of the ligand and one metal orbitals, the d square minus ipso square and the dz square. So in collaboration, this is particularly important, for example, for platinum 4, for the complex classified as platinum 4 octahedral that are ubiquitous also this in chemistry, as for example in catalytic cycle, or also for their strong and efficient anti-cancer properties. In collaboration with Francesco Ruffo, we studied the electronic structure of some octahedral platinum complexes where the metal is associated with halogens again. And as we can see, this is as done for the gold. I reported here the LUMO and LUMO plus 1, so the two lower unoccupied molecular orbital for the platinum hexaiodide. And you can see the very low contribution of the metal to the molecular orbital, the LUMO, and LUMO plus 1, while the corresponding bonding is mainly localized on the metal. So, conversely of what happened in the gold, we have that here, the larger is electronegativity and the more accurate description becomes the covalent one or the classic ligand field. Because we have the iodine and bromine, we have the inverted ligand field. Chlorine approaches the covalent or quasi-covalent description of the bonding, while for the fluorine we have the classic ligand field. So, as done for the gold, we focused our attention, for example, on the activation, generally classified as oxidative addition of a selenium-chlorine bonding performed by a square planar platinum complex to obtain this octahedral complex. So we have that the percentage contribution to the lowest unoccupied molecular orbital, in this case the LUMO plus 2 and LUMO plus 3, are less than 30%. So also in this case we have the occurrence of the inverted ligand fields. The reactivity evolves through an initial transition state featuring a linear platinum selenium chlorine. So we have, after the release of the chloride, the formation of this square pyramidal intermediate cationic with the coordination of selenium, and also in this case we have the occurrence of the inverted ligand field. So, in conclusion, I hope that I show you some hints and some information about how we can use the inverted ligand fields for the 11th and 10th group of transition metal fragments. That the metal center in these complexes are less oxidized than what we expected, traditionally expected, and this open a very interesting research, for example, for a possible interpretation of the metal role in biological cycle or in catalytic cycle. There is also, for example, some influences of the inverted ligand fields, for example, in the study of redox properties that for time reasons I escaped this time. So in conclusion, I would sincerely thank all the researchers involved in this kind of research, and obviously you for your kind attention.
you, Gabriele, for the nice presentation. Are there questions from the audience? One question.
Thank you so much for your presentation. Paul Walton from the University of York. The notion of the inverted ligand field is one that experimentally we're finding difficult to verify. What is your advice for us experimentalists to what to look for experimentally to confirm the inverted ligand field?
Okay, thank you so much. Firstly, I would, for example, we are interested in trying to have some experimental evidence, as you asked. And up to now, because interactivity is not sometimes easy to isolate intermediate or in the reaction. But we found in collaboration with the University of Siena and the University of Bologna that, for example, in this kind of cluster, that is a mixed gold-iron cluster, pentanuclear cluster, we have that this is generally classified as gold-3 surrounded by 2 iron, 2 CO8, 2 minus unit. And this undergoes 2 1-electrons reduction processes. But we found that, for example, they succeed in the, for example, in the isolation of the de-reduced form. And as you can see, you have that the one gold-iron linkage is broken. And this could be also, I know is not direct proof of the inverted ligand field, but we have also that the carbonyl ligands becomes also bridging. So this means that the iron should be most involved than gold in the reduction processes. And so more acting as back donation to the gold, to the carbonyl. I know that is up to now is not so easy to have the shooting gun of the, experimental one. So we are looking for some experimental evidences. Thank you.
Okay, thank you so much.
Thank you.
And we thanks again you for the contribution. And now, next speaker is Christian M. The contribution is entitled Data Science in Organometallic Catalysis, Database and Future Maturation, Allowing Coordination Geometry, Independent Statistical Models. Please, Christian.
Thank you for the introduction. And thank you to the organizing committee for allowing me to be part of this very nice conference. I'm talking about data science today, and a little bit about the way and the reasons why we're doing these things the way and why we think maturation of certain things is a good idea. So the data sets I'm showing are from olefin polymerization, and I have highlighted a couple of things that are challenges in this regard. One is the small size of the data sets. Capital investment for each data point is very expensive. But what's really critical is the high turnover frequencies and the very high complexity in the chemistry. And that's not necessarily, I'm not saying this is more complex than anything else, but it poses a challenge from the perspective of getting things in the computer and digitalizing information. So if you think about modeling, 3 reasons why you would be doing modelings and 3 pillars. Like you have your experimental database. If you want to do predictions, your catalysts need to live in a computer. And then you have your model that connects questions to answers. And you do it to either understand, to predict, or to curate data. And not all things, like you can do all things at once, but you can do this via different approaches. How good does a model have to be depends a little bit on where you want to go with your model, right? If your errors from your model are a nuisance, like in this example from NASA, where the AI occasionally forgets to put attachment points and building blocks, you just throw it in the garbage can. if you think about chemistry, if we could reduce the number of potential catalysts from 1,000 to 10, that would already be very helpful. And if only one of those works, that's great. And this is a contribution on a preprint, basically, of the Sigmund group that kind of goes into that direction. The question is, and you see that here in the model, where? You see this in this model. This is potentially an exciting future where you generate a new ligand framework or whatever, and then do most of the optimization in the computer and arrive at the fully optimized catalyst. Whether that's possible probably depends a little bit on the chemistry you're looking at, and occasionally you might have to go back into real space to generate more training data. So we heard a lot about DEF yesterday, and that's one of the things. If your model is wrong and that has real world consequences, that's bad, right? In chemistry, we usually get do-overs, so you can repeat experiments, and we can correct models, basically. What we need to do there is we need to introduce a level of doubt. Doubt is a really good advisor. It's essentially the basis of science, right? We can never prove a hypothesis. We can only come up with competing hypotheses and then disprove those. But it's a really bad companion. You can't just doubt your whole data set. On the right side, you see that nice example with noble gases, right? That was doubt-driven. So the challenge of kinetics is actually that we're shooting at a moving target. It's a subjective reality, if you think about it. And in difference to, for example, data from the CCDC that has been curated and has very, very high quality. If you go from the left to the right here, the data quality and this challenge in digitalization actually increases. And the reason for that is that we usually use dimensionality reductions, which we call general reaction conditions, right? But whether this is true throughout the whole data set is actually not guaranteed. Simple example, you have an hexagonic reaction. If your temperature management fails, temperature increases, the cell activity goes down. That doesn't matter if you want to develop a drop-in solution, but if you want to fully optimize catalysis, that's actually very important. Now, you can look at the 3 pillars of data science individually. You can have your experimental specialists, your computational people that generate structures so that the catalyst lives in the computer, and then mathematicians as modelists, basically. But what I'm here to argue is basically you should look at this holistic. Like the whole thing is the model, basically. You have your experimental space, your feature space, and your model space. And if you understand all 3 of those, if you can navigate these, you can actually identify poor data points, poor featureization. Everybody who has ever modeled knows that usually you start with a model and then you try to figure out why it doesn't work. And occasionally this is bad data points. So simple models that you can understand and that you can actually test, so that allow testable hypotheses, allow the identification of bad data points because they betray themselves through distinct behavior. And that's important in automated processes if you think about a computer doing the full optimization. So the data I get to work with is high throughput experimentation data, which is great. Every modeler's dream, basically. And there's a lot to say about this. I don't really have the time for this, but this furnishes very high quality experimental data, basically. And there's a lot of innovation and work going on before I ever get to deal with the data that's generated, obviously. Our current modeling approaches use multiple linear regression. That's where that interpretability comes in, right? And it uses chemically intuitive descriptors because you need to be able to navigate feature space. We use active site fingerprinting via 3D steric descriptors, and that allows us a catalyst class and metal independence. We use deconvolution of regions in the active sites, and that then allows the model to waive a contribution, and the one active pocket principle, which basically says if you understand one chemistry that a catalyst can do, then you have already most of the starting points to understand what other things it can do, basically, right? So when we originally started this, we started with a single catalyst class. That was metallocenes, and here you see a little bit the regions that go into the featureization and then are afterwards weighed by the model. And I'm not going to show the model itself. Safe to say, you can actually use it for predictions. But what's really the crucial thing is that this is a relatively crude approach because we were only looking at one catalyst class. There's only so much you can learn. And when we were expanding the application range, there was the question, are we just using the workflow, or are we increasing the application range? We decided to do the latter, actually. And in order to increase an application range, you need to understand feature space, essentially. Electronic descriptors are an important part, and this is the slide basically that shows what we did to start understanding what happens in the feature space. So most of the common electronic descriptors, the whole functional molecular orbital concept, is not usable if you have more than one catalyst class. This is because the HOMO is located on the ligand. One other important thing is that, and you see this here on these two graphs, is that most electronic descriptors only categorize. So if you want to describe more, this electronic descriptor is not relevant which one, can only recognize metal differences once you start putting in a lot of different species. And that's basically not the reality of olefin polymerization. While in this case, you can clearly see that metal and ligand differences are resolved and this whole thing develops a continuum. This is our current generation of MLR models for region selectivity. And you can see that it can even describe different coordination geometries, 2 different metals. It only uses 5 descriptors that deconvolute the regions. It is very stable. You can take out the top 20 performers and repredict, and the accuracy is very high there. And basically from this set of descriptors, we develop all the other performance indicators that so predict other things the catalyst can do. On this slide, there's another example of the importance of covering chemical space and performance space, basically. You see here, we can basically only use 20% of the whole data to train the full model. And that's because these 18 data points represent very well the performance space, and they actually do also represent feature space very effectively. And we compared this to an unbiased MLR approach, and our hand-built model is essentially the top performer. And you can also see that it's only humans that think in terms of tetrahedral and octahedral. So this brings me to the final point I wanted to make, and I'm going in the wrong direction. And this is this question of negative feedback loops and the moving target in catalysis. So on the left, you see an example where here we have the kinetics, so the activity, and here we have a molecular property, so this is polymer weight. And as the catalyst becomes faster, the molecular weight starts dropping. Now this is from the same catalyst to make this visible, but if you see this in the screening, what you would actually get is basically a maximum. You get like a volcano plot where you get an optimal performance at a certain activity. The thing is, that's a mirage, and the models can tell you this. And if you regain control of the catalyst, this actually looks like this. So now you see me. So this is basically the whole vision. These simple gatekeeper models are a little bit slow, but for real data, they can actually be slow. So we want to pair these HDE data with adequate digitalization feature population of the feature space, and simple gatekeeper models that basically run in a loop and guarantee the data quality, which is similar to these processes that are in place as the CCDC. With that, I want to finish my talk. I want to thank you all for your kind attention. And there's one straight line. There's thousands of man hours, not just for me going into this, and a lot of money. Special thanks to Vincenzo, Roberta, and Peter, and of course for all LSP members who have generated the experimental data I'm getting to handle. Thank you.
Thank you so much for the presentation, Christian. There is time for a couple of questions from the audience. No question? I have a curiosity. Are you applied this model mainly on olefin polymerization catalysis? Do you think are you going to expand to other kind of catalysis or?
So these catalysts are able to do more than just olefin polymerization, and that's one of the goals we have, to extend the application range also to other types of chemistry. But what you need is expand the experimental data to start the training there.
So the olefin polymerization catalysis was good as a benchmark for the...
It's really good for training because the data that you're getting actually can teach you so much. I showed regioselectivity because that's the most complex one, but it also very nicely stretches out the active pocket, so you can actually featureize way better with this data than with types of other data.
Okay, thank you so much. Thank you so much. And we thank again Christian M. And it's time for the next speaker, that is Azeveda Portela dos Santos. The title is Exploring the Orthometallation of Phenanthrolene go back, please. At triruthenium acetate complexes by mass spectrometry. Nicole, please.
Good morning, everyone. My name is Nicole. I am a PhD student at University of São Paulo in Brazil, but I am currently a guest researcher in University of Freiburg in Germany, where I've been exploring the orthometallation of phenanthrolene using triruthenium acetates by mass spectrometry. And today I would like to share with you some of the results that I've got so far for this project. Well, triruthenium complexes are clusters composed by triruthenium ions, like these ones, bound through acetate bridges and oxo bridge in the center. These complexes usually bears N heterocycles as ligands, and also small molecules such as carbon monoxide and O and other anions. Well, these complexes are very interesting because of the great electronic delocalization within the ruthenium ions and the oxo bridge, which leads to many interesting chemical features for these complexes. The literature has reported already the application of these complexes in catalysis systems, in supramolecular chemistry for extended structures, and also as potential metallodrugs. In fact, our group in Brazil has reported anti-cancer and anti-parasitic activities for triruthenium complexes bearing isoquinoline ligands, and also vasorelaxing activity for a nitrosyl compound bearing pyridine-type ligands. Well, these complexes also have been described bearing orthometallated ligands by the coordination of polypyridines such as phenanthrolene, bipyridine, and other ligands in this coordination mode. And for these complexes, we also have seen the application in extended structures and mixed valence chemistry, and also as potential metallodrugs for anti-cancer and anti-trypanosomal activities. And today I will talk with you about this reaction, this orthometallation reaction between this ruthenium complex bearing two isoquinoline ligands this lay-by opposition from the coordination of the solvent with the phenanthroline leading to this complex. This structure shows this coordinating mode where both nitrogen atoms binds to the first ruthenium in a bidentate fashion, and then the orthocarbon is able to bound to the second ruthenium, leading to this orthometallated coordination mode. And for this reaction to proceed, we know that C8 bond activation is required, and it happens at room temperature, which is a very interesting reaction for us. So we will study this reaction using mass spectrometry, electron spray mass spectrometry, once both the precursor and the product are charged species. Well, as in all the other cyclometallation reaction, or in our context, the orthometallation reaction, the first step of this reaction is the coordination of the polypyridine ligand, the phenanthroline, by the donor atoms, which are the nitrogen atoms for phenanthroline. And we did this reaction in 2 different solvents, dichloromethane, which is a non-coordinating solvent, and also acetonitrile, a coordinating solvent. And what we found for this experiment, it is that when we set the reaction in acetonitrile, we observed that our main ion in the system is the compound bearing the acetonitrile as ligand. So phenanthroline is not able to substitute this solvent when we set the reaction in acetonitrile. But when we do the same reaction using dichloromethane, we observe the substitution of the solvent by the phenanthroline ligand in less than 30 minutes, which doesn't happen for acetonitrile even after 4 days. Here I describe this structure in a bidentate coordinating mode, but we still don't know if the phenanthroline is bound in a monodentate or in a bidentate fashion. So this is the second question that we want to solve for our system. And for that, we used these CID experiments, the collision-induced dissociation experiments, where we are able to select one of the ions from our mass spectra, and then we can induce collision from this ion with inert molecules such as some gas. And with this, we can fragmentate our ion in smaller pieces and then be able to describe a little bit better what are the fragments that compose our interested ion. And we did this for this ion that I showed you before, which is the main species of our mass spectra. And when we do the CID experiments, we observe the loss of one isoquinoline, which is one of the ligands of our ruthenium cluster. And here I would like to compare the isoquinoline with phenanthroline once both ligands are the nitrogen donor ligands, which is very interesting. So if the phenanthroline was bound in a monodentate fashion, this ligand would be very similar to isoquinoline. And then we would be able to find both isoquinoline and phenanthroline losses. But in this CID experiment, we only observed the loss of phenanthroline. And when we do again another CID using the last ion, we observe again the loss of the second isoquinoline from the precursor, and also the loss of acetic acid from our precursor ion. Again, we don't observe any loss of phenanthroline. And if we do another experiment of CID in both ions, we observe the loss of acetic acid and the isoquinoline, leading to the same ion, the same product, which is an orthometallated ion, where the nitrogen is bound to one ruthenium and the orthocarbon to the second ruthenium, without both isoquinolines. And so once we didn't observe any loss of phenanthroline, we could conclude that this ligand is bound in a really strongly way to the ruthenium core, which is very compatible to the bidentate coordinating mode instead of the monodentate fashion. Well, the second step of a cyclometallation reaction, which is very similar to the orthometallation, is the C8 bond activation once the phenanthroline is already coordinated to the ruthenium core. And analyzing our solution during time, again, using mass spectrometry, we observe the decrease of the concentration of our complex precursor and the increasing of the intermediate complex of our system, which is this bidentate complex that I showed you before. But after about 5 hours, we see again the decreasing of this intermediate concentration to produce our orthometallic product. Here I would like to highlight the structure of our product, which has one less acetate than the intermediate and also one less proton once the C8 bond activation already occurred. Well, we have a challenge here because once C8 bond activation is an intramolecular reaction, we have possible intermediates which have the same MZ than our bidentate complex, and I show you here. We propose that a possible intermediate for our reaction would be this agostic intermediate, which the metal ion is bound both to the hydrogen and the carbon from the bidentate ligand, which occurs before the C8 bond activation, and also this complex after the C8 bond activation, where the orthometallic phenanthroline is already there, but we still have acetic acid coordinated to our complex. So again, both intermediates have the same MZ as our bidentate complex, which is very difficult to distinguish using just mass spectrometry as our So because of that, we did some DFT calculations for our mechanism, and for that we proposed the presence of one agostic intermediate that I show you here, where the ruthenium ion is bound both to the hydrogen from phenanthroline and also the carbon. And this hydrogen is also approaching to the acetate, the bridge acetate of the ruthenium core, leading to the C8 bond activation and the releasing of one acetic acid molecule. For this mechanism, we propose main 3 steps. The first step would be the bidentate coordination of phenanthroline from the monodentate species. The second step would be the production of this agostic intermediate from the bidentate complex. And the final step would be the actual C8 bond activation, leading to this complex bearing the acetic acid coordinated to the ruthenium core. And for this mechanism, the rate determining step for our reaction would be the production of this agostic intermediate. Well, in summary, I would like to highlight some things about my work, which are, we propose from our CID experiments that our main intermediate of this reaction is the bidentate complex from the bidentate complex from phenanthroline. And from the FDA calculations, we propose the presence of this agostic intermediate before the C8 bond activation. And as perspectives of this work, we still want to evaluate the influence of some substituents into this orthometallation reaction. And also, we want to do some NMR experiments to get a better results according to our DFT mechanism that we proposed before. I would like to thank you all for your kind attention, the scientific committee for this opportunity. Thank you.
Thank you, Nicole, for the nice presentation. There is time for a couple of questions. Are there any questions from the audience? No question? I have a curiosity. What is the challenges in obtaining crystal structure of these complexes?
Many challenges. Yeah, to get the trinuclear complex is very simple. We just react acetic acid, acetate, and ruthenium chloride, which is very simpler. But when we want to do this asymmetric cluster, we have to first coordinate the isoquinolines, but we have to protect one position, and then we have to disprotect this position to get the second ligand. So it's about four steps for this synthesis, which can be about 1 month with low yields also.
Okay. So it's difficult to obtain
Yeah.
single crystal for X-ray. Okay, thank you so much. Thank you so much. And now it's time for the next speaker, Claudio Garino, please. The title is Copper-Based Complexes for Lighting Applications. Claudio, please.
Tipo qui non c'è la possibilità di mettere. Okay, thank you, Chair, for the introduction, and good morning to everyone. As Professor Pappalardo said, today I will talk about copper complexes for lighting applications, and but why lighting? Illumination has always been a fundamental need for humankind for several reasons, and we cannot even imagine our life without artificial lighting. In the last century, the efficiency of our lighting systems has increased tremendously, as you can see from this picture. And today on the market, the two leading technologies are light-emitting diodes, LEDs, for lighting purposes, or organic, like light-emitting diodes, OLEDs, for the flat panel display technology. So for the future, the goal is to develop high-quality, energy-efficient, and resource-efficient technologies. And for example, here I report a light-emitting electrochemical cell. That is a thin layer, solid-state lighting device intended for lighting purposes like LEDs, but with a flat and layered geometry typical of OLEDs. So basically, an LEC can convert electric current into light using a single layer of active material sandwiched between two electrodes. So light-emitting electrochemical cells are very simple, very cheap. They can be processed using low-cost fabrication technologies. They can be applied on also flexible or even stretchable substrates. So they are very, very interesting. They also have some issues like the low performance and the lack of blue emitters. In particular, this last point is critical because a light-emitting electrochemical cell can emit green light or yellow or red light, whereas some is yellow light, but for the moment, without the blue part of the spectrum, we cannot cover the whole color space, and this is a problem. So the goal here is how to make this yellow device blue. So how can we make a blue light-emitting electrochemical cell? Well, the answer has been at first iridium. Indeed, iridium complexes are able to emit blue light, but unfortunately, iridium is too rare and expensive as an element for a sustainable and low-cost technology. So scientists are looking for cheaper alternatives, and for example, silver or copper. And in particular, we focused our research on copper, on cationic heteroleptic copper complexes that are a promising family of compounds to face this blue challenge. So now I will show you 12 new copper complexes. They are based on a copper-1 cation chelated by the same bulky xanthos ligand reported here, and by a series of 12 different pyridyl pyrazoles characterized by the presence of different substituents in different positions. Here in the table on the right, you can see the substituent that we employed on the two positions that we changed. For time reasons, I will skip the details on the synthesis. However, you can find everything on poster number 94 that is delivered by Chiara Reviglio, and so please check it during the next poster session. Concerning the structural characterization, this was performed using quite standard techniques like NMR spectroscopy, mass spectrometry. Here you can see the structure that we obtained using X-ray diffraction data. But for now, let me go straight to the photophysical characterization, because the photophysical properties are very, very interesting. Indeed, these 12 white complexes that absorb light in the UV region of the spectrum, well, they are able to emit blue light. Both in solution and at the solid state, as you can see here from the picture. Well, actually, some are more blue, some are a bit green, one is almost yellow, but anyway. They also have a reversible electrochemistry. Here I report an example of cyclic voltammetry. And this is very nice. And in particular, if we start discussing the electrochemistry, well, this is a crucial aspect, because in an electroluminescent device, the material is excited electrically. So this means that in this case, the oxidation of copper-1 to copper-2 must be reversible, as it is indeed. And this means that the bulky xanthos ligand that we employed is able to effectively prevent the let's say, the structural rearrangement of the oxidized species to the flattened geometry typical of copper-2, and we must avoid this flattening. For looking at the oxidation potential, the value is about 0.8 volt, and this is almost constant for all the complexes of the series with very small differences. And this is quite reasonable, because the oxidation is centered on the metal ion, with a small contribution from the phosphorus atoms of the xanthos, as you can see here from the calculated metal-centered HOMO reported here in the picture, in the middle. This means that the pyridyl pyrazole ligand has a very, very limited influence on the oxidation potential. Well, on the contrary, this ligand is strongly affecting the emission properties of the complexes, because the main electronic transition is a pure HOMO-LUMO metal to ligand charge transfer. And here on the left, you can see the electron density difference map between the metal-centered HOMO that I already showed, and the LUMO that is totally localized on the pyridine pyrazole ligand. And this is very important, actually, because means that changing the level of the LUMO, we can we can change the color of the emission without affecting the oxidation potential. Indeed, as you can see on this graph, we are able to blue shift or red shift the emission of about 100 nanometers, going from blue to green to almost yellow. just employing more or less electron donating or electron withdrawing groups in different positions on the pyridine pyrazole. Another key aspect is the emission mechanism, because when electrons and all recombinates, they statistically generate 25% of singlet excitons and 75% of triplet excitons. And this can be a problem, especially for organic emitters, because we don't want this double emission. And actually, in the case of copper complexes, this problem can be prevented by a reverse intersystem crossing that from the triplet excited state repopulates back the singlet excited state, ending with the emission of delayed fluorescence. Well, it is provided that the energy gap between the two excited states is small enough to be thermally bridged at room temperature. And this is actually true in our case. Indeed, from a variable temperature lifetime measurement, like the one reported here in the middle, I can state that at room temperature, 85% of the emission is due to a thermally activated delayed fluorescence. And only the residual part, the small residual part, is due to phosphorescence. So now it's time to see how these complexes perform in a real device. And here, as a proof of concept, I report a couple of light-emitting electrochemical cells. Build one, build with employing a more blue emitting complex, and the one on the right with using a bit green complex. And as you can see, the color difference of the light emitted by the final device is quite evident, meaning that we are indeed able to tune the color of the light emitting electrochemical cell, playing with the substituents on the pyridine pyrazole. So I can conclude saying that heteroelectric copper complexes are very promising systems for solid-state lighting applications. That bulky ligands like the xanthos that we employed are able to limit effectively the structural rearrangement between the two oxidation states of copper. That pyridine pyrazoles can be successfully used to tune the color of the emission into the blue, and that our devices, although prototypes, are the first example of copper-based light-emitting electrochemical cells able to emit blue light. So you can find a small part of this work already published on advanced material, but more is coming in the next month, I hope. And for concluding, I'd like to thank all the collaborators that worked with me on this topic, in particular Chiara Reviglio and Luca Cavinato, who performed most of the experimental work at the University of Turin and at the Technical University of Munich. And thank you all for the kind attention.
Thank you, Claudio. Very nice talk. There is time for a question. Are there questions from the audience? Please.
Thank you. Great talk. I like it a lot. You're probably going to tell me one problem at a time, but I see you solved this situation with the lack of blue emitters. What about the performance?
We kind of solved the situation with blue, even if we need a bit more blue emission, actually, because we are at about 470 nanometers, and we have to lower a little bit still to go to the blue like 450. Anyway, the performances are decent for the moment. The luminance is fair. The stability needs to be improved. Obviously, this means that we have to work much more on the device part, more than on the chemical part for the moment. And
Not on the chemical part.
the optimization of the layer of the device is crucial. So there is plenty of space to optimize the performance from that side, actually.
When I see these complexes, I cannot help thinking about Oliver Reiser in Regensburg. Are you aware of his work? He used similar complexes but for photocatalysis. I don't know if there you might have some inspiration or ideas to further tune your system.
Okay, no, actually not, but I need to check it.
We can check later.
Yeah.
Okay, thank you.
Okay. If it's quick, please.
Sorry.
It's difficult to hear.
Just a curiosity, did you try to study zinc-based complex instead of copper one?
I studied zinc complexes in the past, not with these ligands, and we can try, but the electrochemistry of zinc is tricky. So,
okay, thank you.
Thank you.
We have no more time, so thanks again, Claudio, and we can continue the discussion with the topic there. And time for the next speaker, Raffaele Fontana, unraveling the reactivity of bismutidine towards orthoquinone. Unveiling, sorry.
Good morning to everyone. I'm Raffaele Fontana, and today I'm going to present a part of my work as a PhD student in which I studied the reactivity of bismutinidenes towards orthoquinones. Bismutinidenes are also known as compounds in which the bismuth is in the oxidation state +1. Those compounds generally can be seen as analog of carbenes and nitrines, but due to their unusual low valency, they are unstable and they readily react or they undergo decomposition. That's why in the last decades, many different studies were focused on developing new type of ligands that could stabilize the bismuth-1 metal center. Those generally implied the use of polydentate chelating Lewis-based ligand, which upon donation stabilize the bismuth-1 compound, or highly sterically bulky ligand that can protect the bismuth compound from further reacting or from decomposition. Though, if the ligand are not bulky enough for the donation, is not enough for the stabilization, those compounds easily undergo dimerization or cyclization, leading consequently to the formation of these species bearing bismuth-bismuth double bond or cyclic oligomers, also known as cyclobismuthanes. Previous studies that were performed have displayed the potential of low-valent metal of the main group of undergoing cycloaddition with orthoquinones, such as the study that has been performed previously in France, showing the cycloaddition of germylens to orthoquinones, forming germanium for catecholates. Moreover, the usage of orthoquinones is pretty also interesting in low oxidation bismuth chemistry because it has been recently used by Lichtenberg in order to demonstrate and to trap a bismuth-1 intermediate that has been formed during a reaction mechanism, so could be helpful in order to study what's actually happening. So that's why, starting from this, we decided to check and to analyze the reactivity of those compounds towards bismuth-1 species. So the first part of the work has been mostly focused on the synthesis of bismuth-1 compounds. So in this case, we started from already known bismuth-1 species, a cyclobismuthane, in which the R group is an N-N-dimethylbenzylamine. This compound the synthesis already known in literature, but is actually not reproducible due to the problematic reduction with sodium in liquid ammonia or with lithium aluminum hydride. Upon reduction, mostly metallic bismuth directly form. So we developed a new procedure using instead potassium selectride, which is a strong hydride donor that upon formation of monoorganobismuth hydride, it undergoes easily reductive elimination, forming a cyclic structure. In this case, the cyclic structure presents an interesting equilibrium between a 3-member and a 4-member ring, which is temperature dependent. Though those compounds are extremely unstable and at temperature which are higher than -30 degrees, they easily undergo decomposition, forming bismuth-1 species and dibismuthane. Also, from the NMR was also noticeable the presence of 3 sets of signals which are related to the 3-member ring and the proton of the 2 non-equivalent R group on the 4-member ring. Once those compounds were directly synthesized, it was possible to react them in situ due to the problematic isolation of them with the orthoquinone. So we started directly with the 3,5-diters-butyl orthoquinone, showing directly the formation of these species. In this case, it was also noticeable a strong change of color upon addition to an intense blue color that then slowly disappeared, probably due to the formation of a radicalic intermediate. It was also possible to crystallize this compound, showing that the bismuth is a pentachlorinated bismuth with a highly strong interaction between the oxygen of the catecholate moiety of another bismuth species. When then we decided to also change a different type of quinone, we decided to use orthochloranil. The problem that we made up by reacting this compound with orthochloranil is that we had different results based on the temperature in which the reaction has been performed. When the reaction was performed by letting it reach room temperature overnight, not only the cycloaddition adduct, but also a direct chlorination product were obtained. This didn't occur when we kept the reaction temperature overnight at -25 degrees, where only the cycloadduct product has been instead obtained. And this was clearly noticeable from the NMR of the 2 reaction mixture, the one at low temperature and the one at room temperature, showing clearly the presence of both the chlorination product and the cycloaddition adduct, both in the aromatic and also here in this case is noticeable in the aliphatic area of the NMR. Then we decided to also try to change the R group on the bismuth compound. So in this case, trying to put more pendant arms or have a higher stabilization of the bismuth metal center. And so we started from this analog in which instead 2 amino donors are present. And in this case, as before, the reaction went pretty straightforward. It was directly reduced in situ because it was never possible to isolate fully this compound. And always, in this case, the cycloadduct were directly formed, always showing a transient color change that was observed after the addition of the quinone. Also, in this case, it was possible to obtain a single crystal, crystal structure that was studied. And in this case, due to the coordination of the 2 nitrogen arm, not a dimeric structure directly was present, but mostly dimeric supramolecular interaction that led to the formation of a dimer with a way longer bismuth-oxygen interaction compared to the previous one shown. And then we decided to upgrade. Instead of using an arm that could actually move, we decided to use a pyridyl group that can actually is more rigid to increase the rigidity of the bismuth compound. Though in this case, the synthesis of the ligand was a bit more complicated because we needed to pass through the use of an organomercury derivatives and then transmetallate it to the bismuth bromine in order to obtain compound, the organobismuth derivatives. And also in this case, the same pathway has been done in order to reduce it in situ with potassium selectride and then reaction with both orthoquinone. In this case, it was noticeable that this bismuth compound was way more stable than the one previously shown due to the formation of an aromatic bismazole ring upon coordination that further increased the stabilization of the species. Also in this case, we managed to obtain a crystal structure, but due to the extremely low insolubility of the compound, the DMSO was needed in order to break the dimer and coordinate to the bismuth, showing that probably also this species was a dimeric due to the donation of only one nitrogen to the bismuth, and consequently DMSO was needed, and also in this case, as previously, dimeric interaction, supramolecular interaction were noticed between bismuth and the oxygen of the other catecholate moiety. Lastly, we decided to try with a way more stable bismuth-1 compound, so 2-pyridyl group that upon donation form 2 bismazole ring that can way more stabilize the species. So this compound has been obtained. Firstly, the carbon skeleton has been built through steel cross-coupling, and then consequently, as previously, we activate this position through mercuriation, and then we insert the bismuth to transmetallation with bismuth bromide. It's need to mention that this species is extremely stable at room temperature. Differently from all the other bismuth-1 compound, this doesn't undergo decomposition but can be kept in solution. Though we are still working on trying to isolate it, since the high planarity of it doesn't let it to be extremely soluble in comparison to the other bismuth-1 compound, and it's pretty hard to crystallize and to work with. So in this case, we added it to the orthoquinone, and with diterbutyl orthoquinone, we had no problem. We always obtained the cycloadduct. But with the orthochloranil, in this case, we always obtain a mixture of product, no matter the temperature that we are working at. We also managed to obtain the crystal structure of the diterbutyl orthoquinone that showed us previously that the bismuth in this environment is satisfied, so there's no further interaction with it. And then we synthesize again the cycloadduct in order to further confirm its structure, because in the cycloaddition methodology, we always obtain a mixture. So consequently, we obtain it by direct anion exchange reacting with this catechol moiety. And then we compared the NMR spectra, showing that always, no matter which temperature we are working at, the cycloaddition always led to the formation of the chlorination adduct. So in conclusion, we assessed the reactivity of bismuth-1 toward orthoquinone, and the reaction of bismuth-1 species that were generated in situ have proved that we can easily obtain monorganobismuth catecholates in good yield without any purification step, because they easily precipitate from the solution, so they are extremely easy to be obtained. We generate a different array of bismuth species at a low temperature. We didn't need to further, we didn't need to isolate them for reaction, but we are still working on trying to check how we can isolate them. And then we also check that chlorination products are obtained. So in this moment, we are trying to aim to check whether there's a radicalic intermediate forming, showing that the bismuth compound doesn't go a concerted cycloaddition, but probably an addition toward a single electron transfer mechanism. So we are currently doing some APR studies in order to check if we can catch a semi-Quinone radicalic intermediate. And I would like to thank my research group, especially the crystallographer, helping me, and all of you for your attention, and especially the committee to allow me to head this talk.
Thank you, Raffaele, for the nice talk. Are there any questions?
Thank you. A very interesting fundamental study. I'm just wondering in which direction is your group targeted to address all these findings?
Well,
synthesis, catalysis, or?
Yeah, the idea was to mostly try to check how the oxidative addition of bismuth undergoes, because generally bismuth, being a main group metal, as other main group metal is not that well known for having a transition metal-like behavior. But when they're in low oxidation state, mostly in the recent 3-4 years, many different possibilities were unlocked by having the possibility of having, for example, CC coupling or different type of coupling. But for that is, let's say, need to start to understand whether the addition is concerted, whether it undergoes a set mechanism. So we are trying to do mostly in this moment studies to check how it behaves. Because, for example, this reactivity with bismuth is totally different from what with orthoquinones, totally different from what was recently published with arsenic 1 and antimony 1, because the cycloadats are more strongly made. Instead, when there's antimony or arsenic, there's more lability on the obtained complex, and the reaction might also work differently.
Okay, thank you so much, Raffaele, once again. And now we have the last speaker of this section. It is Maria Defensa, from design to catalysis, exploring the versatility of miniaturized enzymes. Please.
Okay. Good morning, everybody, and thanks to my chair, Prof. Pappalardo, and the scientific committee to give me the opportunity to be here today and share with you the last results that our group obtained about the versatility of a class of miniaturized heme enzyme that are mimochrons. So first of all, who are mimochrons? Mimochrons, sometimes we define this class of enzyme as a Swift knife miniaturized heme enzyme. Why are they versatile? Because of their broad catalytic activity, especially in this slide, I showed you the last analog that is also the most efficient from a catalytic point of view, having peroxidase activity, that is iron mimochrom 6-A. From a structural point of view, we can identify the deuteroporphyrin ring here that is covalently linked to two short peptides, one made of 10 residues, that is the distal side, and one made of 14 residues, that is the proximal site, in which in position 6 we inserted the histidine residue in order to coordinate the metal ion inserted in the porphyrin. When we have iron 3, we have a peroxidase activity, and this analog is able to oxidize a BTS better than the natural counterpart, that is the HRP. However, when this iron ion is replaced by a cobalt ion, we reach hydrogenase activity, or when we have a manganese ion, we have a peroxygenase activity. However, really soon this afternoon, my prof, Angela Lombardi, will be awarded of a malatistamide and will show you how in our research group we shaped the catalyst over the years and also mimochrons. So let's go to the focus of this, to the core of this presentation about the results we obtained on two main classes of mimochrons. The first, imidazole bearing, and the first, a new challenging project about the development of a new thiolate bearing mimochrons. And about the first part of this presentation, I will talk you about one of the applications of iron mimochrom 6-A into catalyze the conversion of halophenols. And a few years ago, we published the paper in which demonstrated that iron mimochrom 6-A is able to catalyze the oxidation of halophenols with different halogenation degree, so from mono to penta-halophenols. And about the mono-halophenols, we obtained a really interesting result in terms of selectivity, because the reaction, was chemodivergent. So changing the nature of the substrate, so changing, for example, from 4-fluorophenol to 4-chlorophenol. In the first case, in this condition, we obtain just benzoquinone as a reaction product. But on the other hand, when we have 4-chlorophenol or also bromophenol or iodophenols, the reaction gives just the 5% of benzoquinone and then oligomeric products with the CO unprecedented radioselectivity. So we were really interested in to understand the reason why of this chemodivergent outcome, and so we started to study the catalytic mechanism of this reaction. And this is a common catalytic cycle for a natural peroxidase that we also hypothesized for our catalyst. So this is the resting state in presence of hydrogen peroxide, that is the clean oxidant used as co-substrate. We obtain compound 1, that is the active species, able to catalyze the first single electron oxidation, giving this phenoxy radical 1 and the compound 2, and then the second single electron oxidation, giving once again the resting state to close the cycle, and the diene 2. So what we hypothesized to explain these results is that when we have a chlorine atom in paraposition, or also bromine or iodine, what we have is accumulation of the reaction media of this phenoxy radical. So from self-coupling reaction, we obtain then oligomeric species. On the other hand, when we have a fluorine atom, probably the reaction quickly proceeds to the diene 2, giving then just benzoquinone. However, our aim was to demonstrate, first of all, the different accumulation of this phenoxy radical 1 in the 2 different conditions. So what we did, firstly, was to trap this radical and demonstrate its existence. And we used this molecule, this spin trap agent, to obtain these 2 covalent adducts monitored, first of all, by UV-Vis spectroscopy. So these are the 2 different reactions, and the spectra over time indicated in both cases the presence, the formation of a new band at 340 nanometers, suggesting the formation of these 2 adducts. And however, we were not able to quantify by UV-Vis or by NMR the 2 different adducts, so we decided to observe the 2 reactions in real time by EPR. And so in both cases, we performed the reaction in the same condition and analyzed the EPR spectra at the same reaction time. And in this case, when we started from 4-chlorophenol, we observed a really nice organic radical signal, totally absent when the reaction was performed starting from 4-chlorophenol, meaning that in this case there is accumulation of this phenoxy radical and no accumulation of this when the reaction was performed from 4-chlorophenol. So we were able by EPR to demonstrate that the chemodivergent outcome of this reaction. And now let's move to another aspect concerning the versatility of iron mimochrome 6 array to catalyze the oxidation of halophenols, and especially its ability to retain its activity even in presence of multiple substrates. And this is one of the reactions that iron mimochrome is able to catalyze, so the oxidation of 3-chlorophenols to dichlorobenzoquinone. In this table, the catalytic parameters for this reaction, and especially the very high catalytic efficiency that is higher than other natural and artificial system doing the same reaction. This reaction is also catalyzed by the haloperoxidase B, that is a natural peroxidase. However, when in presence of 4 halophenols, the activity of the haloperoxidase is totally repeated. And so we were wondering if our catalytic system was able to discriminate between 3-chlorophenol and monohalophenols. So we performed the reaction of, the oxidation of TCP in presence of the different halophenols, and we analyzed the reaction by gas chromatography, revealing that the turnover number concerning the substrate consumption was really lowered by the presence of 4 halophenols, meaning that also in this case we have inhibition of its activity, but there is still retained activity, even in presence of multiple substrates, different from the haloperoxidases. And then we were curious about how the 4 halophenols were influencing the kinetic parameters, and so we studied, here on the left, we studied the the reaction, the TCP oxidation, in absence or in presence of increasing concentration of one of the 4 allophenols chosen as a model inhibitor. And we demonstrated that the maximum rate of the reaction was unchanged after the addition of inhibitor, while the Michaelis and constant increased with the increase of the concentration of inhibitor, meaning a lowering of the affinity toward the substrate. And also analyzing this data by Lineweaver-Burk plot, we demonstrated that 4-fluorophenol is a competitive inhibitor for this reaction, for our catalyst. And now let's move really quickly to the last part of this presentation, in which I will show you, I will give you just a taste of this new project in which we are trying, we are replacing the histidine in position 6 of the proximal site with the thiolate-bearing amino acid that is homocysteine. Why? The aim was to obtain a mimic of unspecific peroxygenases. Unspecific peroxygenases are fungal enzymes able to perform many oxidation reactions, 1 electron and 2 electron oxidation reaction on a plethora of organic substrate, aliphatic and aromatic, always using hydrogen peroxide as oxygen donor and reductant. This project is part of the doctoral project of Adalberto Oscar Niola, which has this poster, number 76, and please go to visit his poster if you have other questions. And so this is the new model, new analog, in which we replaced the histidine with the homocysteine, coordinating the iron ion. Just this slide to say you that we characterize this new analog. These are the UV-Vis spectra at pH 7.8, in which we have the Sore band at 391 nanometers and shifted to 415 nanometers after the reduction to iron 2, and then the binding, the classical binding with the carbon monoxide. We firstly tried this substrate to prove the activity, the catalytic activity of this new analog, and this is typically used to detect the presence of unspecific peroxygenases because it's a spectrophotometric assay because of the formation of this orange-colored cerulinium dimer absorbing at 469 nanometers. And these are the results, the preliminary results we obtained, in which you can see the initial rate and the conversion in percentage at different pH value for this reaction, from which we demonstrated that the best condition seems to be the basic condition. And just to conclude, I hope I convinced you about the versatility of this artificial metalloenzyme with a very simple structure, but really effective. And about the story of allophenols, for sure, computational studies are still needed to better understand the chemodivergent outcome of our reaction, of the conversion of allophenols. And about the new project, we prepare this new analog, and Raman studies are ongoing to further confirm the iron-sulfur coordination, and the further aliphatic and aromatic substrate will be tested. Finally, I would like to thank you for your kind attention, and my research group and Prof. Angela Lombardi and Prof. Flavia Nastri, which coordinated our work in lab every day. Thank you.
Thank you, Maria. Very nice presentation. And now we have time for a question.
Congratulations, very nice talk. Just a curiosity about the chemostability of your catalyst. How much they are stable at temperature over the time?
Are you talking about the first analog I just showed you? Yes, I mean, the typical reaction are performed at room temperature. We didn't perform studies over temperature from a catalytic point of view, but over pH, yes. And the best condition we found for example, peroxidase activity is 6.5.
No, it was just because many other catalytic reactions require higher temperatures, and so to understand the versatilities of your catalyst. That was my question.
Yes, but I mean, this reaction does not mean need a higher temperature in this case. We reached all result at room temperature, also concerning the peroxidase activities and so on. We tested this catalyst on a big plethora of substrate. In all cases, the reaction proceeds at room temperature. In aqueous condition also.
Thank you.
Are there other questions? There is time for another quick question. No? Okay. If not, we thanks again Maria. We thanks. And we thanks, please join me in thanks again all the speakers of this session. There is a short break and then again at in 50 minutes in this room for the prize. Okay? Okay. Thank you so much.
partire lei le presentazioni, come sempre. È già acceso.
So, good morning, everyone. It's a great pleasure for me to chair this session dedicated to the PhD Thesis Awards. So this year, the board of the division has received 13 PhD theses to be evaluated, and the selection was not easy at all. And all the theses that we received demonstrated the high quality of the research that the young members of our division are performing. And we, as the board, we wish to congratulate with all the PhD students and now doctors who submitted their thesis. Anyhow, a selection has to be made, and so we are very pleased to announce the awardee of this 2025 edition of the PhD Awards. And these doctors now are, for the bioinorganic chemistry, Dr. Lucrezia Cosottini from the University of Florence, and her thesis is entitled Linking Cytotoxic Gold-1 Compounds to Human Ferritin. For the materials chemistry, the winner is Arianna Actis from the University of Torino and Nice Center, and the thesis is entitled Electron Paramagnetic Resonance Studies on Native and Photoinduced Species on Carbon Nitride. And for the organometallic chemistry, the winner is Massimo Melchiorre from the University of Naples, Federico II. And the thesis is entitled Sustainable Solvents and Chemicals, Synthesis and Applications in Catalysis, Storage Energy Devices, and Cultural Heritage. So first of all, our compliments to the three awardees. And we start with the presentation of Dr. Lucrezia Cosottini.
Okay, so good morning, everyone. First of all, I would like to thank the Division of Inorganic Chemistry for this award. It's a real honor. So today I'm going to talk to you about the link of cytotoxic Gold-1 compounds to human ferritin, which is an extract of my PhD thesis. So first of all, human ferritin is an high-rich storage protein. Today I'm going to talk about a recombinant version of this protein for biomedical application. Ferritin is a protein that it is composed, in this case, of 24 identical heavy chain subunits that are able to self-assemble in this hologlobular structure. This protein is really well known as an nanocarrier for biomedical application due to its characteristics, in particular for its biocompatibility, the fact that it is not immunogenic because it is of human source, the fact that it is highly resistant to harsh conditions, so it is really endable in the lab, And moreover, it has this internal cavity that can host different kind of molecules, but also has an extensive external surface that can be suitable for bioconjugation. Moreover, the heavy subunits of the ferritin are physiologically recognized by a receptor, which is the transferrin receptor 1, which is known to be overexpressed on different kind of cancer cells with respect to healthy ones. And over the year, I indeed confirmed the overexpression of the receptor on a series of cancer cell lines, comparing it with healthy ones. And I also correlated the internalization of this protein with the expression levels of the receptor. So with this basis, the idea of my PhD project was actually divided in 2 sub-projects, but today I will focus on the first part. So on one hand, we have the targeted delivery of methyl compounds towards cancer cells to enhance the selectivity of these compounds to avoid the side effects of the heating and killing healthy cells. While the other part of the project was to exploit therapeutic anti-cancer ferritin-based vaccines that I hope one day I will talk to you about. So let's start. Here I reported the 3 gold 1 compounds that I've worked with, which are auranofin, aurathiomylate, and the gold 1 monocarbene. Auranofin and aurathiomylate are actually FDA-approved drugs that are now repurposed for cancer treatments, while the gold monocarbene is a molecule of new synthesis. I also reported the IC50 values against A2780 ovarian cancer cells, which are the primary cell lines that I have studied. So the idea here is to conjugate these 3 gold compounds on the surface of the ferritin. And to do that, of course, I had to produce the system in Escherichia coli. I purified the protein, and then I developed a bioconjugation protocol, which is the incubation of the protein with an excess of the gold compounds in a reaction that lasts 3 hours, 37 degrees in PBS. And then I removed the excess of the gold, the unbound part of the compounds via dialysis. Then we started our characterization exploiting electrosparing mass spectrometry. And here I reported the 3 mass spec of each bioconjugate. As you can see, we have a different kind of profile here, but in each case, of course, the peaks are referred to the ferritin subunits and not to the entire cage due to the experimental conditions. So in the case of auranofin, for example, we have the presence also of the apoform and 3 different peaks that are referring to the ferritin subunits plus different moieties of auranofin. In the case of aurathiomylate, instead, we do not have the presence of the apoform, and we have a single peak, meaning that all the subunits are actually bound to the same species. For the carbene, we have another different situation. We still do not have the apoform, but we have a distribution of different amount of carbene molecules bound to the ferritin subunits. So then we went over and we thought, since gold is actually a soft metal that has high affinity for cysteine and selenocysteine, and since each ferritin subunits present 3 different cysteine, one which is a little bit more hidden in a channel of the protein and 2 solvent exposed one, the idea was to design and express 3 different kind of mutants. So I replaced 1 or more cysteine with alanine, and I performed the same reaction with the gold compounds. And what we observed was that when, in the case of the mutant at the level of this cysteine here, which again is the more hidden, actually the binding ability of the protein seems to remain the same as for the wild type. While in the case of the double mutants, so both the 2 solvent exposed cysteine were actually removed, we lost the binding ability to the drugs. And in the last case, instead, I removed just 1 of the 2 solvent exposed cysteine, and we were able to decrease the binding ability. So this is actually telling us that these two solvent-exposed cysteines seems to be the binding sites for these gold compounds, and that the binding seems also to be cooperative between the two. So then we started characterizing each bioconjugate by itself. And regarding aranofin, we try to simulate some biological context, starting from competition binding assay with serum albumin. Serum albumin is a circulating protein that presents a free cysteine. And so we incubate the two proteins together. And what we observe is that there is no transfer of the gold from the ferritin to the albumin. And that is a good thing, because serum albumin is known to bind free aranofin and to alter its pharmacokinetic properties in vivo. Then we lower the pH of our bioconjugate solution to mimic the end-lysosomal pathway, which is a pathway that ferritin goes through after the recognition with the transferrin receptor. And what we observed was that we had a release of the drug, a slow release, not complete, but we have a release of the drugs. And finally, we incubate, again, the ferritin aranofin bioconjugate with the primary biological target of aranofin, which is thioredoxin reductase, which is a protein that has a selenocysteine. So we use a dodecapeptide of this enzyme, exposing the selenocysteine, and what we observed was that after a few hours, we observed the transfer from the ferritin to the thioredoxin. So this is actually meaning that aranofin has different affinities through different proteins, and that even though the release of the drug is not complete due to the pH, if the bioconjugate encounters its biological target, we can still have an effect. And here I also report a molecular simulation that propose this kind of structure for the mainly moiety of aranofin bound to the ferritin with this gold bound to the two solvent-exposed cysteine. Then moving on to our thiomalate, we started from the electrospray spectrometry data, and then we perform molecular dynamics. And as you can see here, the reaction with the wild type and with the single mutant gave us a different mass increase. And what we observed was that in the case of the wild type, we have the presence of a species with a molecular mass of 3 gold atoms and 2 thiomalates. That here is proposed by molecular dynamics with this structure here. So you see that the golds are base coordinated by a cysteine and a thiomalate or 2 thiomalate. In the case instead of the single mutant, where the cysteine 19 is absent here, you see that to complete the binding of the coordination of this gold, a thiomalate more is needed. Therefore, we have the increase in the mass. And finally, for the last bioconjugate, we were able to solve a high-resolution structure exploiting cryo-electron microscopy that shows us the presence of a tetranuclear gold cluster that you can see here, where again we have 2 gold atoms bound to the 2 solvent-exposed cysteine. And here is reported just a single carbene, which was the only one that we were able to solve because it was the only one well-ordered, but of course there are the other 3 carbenes here too. And we also observed that the interaction between these gold ions are actually aerophilic interaction, because the distances that we observed were in the range of 3.2 angstrom that are in line with the theoretical ones. So of course I showed you the binding mode and the binding ability of the protein to link these gold compounds, but my goal is also the one to exploit this protein as a nanocarrier. So we moved to the cytotoxicity studies, and we started with the MTT assay to determine the IC50 values of the bioconjugate, comparing them with the one of the free drugs. and they were all active. And in particular for RS malate that you see is the one with the highest IC50 against A2780 ovarian cancer cells. We also perform ICP on cell lysates to see the internalization of these drugs, of this drug. And as you can see, comparing the bioconjugate with the free administration of the gold, we have an increase in the amount of gold present in the cell lysates after the delivery by ferritin. Moreover, we also exploit 1H and MR metabolomics on A2780 ovarian cancer cells that were treated in equal toxicity condition to observe the metabolic changes induced by the treatment of the free drugs compared to the one with the bioconjugates, of course. And looking at the trend of these bar plots, you see that it is always the same. That means that the presence of the protein actually does not change the metabolic changes induced by the gold drugs after the treatments of the cells. And we also observed that the ferritin, the apoprotein alone was completely inert against these cells. So to conclude, I was able to develop a reproducible protocol for GOL1 compounds bioconjugation to human ferritin. We determined the two solvent-exposed cysteine as the binding sites for these GOL compounds, and we were able to solve a high-resolution structure via cryo-electron microscopy of one of these. We demonstrate that the transferrin receptor 1 expression level are correlated with the gold uptake in cells, and that the protein as an nanocarrier does not alter the metabolic effects of the gold compounds. So after 3 years of PhD, I'm here to say to you that ferritin, human ferritin, is a suitable system for biomedical application and for the targeted delivery of GOL1 compounds towards cancer cells. Here, of course, I would like to thank and acknowledge my supervisor, Professor Turano, and all the people that helped me and worked with me during this project, and of course, all of you for your kind attention. Thank you.
Thank you, Lucrezia, for this very interesting presentation, and we have now time for one question. So if not, everything was clear, and now we leave for the thank you.
Thank you.
Congratulations.
So now we move to the next talk by Arianna Actis, please.
Thank you for the introduction and good morning, everyone. I'm very humbled to be here today and grateful to the Divisione Inorganica della Società Chimica Italiana for this award. And I'm really glad to have the opportunity to share with you the content of my PhD thesis that was focused on the investigation of carbon nitride by means of electron paramagnetic resonance spectroscopy, or EPR in brief. So carbon nitride is a semiconductor that has raised much interest in these last years in several contexts of catalysis. It is used both as a photocatalyst in heterogeneous catalysis and as a support for single atom catalyst. So it is a very versatile material, but there are still several aspects of its reactivity that still need to be investigated. And how can, in this context, EPR be useful? So as far as photocatalysis is concerned, the major obstacle that carbon nitride is still facing is the fast charge carrier recombination that basically makes most of the photoexcitation being extinguished before it can be effectively exploited to drive a chemical reaction. And therefore, there is a genuine interest in understanding what are the mechanisms underlying light harvesting and how these then translate into species that can be effectively used to drive a chemical reaction. So EPR spectroscopy is of course sensitive only to photogenerated species with a paramagnetic character, but for this reason is able to provide some pieces of information that are simply inaccessible to other characterization methods. At the same time, as far as single atom catalysis is concerned, one of the major questions that one usually tries to address is the nature of the chemically active metal species. And in this context, this usually is specifically determined by the nature of the bonding interaction between the metal species and the support. And in this sense, EPR spectroscopy is really able to selectively pinpoint the species with a paramagnetic character and provide a very detailed description of this bonding interaction. So my thesis basically dealt with these two contexts. And as a brief introduction to this material, carbon nitride is a semiconductor that is obtained through a thermal condensation process that leads to this polymeric structure that is somehow reminiscent of graphene structures. But as you can imagine, this thermal condensation is leading to a high level of structural disorder and poor crystallinity, which are factors that usually make the characterization quite challenging. And I would like to stress that throughout my PhD project, I studied specifically carbon nitride materials that are not model system or simplified anyhow, but are actually working catalysts. So to start with the first section of my thesis, this was focused on studying intrinsic photogenerated species in this material. So here I reported a very simplified scheme to represent the major processes that occur after light excitation of a solid-state semiconductor. So light excitation can be schematized as the generation of an electron-hole couple, which is a bound state, so an exciton, initially in a singlet spin state, which can then undergo conversion into a triplet, or can split, the exciton can split into free charge carriers, which on longer time scale can get stabilized at lattice position and singularly are doublets. So clearly, only these two latter species have a paramagnetic character, but it's also important to remember that these are characterized by, most of the time, by a lifetime that is compatible with the same time scale where the surface reactivity at the surface of a heterogeneous semiconductor can take place. And so EPR is really able to give us a direct insight into those species that are more likely to be involved in a catalytic processes. So the first one that I characterized are triplet excitons, which are, of course, transient species. So I applied a time-resolved version of EPR spectroscopy. First of all, to probe that triplet excitons actually exist in this system, because with this method, we can directly observe them. And in second instance, we try to define an energy for triplet excitons. By repeating this EPR experiment at different excitation wavelengths, we could notice that the EPR signal changes intensity, and we collected this intensity in a sort of, cannot really use this, in a sort of triplet absorption band, which allowed us to extract the optical behavior of the triplet exciton from the general optical behavior of this semiconductor, which here is represented by the diffuse reflectance spectrum in black. And then by comparing this with the fluorescence excitation spectrum in purple here, we were able to to distinguish the behavior of triplet excitons from singlet. And by defining the energy of these two species, we were able to compile an energy level diagram that I'm showing here, where we were able to outline the fact that in this system, triplet excitons lies at a slightly higher energy with respect to the singlet. This is also known as inversion of the Hans rule, and it's a peculiar property occurring in some aromatic systems, which was previously investigated theoretically for the carbon nitride monomer derivatives, so these eptazine derivatives, but never directly experimentally observed on polymeric carbon nitride. And we can expect that this property might also have important implications in photocatalysis, because it means that in this system, generation of a triplet exciton is no longer a downhill process. So we might expect that part of the electrochemical potential of the original photoexcitation event is somehow retained also on longer time scales. Then if we go back to this timeline, we can imagine to follow the evolution of the photoexcitation up to the point where charge carriers get stabilized at lattice positions as radicals, so doublet species. So carbon nitride is known to host intrinsic radical species arising from structure defects, but it's also well known that these species can be photoexcited and photoaccumulated. And their presence has been correlated to an augmented photocatalytic activity of this system. So there is a genuine interest in understanding how these species, what are, first of all, these species, and then how they are distributed within the material. So to investigate this aspect, I applied, first of all, hyperfine spectroscopy, which in a first instance, at least, exploits the magnetic dipole interaction established between the electron spin and the magnetically active nuclei in the surrounding of the radical defect, and therefore allows to map how the electron wave function associated to this radical species is delocalized over the structure, and so its location, basically, on the structure. So for this, we derived that these radicals that are already known to be carbon-based are actually quite delocalized over the structure, but still confined within one monomer unit. And then by exploiting the same dipolar interaction, but this time between electron spins, we are exploited by this so-called dipolar spectroscopy. We are able instead to map how these radicals are distributed within the material. And as you expect, of course, this interaction can span much longer distances on the nanometer range. And this informed us that these species in this material appear in couples and at definite distances. So with this, we were able to map both the local and the long-range distribution of these species that have been somehow correlated to catalytic activity in this material. As I anticipated at the beginning, the second major topic that my thesis tackled was exploring instead the role that carbon nitride plays as a support for single atom catalysts, so single metal species. And in this instance, so the system that I studied was constituted by nickel-2 ions deposited on carbon nitride. And the major questions that we tried to answer were, first of all, if these metal species are effectively isolated, and if they display some sort of chemical reactivity. And then what is the nature of the bonding interaction that they establish with the support. So nickel-2, when it is present in a tetrahedral coordination, is a singlet. Oh, sorry, is a singlet spin state. So it's EPR signed, but it can form another paramagnetic adduct by interaction with nitrogen monoxide, and this can occur only if the species is effectively isolated. So this is a simple experiment that already tells us that at least a fraction of nickel species exist as effectively isolated metals. Then upon reduction of nickel-2 to nickel-1, we can obtain a doublet species, which is instead EPR active, and informs us that there exists a fraction of nickel species that are that display a chemical reducibility. And by repeatedly reduce and oxidize them, we were also able to prove that these species can undergo a reversible redox activity. And then we decided to focus on Nico-1 because this oxidation state has been appointed as a key intermediate in the catalytic reactions this material is involved in. So again, we turn to apply hyperfine spectroscopy to investigate the bonding interaction and the nature of the bonding interaction that this metal has with carbon nitride, especially exploiting several different methodologies that can inform us either on strongly coupled nitrogen nuclei, so directly coordinating, or more weakly coupled nuclei that belong to second, further on coordination spheres. And collecting all these pieces of information, we were able to draw a structural model that I tried to represent here, showing the metal Nico-1 coordinated by 4 nitrogen atoms. And by analysis of the hyperfine couplings, we were able to find a distinctive reminiscent of this structure with Nico-1 tetrapyrrole complexes, but more importantly, also a close agreement with Nico-2 carbon nitride, so that the model that has been defined for this system in a very recent work. So this once again proves how EPR spectroscopy is able to integrate structural information that can derive from other characterization techniques. So in conclusion, I tried to apply a broad variety of EPR-related methodologies to investigate, on one hand, photogenerated species that to different extent have been correlated to the catalytic activity of this material, and at the same time applying different methods to investigate the role of this same material as a support for single atom catalysts. Once again, using real working catalysts. So I really hope that the observation that we provided might be somehow useful to advancing also the understanding of these systems. But I have to say that very little of what I've shown here would have been possible without the guidance and the support of my supervisor, Professor Enrico Salvadori, and all the group at the University of Torino, and our collaborators at the University of Trieste, Professor Michele Melchionna and Paolo Fornasiero. So let me thank once again the Divisione Inorganica della Società Chimica Italiana for this award, and thank you all for your attention.
Thank you so much, Arianna, for your very interesting presentation. And we have now time for one question. Please.
Very nice work. Which are the typical light power that you use for these experiments? And have you ever investigated the effect of the light power on the distance, for example, of the species that are obtained, or this is not relevant at all? I'm just curious about that. Thank you.
So thank you for the question. Yes, we didn't investigate specifically the effect at different powers, in fact. So unfortunately, I don't know this. Yeah.
So we thank Arianna again. And now we move to the last presentation of this PhD thesis award session, and is delivered by Massimo Melchiorre.
Thank you, Professor Milani, for your very kind introduction, and I would like to start by thanking also the Inorganic Chemistry Division of Società Chimica Italiana for recognizing this award for selecting this PhD work for this prize. Sorry. My PhD work basically focused on the development of alternative bio-based solvents. And we proposed a new class of dioxolane organic molecule, and we tried to find application in catalysis, energy storage devices, and cultural heritage application. So the story of solvents development and green chemistry is very tight connected. And the first idea about solvent replacement started to arise during the 90s after the first national and international action to prevent pollution. And in that period, that was the time of the rising new solvents, neothetic solvents like room temperature ionic liquid, supercritical CO2, or gas expanded liquids. In 1998, Paul Anastas was publishing the 12th principle of green chemistry, and on the 5th principle, he was highlighting the necessity to use Benning solvent and auxiliaries. Few years later, Abbott was publishing the first hypothetic solvent, and 2 years later, Jessop was publishing the first switchable polarity solvent. And the same author in 2011 was publishing a paper with the title Searching for Green Solvents. And in this work, he was basically challenging the chemistry community to different topics. The first one was to populate the diagram. The diagram that he meant was the Kamlet-Taft diagram. And in this plot, each solvent is rationalized according to three main parameters, which are P star, which represent the measure of polarity and polarizability of the molecule, and then alpha and beta parameters, which are respectively the measure of hydrogen bond donor and accepting ability. And here are reported the Kamlet-Taft plot for the polar aprotic solvent in red and in blue for protic solvents. And if we look at the plot, is it clear that common organic solvents have a very great advantage, and it is that we can have an extremely wide choice. But on the other hand, they can have issues like most of them came from fossil-based feedstocks, and they can have some ecotoxicological issues. So in this context of solvent replacement, we can highlight three main approaches for solvent replacement. The first one, of course, is to use solvent-free conditions, like in mechanochemistry, or switching to water-based reaction media, for instance. But then most of the time, these two approaches are not always direct possible to have in some system. And most direct approach is the direct drop-in replacement with a different organic molecule with improved ecotoxicological parameters, for instance. So we decided to focus on a chemical scaffold that could provide a dipolar aprotic solvent. And we decided to focus on alpha-hydroxyacids because this molecular scaffold can be easily achieved by fermentation from carbohydrates, which is one of the most abundant fraction of biomass. But then we also had to think about a chemical strategy to achieve a proper dipolar aprotic moiety. And we decided to perform a catalyzation reaction because in this way we were able to employ at the same time both the protic moieties of this molecule. And dipolar aprotic solvents are among the most difficult of being replaced because most of the time water or aqueous reaction media can't be used. So with this strategy, for sure we have some advantage because we can have a bio-based feedstock reagent with a high tunability. It's possible to control the fine structure of the product and therefore of the properties of the solvent. And we have water as a side product. On the other hand, catalyzation is an equilibrium reaction, and we have oligomerization as a competing reaction promoted in the same reaction parameters. And the state-of-the-art typically is used paratoluene sulfonic acid as a catalyst in very high loading, up to 10% by mole, and some apparatus is needed to remove water from the reaction mixture, like the Dean-Stark apparatus. And within this part of the project, the idea was to define a greener strategies to achieve the desired product, exploiting Lewis acid catalysis. And we decided to focus on iron-3 catalysts. And actually, we have also a pending patent in collaboration with the ISOSCAN, which is a university spin-off from the University of Naples. So we selected the lactic acid and acetone as a benchmark reagent, and we started to performing a screening of different iron 2 and iron 3 catalyst precursors. Then we moved on the screening of the co-solvent necessary to properly remove the water from the reaction environment. In the best of condition, using iron perchlorate, iron 3 perchlorate in very low yield and low loading at 0.05% by mole and in stoichiometric ratio, within 4 hours we were able to achieve a mild yield of 60-65%. But the most interesting, we were also able to collect a solid from the reaction mixture, and the residual iron 3 content in the mixture was roughly 5 ppm. So the iron 3 had to be contained in the solid, and then we tried to recycle this solid at the end of the reaction, and it resulted to be still active even after 2 runs. So to take a long story short, we tried to make different characterization of this solid, but in the end we ended up with a single crystal analysis that showed to be iron 3 perchlorate. Iron 3 lactate still not reported in literature. Most of these results have been collected in a very recent publication in HES Sustainable Chemistry and Engineering. So if you have any other curiosity, you can check it out there. Then we moved also to prepare a panel of 6 solvents with this approach using different alpha-hydroxy acid, lactic, mandelic, and alpha-hydroxysobutyric, and changing the carbonylic compound to have a possibility to explore the different effect of substituents in position 5 and position number 2. And then we try to answer back to the challenge from GESSOP, and we analyzed the Kamler-Taft parameter for each solvent, and all of them resulted to be a polar aprotic solvent with a P star parameter higher than 0.5. We also evaluated the Hansen parameter, which will be used later on in the cultural heritage restoration. So we selected also benchmark cross-coupling reaction to evaluate their performance as a reaction media, and we chose the iodobenzene and methyl acrylate as a benchmark reagent. And in very standard condition, solvent number 1, LHH, proved to be the most performing and stable. So we decided to focus on this solvent. We performed an optimization on different reaction conditions like temperature and the molar ratio with between olefin and amine with the iodobenzene. And in the end, in optimized condition, we were able to achieve almost a complete yield within 24 hours. And here I'm reporting just the proton NMR spectra for the crude reaction mixture. Most of these results have been collected in green chemistry, and here I want to highlight also that developing a new solvent is not very always easy, and there are going to be very often some limitation. For instance, this was what we figured out with the fluorination reaction, that the polarity of the media was not enough to promote this reaction. But still there is room for improving, and we are now exploring different cross-coupling like Suzuki and Sonogashira, and here I'm reporting basically non-optimized results. So we hope to achieve better in the next future. Second part of my project was focusing on energy storage device at the Friedrich Schiller University in Jena in Germany in collaboration with Professor Andrea Balducci. And here the state of the art is represented by organic, carbonate, and nitriles basically. And they also have some issue, especially regarding the high flammability and some toxicity. So here in this field also there is the topic about their replacement. And we try to introduce LHH and gamma-valeriolactone as a main solvent for electrolyte in the lithium-ion batteries. We explored several properties, and then we moved on benchmark materials like graphite and cathode in half cell configuration, and then we moved on full cell as example. Here I'm reporting the half cell results with the gamma-lactone based electrolyte. We achieved somehow better result thanks to its a bit higher conductivity, and the result to be stable for up to 180 cycle. These are the results for LFP half cell configuration, and also in this case, we were able to achieve a nice result, and the stability was even improved up to 200 cycles. This is the results for the full cell configuration, and it reflects basically the result that we achieved in the half cell. So we were able to transfer probably the capacity that we had with the half cell in the full cell, achieving a capacity retention up to 80% for 180 cycles, more or less. And these results have been collected in another publication in Green Chemistry if you are more interested in the energy storage devices. The last part of my topic is focused on the alternative solvent for cultural heritage. And here the main solvent used are acetone, ethanol, and isooctane for dipolar, protic, and apolar solvents. And in this field, we had a collaboration with Professor Andrea Carpentieri from the University of Naples, and we exploited the TEES plot to rationalize the property of each solvent. In this plot, it's represented all the solubility area of different materials that you can find in cultural heritage, and in this way it's possible to understand if a solvent will be able on theoretical basis to dissolve this material. And even in this case, to make a long story short, we try to have different specimens, even fresh and aged with an accelerated aging process. And the solvent proposed were able to have a solubility proper according to the TEES parameter as expected. Then we moved on real case studies on wooden panel and canvas painting. So here was the main filmogenic material to be removed was Dammar rosin, and we were able to remove it in a combination with the sustainable solvent proposed. Here the results have been collected in a Journal of Cultural Heritage, separated for the two classes of solvents that we have developed. Some final remarks. This is a not commercial solvent. It has a very wide liquid range temperature. It's a biodegradable compound, and it also showed a very peculiar behavior because it was hydrophobic and lipophobic at the same time. And we were able to build up a 4 phases full liquid system using octane, water, and perfluorodecaline. Anyway, it's a non-registered substance, so its acute and chronic toxicity need to be defined. And actually, we are in collaboration with Professor Stefan Stolt and Marta Merkwitz. We are exploring its ecotoxicity. So basically, a new class of dipolar peroxide solvent is available, and they can be prepared in mild condition. They can work as a reaction media, as well as in energy storage devices and for cultural heritage application. I would like to conclude by thanking, of course, my research group Method Plus from the University of Naples, and especially Professor Francesco Ruffo, Professor Maria Elena Cucciolito, and Professor Roberto Esposito for their support during this very long journey. Professor Andrea Carpentieri for its guidance in the cultural heritage field, Professor Balducci and his research group from the University of Vienna for all the experience in energy storage sector. And again, I would like to thank the Inorganic Chemistry Division for this award, and all of you for your attention.
Thank you, Massimo, for this presentation. Very interesting. And it's now open for one question. So if not, we go ahead with thank again all the students, and we go for lunch, and we will be back at 2:30 for the Malatesta medal.
Prende lei? Pronto? Sì.
Scusami, giusto facendo la stessa cosa, sono questo più qua.
Cominciamo. Posso aprire, c'è una presentazione. Magnifico, grazie. Qui c'è. Allora, buongiorno, io credo possiamo cominciare questa sessione che si apre con il premio Malatesta della divisione di chimica inorganica e dirò due parole brevi sulla figura di Malatesta, in particolare per i più giovani e anche per inquadrare un pochino questo premio che è il più giovane tra i premi che la divisione bandisce. La prima edizione è stata nel 2021 ed è un premio che vuole come dire, riconoscere il lavoro attuale di figure importanti della nostra comunità nel pieno, diciamo, della loro carriera e quindi di persone che stanno lasciando delle impronte importanti nel nostro settore. E questo per onorare la figura di Lamberto Malatesta, di cui qua vedete un'immagine durante una lecture. Questa fotografia è presa da questa review dedicata proprio a Malatesta, scritta dal professor Calderazzo insomma nel 2005, quindi lì potete trovare aneddoti e curiosità. Il professor Malatesta nasce nel 1912 nel nord-est dell'Italia e poi si trasferisce a Milano, dove nel 1948 ottiene la cattedra di chimica analitica per poi, diciamo nel 1950, ottenere la cattedra di chimica generale inorganica, che poi terrà fino alla fine della sua carriera a Milano. E Lamberto Malatesta è uno forse dei chimici più influenti della sua epoca, che ha lasciato tracce importanti, in particolare per i suoi lavori sui metalli di coordinazione, sui metalli di transizione in basso stato di ossidazione e è stato il primo a iniziare in fondo alla chimica dei nanocluster di oro, che poi ha dato luogo in qualche modo allo sviluppo nelle nanoscienze, in qualche modo nel termine più ampio. Diciamo, mi piace ricordare anche il suo impegno naturalmente nella società chimica. È stato per 2 volte presidente della Società Chimica Italiana e verso la fine della sua carriera teneva una piccola rubrica sulla chimica e l'industria in cui teneva una sorta di diario, di review diciamo, di lavori di chimica su giornali internazionali che spaziavano in tutti gli ambiti della chimica, dalla chimica bioinorganica fino alla geochimica, e sottolineava sempre l'importanza della chimica come scienza centrale e scienza diciamo ad ampio spettro, per cui ricordandoci non dovremmo mai focalizzarci troppo sulle nostre cose, ma tenere ben presente quanto siamo rilevanti come chimici inorganici e generali in particolare per tutte le scienze. E quindi direi che è un insegnamento attuale. Diciamo, detto questo, il premio, come vi ho detto, è stato la prima edizione è stata bandita nel 2021 ed è stato assegnato a personalità prestigiose, Roberta Sessoli, Paolo Fornasiero, Alberto Credi, Filippo De Angelis, e per questa edizione del 2025 con grande piacere assegnare il premio alla professoressa Angela Lombardi. Quindi vi chiedo un applauso per Quindi Angela Lombardi diciamo, ha svolto tutta la sua carriera qui a Napoli, laureandosi e poi facendo il suo dottorato sotto la guida del professor Pavone, lavorando sostanzialmente sulla chimica dei metalli e il loro ruolo nella sintesi peptidica. Diciamo un tema che poi ha continuato a portare avanti nell'ambito della sua ricerca scientifica, che ha avuto importanti come dire, momenti anche all'estero, in particolare negli Stati Uniti, sia in centri di ricerca prestigiosi di tipo industriale che in università importanti. E quindi tutto il suo lavoro centrato in particolare intorno allo sviluppo di sintesi de novo di metallo enzimi che mimano diciamo sistemi metalloproteine per davvero capire in maniera fine meccanismi di reazione per applicazioni nella catalisi nei sistemi più vari. E quindi questo è in sostanza la motivazione per cui questo premio viene assegnato, lo potete leggere, per l'originale innovativo contributo alla chimica bioinorganica attraverso lo sviluppo di metalloenzimi artificiali. Questo naturalmente è un lavoro importante, è un lavoro che naturalmente Angela ha portato avanti anche grazie al suo gruppo qui a Napoli, e quindi lascio la parola alla professoressa Lombardi per la sua lecture e poi avremo la premiazione. Grazie.
Can you hear? Yes, okay. I would like to say just a few words in Italian, sorry. Grazie chiaramente per questo bellissimo premio, sono felicissima e anche molto emozionata, non so se si apprezza, e vorrei ringraziare innanzitutto le persone, i colleghi, gli amici che mi hanno proposto per questo premio, e vorrei ringraziare il Presidente e il direttivo della divisione di chimica inorganica per avermi assegnato questo premio, e poi, come mostrerò durante la mia presentazione, le persone con cui ho lavorato in tutti questi anni, che mi hanno introdotto alla chimica bioinorganica e alla chimica di coordinazione, e tutte le persone giovani che hanno lavorato durante la mia carriera per ottenere i risultati che oggi vi mostrerò. Come vedete, la mia presentazione, my talk, will be mainly on shaping catalysis, the beauty and power of artificial metal enzymes. So when I was informed of this prize, okay, we already have seen this picture by Professor Mario Chiesa, by Mario, and Professor Malatesta was an eminent member of the Milanese School of Chemistry, and he was really involved in coordination chemistry. So my first thought was, do I deserve this prize? Why? Probably I am quite far from what Professor Malatesta did, but I have already read this review from Professor Professor Fausto Calderazzo, and I found the conclusion of the review very interesting, because at that time Professor Malatesta said, I believe that one should not forget that chemistry is part of the scientific world of great utility in other fields. So I have extended, Professor Malatesta has extended his study to other fields of natural science, biology, physics, and so on. And so I said, yes, probably better, thank you. So I said, oh, that's me, because, okay, this is my career in just a few words. I started my master's degree in industrial chemistry, and I did the thesis with Professor Augusto De Renzi, who was always for me a lighthouse in coordination chemistry until the end of his life. And I worked on regiospecific catalytic alkylation of aromatic substrate with coordinated dienes. So this is coordination chemistry, classic coordination chemistry. But then for my PhD, I moved in the Professor Pavone group, and Professor Pavone at the time was set a standard of excellence in protein structural crystallography of protein and peptides, and he trained me in the development of a molecular tool able to freeze peptides in also disordered peptide in a well-defined three-dimensional structure. And we started the structure-based design of a metalloenzyme. And finally, some years later, I moved to United States in the laboratory of Professor William Degrado, who was a pioneer in de novo protein design. And we developed also some metalloenzymes by protein design. So this is more or less, I did what Malatesta was suggesting at the end of that very nice review, and I suggest to all people, young people, to read, because it's very an impressive review, also to understand the time in which our colleagues were working during the Second War. So I try to join, so my knowledge in organic chemistry, in coordination chemistry, and with peptide chemistry to develop artificial metalloproteins. Also because, what are metalloproteins? I am borrowing a sentence by Ed Solomon. Metalloproteins are simply metal complexes, but with remarkable, intricate, and complex ligands. So, can we try to make this intricate ligand, complex ligand, simpler and simpler, but with the same, retaining the same catalytic structure properties? Let's try. So, if we look at nature, biology provides us with a plethora of metalloproteins. These are some examples of iron-containing metalloproteins, which contains both either an heme, or a dicarboxylate bridged diiron center. As As you can see in this slide, the metalloprotein are able to perform a wide variety of functions using very similar metal cofactor. You know, we have a lot of elements in the periodic table, but nature uses only a few because it is able to modulate the properties of a single metal cofactor. So what's the problem? The problem is that sometimes high production cost and the protein stability issue of a native enzyme hamper the wide use in industrial and biological application because nature use these metalloproteins in very mild conditions, in water solution, at room temperature, and so on. So one of the questions I would like to answer is, can we make these proteins more stable that can we use as catalyst also in rush conditions? And once again, looking at natural metalloproteins, we can see a very nice partnership between the metal cofactor and the protein matrix that is able to generate such functional diversity. But why? Because the protein environment is able to select the first coordination sphere, the ligand that directly coordinate the metal ion, but more important, provide a variety of second shell interactions that tunes the properties of the metal ion. So what we can do as bioinorganic chemists, we want to master simply coordination chemistry and building many different chemistry, modulating promiscuity or selectivity, because also promiscuous catalysis is very important. For example, if you think it environmental application, depending so on the application we want to design. This slide is very cloudy, but this is just to show you how many different methodology are nowadays used for designing repurposed and artificial enzymes. I just would like to mention the de novo design we have listened about by Anna Peacock and Vincent Pecoraro, or the metal insertion in privileged scaffold, mainly done by Tom Ward and Gerard Rolfe, or the metal cofactor replacement by the group of Hayashi and Hartwig. And on the molecules obtained through all this methodology can be subjected to direct evolution to improve the properties, and this was the Nobel Prize in Chemistry by Arnold. So we use peptides, and I said at the beginning of my presentation, and peptide, both structural designed or de novo designed, and we have used the peptide to implant different activity, as you can see in this slide: peroxidase activity, oxidase, electron transfer or oxygen cleavage, using metalloporphyrin, dinuclear site, or mononuclear copper or iron site. Okay, let's go. This is our evolution of the first class of metalloprotein that we designed in the last more or less 30 years. And we started, I will show you the milestone in the development of this class of compound, starting from the first structural compound to the catalytic active compound. And I would like to give you just an overview. If you are interested in more specific things, we can talk when you like to do. Okay, so our thing is less is more. So what we have designed this class of compound, mimochrome. Okay, we first is a structure-based approach. So we started from an analysis of the human hemoglobin, and we saw that the heme here is embedded between the E and F helices, that the F nonapeptide chain of the F helix is sufficient to cover the porphyrin plane. Then we selected an appropriate rotamers, the ideal angle for the side chain of this lysine, which is present in this peptide, and the propionic group of the protoporphyrin to covalently bound the peptide chain to the heme, and then we did some mutation just for synthetic problem. At the end, we applied a C2 symmetry in order to have both side of the heme protected by a peptide chains. So, since we applied a C2 symmetry, these two chains are exactly the same. And this heme, this iron heme, is hexa-coordinate with the two histidine coordinating the iron. Then, through a design and redesign process, we tried to optimize first the structure and then to optimize the function. And so it was necessary to insert some interaction by design. So we inserted, you can see here, a very nice intramolecular intrachain ion pair interaction for stabilizing the sandwich structure. And then to have a catalytically active molecule, we needed to create, we needed to create a cavity, a distal cavity, like in natural protein. And so the first molecule we designed was MC6. So we inserted some asymmetry by designing a tetradecapeptide here in blue and a decapeptide chain in green. As you can see here, the decapeptide that we call the distal peptide chain, like the axial ligand. We can see here a substrate binding pocket, as for example, the distal site of peroxidase, which activate hydrogen peroxide. And then we stabilized also, we try to stabilize and to put other important finding in this model. And the most important was that we did a mutation in the proximal chain in order, in particular, we mutated glutamic acid here with leucine because this arginine now is unpaired, and is very important, we will see, for peroxidase activity. And finally, we tried to construct, to insert, for stabilizing the helical structure, two AIB residues, alpha-aminoisobutyric acid, which is a non-proteogenic amino acids that favor helical structure. And also this substitution improved a lot the catalytic performance. So this is the enzyme that we selected as lead molecules after some cycle of redesign, and this is the main feature that I have already shown you in the previous slide. And you can see here this arginine residues is very important because it played the same role of arginine 38 in natural peroxidase. It is important for stabilizing the high valent oxoferryl species compound 1 during catalysis. So you can see here just that the peptide is helical from CD as expected. And now we did some catalysis at the beginning with the chromogenic substrate, and we actually saw that what we selected as lead, of course, as the best catalytic performance with a catalytic efficiency that outperform, you can see here, the natural HRP, and with the ton number of 14,000, which is quite close, I would say, to the natural HRP, considering that our molecule has a molecular weight which is 10 times lower respect to HRP. So, having established that this compound is really a lead compound, is active in peroxidase activity, just an overview, we tried to do really chemistry with some utilities, and we did some, we tested the peroxidase activity with other substrate. We have here from Maria this morning the activity of the iron derivatives in halophenol oxidation, but it is active also in luminol oxidation and in the degradation of organic dyes. But the thing, another important thing, in my opinion, is that this compound is able to host different metal ions, and so because it is synthetically made, so it's very easy to insert into the porphyrin ring different metal ions, and we can modulate the reactivity also in this way. And so we inserted, first of all, manganese to test the peroxygenase activity, and indeed it was active mainly in a very selective indole oxidation. And we also tested the cobalt derivatives that is active in hydrogen evolution and CO2 reduction. Okay, I don't want to go into the detail of this reaction with manganese, but just I suggest you to look at these two numbers, that the selectivity toward the oxidation in position 3 of the indole ring is really very high, approaching 90%. And you have considered that before, even natural proteins or the small molecule complex give a plethora of different compounds, and also the conversion was quite high. And to show you the role of the, once again, the role of the distal site, the importance of the distal site in this mimochrome, just have two numbers in hydrogen evolution reaction. It is active in both electrocatalytic hydrogen evolution or in photocatalytic hydrogen evolution, if you compare the results that we obtained with our mimochrome respect to cobalt MP11, which is a small compound obtained from the proteolytic degradation cytochrome C, so it is a structural chain which just bring the histidine here coordinating the imiron. You can see that the turnover number is 10 times higher from here to here, and also we observed a lower over potential, and so we can say that really the distal chain is important for protecting the porphyrin from degradation, and the same in the photocatalytic hydrogen evolution. And we did all this work in collaboration with Cara Bennett, University of Rochester. Okay, we have also linked on the mimochrome on different nanomaterials to obtain functional nanomaterials, and we have used the different supports going from gold-based nanomaterials of different shape, and also catalytic. We have constructed, probably you have seen the poster by Alessandra Esposito in this meeting. So we have construct some catalytic amyloid by forming amyloid peptide with our molecule. And the important thing is that the catalyst retains activity when is conjugated to gold nanomaterial, or both gold nanoparticle, nanotriangle, or nanorod, and the same is from the other nanomaterial we used. I have just few minutes to show you this other project, which is based on the novel design of 4-helix bundle peptide that I started when I was visiting at DuPont with Bill DeGrado. And we also in this field obtained some very important milestone. And I will, for matter of time, I will skip all the design process that we did from the first to the last molecule, but important milestone that we obtained are okay, this is the design. Okay, we did the first molecule that we called DF1. You can see here the superposition of the crystal structure in green and the design molecule in gray. This is a very good superposition, and you should consider that this is the first crystal structure of an artificial de novo designed metalloprotein. So we was very happy to obtain this molecule. But even though the structure was correct, it was not a good catalyst because it was too well structured, and so it was not able to support any kind of chemistry. And so we learned that we have to face a very important the trade-off between protein stability and protein function, because protein stability and protein function required very different, very different and opposite properties. And so we had to play a little bit with the structure of this model to open the cavity, and we did this. You can see here, because we replaced the two leucine residues here, leucine 13, we blocked the cavity here, and with alanine, and then with glycine, and you can easily see the difference between the two structures. Here the cavity is completely closed, no water molecule, structure water molecule in the cavity. Here it is open, you have a number of water molecules, here red, and with the gly, of course, the cavity is larger and you have a larger number of water molecules. So, this was the first designed phenol oxidase, which is a model of alternative oxidase. But in nature, as a phenol oxidase is able to catalyze the oxidation of catechol to quinone. But in nature, this kind of reaction is usually not catalyzed by the iron protein, but by the couple proteins, type 3 couple proteins. And so we asked ourselves, can we use this model to insert the couple proteins? The answer was yes. Probably I don't have time to show you also this structure, but we did some redesign. We shaped the cavity in this new molecule. At the end, we obtained this molecule that we have fully characterized from a spectroscopic and structural point of view, and also from a functional point of view. Just two results is that the protein, of course, is able to catalyze this reaction that can be easily followed. If to show the involvement of molecular oxygen, we first performed the reaction in anaerobic conditions, and you can see here that there is just one turnover, and then if you open up to dioxygen and restore the aerobic condition, the reaction starts again, and so this means that really there is dioxygen involvement, and this was also shown by EPR, by collecting the EPR spectra in the resting state, in the absence of substrate, and in the presence of the substrate. Okay, this is the kinetic, but if you would like to have more information about this kinetic of the one, we can talk later a little bit. Where we are going now? We are going behind the nuclear site because we have characterized this small tetranuclear site with zinc. And why we like this one? Because we want to shift from a tetranuclear to a tetramanganese, because it would be very important for the water splitting as an analog of photosystem 2, and we have gone toward mononuclear couple site, but you have already listened the presentation of Linda Leone on Tuesday. So, what is my take-home message? Okay, I hope that I have convinced you that bioinorganic chemistry, first of all, is a coordination chemistry, because you should know principle of coordination chemistry to design some good molecule. that nowadays it is possible to modulate plasticity and structure for obtaining catalytic active molecules. And I should say that this prize for me also came in timely, because this was the year that the Nobel Prize was assigned to 3 scientists for computational design, to David Baker for computational protein design, and to Asabis Dunbar for the structural protein prediction. So probably protein design is well recognized in chemistry because of the Nobel Prize. And just the very last slide. Do we need human intelligence nowadays? My answer is yes, because this is the first de novo design that I did. And this is the design, is not a metalloprotein, but was a natural peptide binding protein. And this is, oh, sorry, can I go? Okay. This is the model that we obtained with very primordial computational tool. And this is the model predicted by sequence by SHA-1 of AlphaFold 2. And so there is a very, very good, it's quite similar, the two structures. So, okay, this is the current research group. So I don't want to mention all of them, most are here, but I want to thank also my former PhD student, beginning from Daniela Malasca, who is now a colleague, but Daniela was my first student, and he worked on one of the best monochrome molecule, and also Salvatore Lagatta and Marco Chino and many others. You see here Caterina Damiano, who is now in the group of Emma Gallo, and all the people, Marco Chino. I cannot mention all these people who have contributed to the work that I have presented today. These are the international collaboration that I had over the years from both University of Naples, and I have to thank Calabren in particular, Mario Chiesa, and Paul Walton for the more recent study on dicoupled and monocoupled protein, and for the hydrogen evolution reaction with the Calabren. And thank you for the kind attention. I am sorry that I was a bit late.
Thank you, Angela, for the very inspiring talk. We normally don't take questions for prizes, but if there's a curiosity and a quick answer, we can take it. A quick question and a quick answer, of course. Yeah. If not, I would like to present the prize. Okay, so now we move on to the next talk. That is a keynote lecture that will be delivered by Stefano Stagni. Stefano is associate professor at the University of Bologna, where he developed his career. During his PhD, spent some period in UK, in Bristol, if I remember well, and his main scientific interest is within the photoactive metal system, so transition metal complexes, organometallic complexes for applications in a vast area from material science to life sciences. So the floor is yours, Stefano.
Yes, please. And pointer? Il puntatore? Per puntare. Okay. All right, so thank you very much, Professor Chiesa, for your kind and precise introductions. And first of all, of course, I wish to thank you and the whole organizing committee and the scientific committee of our division for giving me this wonderful, really wonderful opportunity. And to show you what is basically a 25 years or less journey. And in this journey, we could learn how to use metal complex and to tailor their synthesis, to use this kind of ligand, so tetrosolites, to address their application towards materials and life science. So taking advantage from the interaction of light with our complexes. This journey actually started from classic organometallic chemistry while working with Professor Palazzi. And during my time in Bristol, Professor Chiesa mentioned during, I might say, quite commonly rainy morning in Bristol, my local supervisor just told me, why don't you try it at home? Sometimes happens that somebody tells you, why don't you try? And I said, just why don't you try to move to ruthenium polypyridines? I actually, at the time, I didn't have just a few, I just knew a little bit about ruthenium polypyridines, but over that afternoon, the following afternoon, I did, and I could enter into, let's say, what is I interpret as a wonderland. So, class of compounds which are air stable, okay, and for which some properties such as like light absorption, light emission, and the concomitant redox properties that are connected with light absorption and light emission did actually discover a new word for me. And by starting from 2006, okay, actually we start publishing this compound, which is very closely related to the iron complexes, and we get to know something that was really, really nice for us. So the luminescence, absorption of light, and the concomitant electron moving to promote luminescence and electrons that can flow upon absorbing light. And of course, this was really kind of a sliding door for me. And so the development of this kind of chemistry throughout the years was directed to the other families of D6 metal complex, luminescent metal complex. So we could open 2 new chapters which are still in progress. So the iridium cyclometalated complexes chapter and the rhenium triscarbonyl diimine complex chapter. And by manipulating, okay, the tetrasolate ligand in combination also with the cyclometalating or polypyridine ligands, we could explore how it was possible to tailor the structures that we had in combination with their luminescent properties, and lastly, to address their application toward material science or life science. Relative to life science, I'm happy I want to cite my mate in this journey, which is Max Massey, which shares with me the legacy from Professor Palazzi, who moved to Australia and Curtin University, and he could develop a very important research related with the tetrazolate complexes and life science. Actually, there has been a lot of crossover between our two groups. So, what is worth about tetrazolates and tetrazoles? The point is that in the photoactive metal complexes, such as rhenium and iridium complexes, the tetrazolate ligands actually plays a role in determining the kind of performance that we might want to have. And their influence is made by the, let's say, the residue, okay, bound to the tetrazolate ring, okay? So we can actually modulate the properties of the luminescent properties of this kind of compounds by changing the nature of the substituent ring. We can also combine this modulation with the changes over the ancillary ligands. And netted value coming from the use of the tetrazolate is given by their sensitivity, even coordinated to a metal center, their sensitivity toward electrophiles. And this kind of process, this kind of equilibrium in some cases, is also another way to further modulate the emission properties as well as the radix properties. All right, so a few showcasing what is important about the tetrazole in life science. Okay, the different substituent ring that we can have with tetrazolates. Max Massey showed that it can be a very important thing to address the localization of this luminescent compounds into cellular compartment. So the benzonitrile ring is good for providing, okay, an affinity of lipid droplets in the cell, or by simply changing the benzonitrile to a 3-pyridine unit, we can have a preferential localization over lysosome. In another example, okay, the 4-pyridine ring actually is good for the endoplasmic reticulus. So there's no way to predict that. I want to anticipate that, but the importance, okay, of this ring is actually crucial for determining, okay, the localization. In other examples, by manipulating, okay, the substituent ring, like in this case, we could have, we built a platform that could be used for some click chemistry, and bioconjugation, in this case, so sugar bound to azides, in order to have a new library of sugar rhenium bioconjugates. It can be used for getting insights into the glucose metabolism in cells. And all right, but when we are talking about luminescence, the most important thing is that iridium allows to have bright luminescence and color tunable. And in this case, by changing the nature of the substituent ring, we had different emission profiles, so a blue one, an orange one, and the green one in this case. And we could actually, in the beginning, transfer this kind of luminescent spectrum into reality by making electroluminescent devices, so OLEDs, in which we can see actually the color stemming from the complexes with some kind of variation, since the color is sometimes often different and going from the solution state to the solid state. And this kind of study has been still continuing, and in 2025 we have just published, okay, a new OLED in which we have been changing both the tetrazolate and the substituent on the ancillary ligand. Electrophile sensitivity is even more important for iridium complexes. We have the dramatic change of luminescence in terms of quantum yield, intensity, and in terms of the emission color when we add an electrophile to a neutrally charged iridium complex. And the neutrally charged iridium complex is transformed into the cationic compound. And when the electrophile is a proton, of course, we can have a reversible equilibrium from which we can modulate the emission color stemming from this compound. And neutral complex to cationic complex, this is very, might be a subtle change, but it has an importance both for material science and for life science. In this case, okay, by using this kind of approach, we have been building, okay, a proper color palette in which different tetrazoles, by different for the nature of the substituent ring, or by the presence of the substituent in here, so neutral or cationic, can display actually very different color. And this color palette is still being updated day by day. And neutral to cationic has a role also for their life science application, in particular for cellular staining. Indeed, we could see that neutral compounds, okay, can actually stain lipid droplets and lysosomes over cells. And most importantly, cationic compound might have specifically localizing into mitochondria, which is a very important thing. There's just a few dyes which are able to actually localize in mitochondria. The problem is that if neutral compounds are well tolerated by cells, most of the cationic compounds are cytotoxic, with only one exception, okay, in which we have this particular ring in here, and this cationic complex seems not to be cytotoxic, so we could have a mitochondrial staining, okay, inside in the heart sheath tissue that we have been showing in this case. Okay, but at the same time, okay, just skipping the life science, since cationic compounds were found to be cytotoxic, we decided to explore in a slightly different manner by keeping the life science for the antibacterial activity toward Deinococcus radiodurans, which is not pathogenic, but is one of the most resistant cellular bacterial lines, okay? And switching from neutral to cationic make this compound extremely antibacterial. So the antibacterial properties are really switched on moving from neutral to cationic, so by the aid of adding just a simple methyl group. Okay, so Deinococcus radiodurans resists to oxidative stress, UV light, but seems not to resist to this cationic compound, which is quite... All right, so iridium, as I told you, means colors, okay? And we had a color palette in which we can pick, okay, different colors depending on the structure that we are being considering. And so for playing with color, I may say that's the funniest part of all this work. We decided to combine a blue-emitting anionic complex and a deep red-emitting cationic compound, okay, to make the so-called soft soul, to combine them together. And it was nice to see that in the condition in which the Lambert-Beer law is obeyed and in the presence of oxygen, the blue emission and the red emission coexist in the right balance to give rise to a white emission. So exactly the combination of red and blue. So playing with colors is something that it's something like that, like being Alice in Wonderland for us, okay? And at this point, we decided to try to keep all what we have learned from this kind of color tailoring, okay, to combine them into polymer science, to have, I mean, solid stuff in which we could reckon the colors that we have been tailoring with our iridium complexes. And for doing this, that was the primary goal for sure. For doing this, so we have been studying our luminescent complexes first in combination with polymers to make some luminescent hybrid materials and for the luminescent solar concentrator technology. And in the other side, we decided to use luminescent complexes in photoredox catalysis, very important, in the making of polymers, okay? So the first part of this, in combination which is a very important task, and it's a PhD program of Eleonora Previati, which is sitting right there. In the beginning, first, I want to tell you what is a luminescent color concentrator. So it's a device that polymeric, transparent polymer, okay, is embedded with the luminescent dyes so that the solar light, okay, crosses the transparent polymer, and the emission stemming from the luminescent dyes actually provides some more light that is going to reinforce the radiation that is going to a solar cell, which are combined with this luminescent solar concentrators. And so in the first thing is that why should we use iridium phosphorescent complexes? Because we can have intense and color tunable emission, phosphorescent emission, so we can harvest both singlet and triplet excitons, large Stokes shift, excellent photostability, okay? And in general, we have that's a little bit of a drawback. We have not so pronounced absorption over 400 nanometers, so in the visible range, even though most of the complexes have a yellow color. Aiming at getting at using iridium complexes in the for luminescent solar concentrator technology, we decided to tailor one of our complexes in order to have a likely red emission, which is something important for the LSC. And with the aid of Valentina Fiorini, my coworker, it was designed she could design a couple of complexes to be used for this kind of purpose. And in collaboration with Andrea Pucci, Professor Pucci in the University of Pisa, the first thing that said us that just try to combine a polymer and your complexes and see what happened. And so the physical dispersion of complexes with polymers, and we end up with devices, so polymers, which are actually transparent and colorless, but when exposed to the UV light, okay, to the near UV light, actually display a yellow color, okay? Yellow color, which is not exactly red, okay, because we have a blue shift and going for a solution to solid state, but the performances were quite good, and in particular, we can have a class of colorless, okay, polymers, which could use can be embedded in a window for photovoltaic integrated buildings. The efficiency is quite good, okay, not exactly comparable to those of organic dyes, but still, okay, it's a very good starting point. And at this point, so physical dispersion have some drawbacks, okay, and possibly we can have basically aggregation. So we decided to pursue this kind of study by going, as we are synthetic chemists, we're not afraid of synthesis, so let's try to chemically anchor our iridium complexes to polymers, okay, in order to get proper metallopolymers. And as Eleonora Previati started to work with, okay, we needed to design a polymerizable ligand. So a ligand which is capable of being chelating the metal center, and at the same time decorated with a polymerizable unit. Of course, guess what kind of ligands we used for making the ligand, but the final goal was to build exactly this kind of polymer. So the polymer chain and the side chain in which contains our complexes. For doing that, we have been following two different strategies. The first one was represented by let's try to make the copolymer. Then we add the metal under the form, okay, the iridium complex, so the complexation reaction. And for the metal fragments, we use different kind of cyclometallic ligand in order to have possibly different colors. And what we obtained, these are transparent film made of these metallopolymers. We could see that, actually, we could see the emission coming from the iridium, so the iridium fingerprint, low energy, which was always accompanied by an emission, a fluorescent emission coming from the matrix, in particular from the from the sites that were not, did not undergo complexation, so the free sites. And so we were quite happy, but not completely happy, because we would like to see, I mean, some color actually stemming precisely from the iridium complexes. And the other goal was to get into red emission metallopolymers. So we explored the other strategy, which involves first, okay, let's make a complex monomer. Then we submit that to copolymerization with methyl methacrylate. And for this kind of procedure, we used different tetrazolate, tetrazole, substituted tetrazole, okay? And we also had a new guy in town, so not exactly a tetrazolate, but it's closely related cousin, which is an oxadiazole, which is obtained from tetrazole with whatever acyl chloride you might think of, in this case, benzyl chloride. And the characterization of the polymeric films, transparent films, actually were quite satisfying, since we could see exactly the color, the emission color coming from iridium in these polymers, okay? And the oxadiazole part actually provided something that this emission was going to shift to red, and it was quite a good point for us. Two of these polymers were in Pisa, okay, with two of these polymers, the devices, so the LSC were, let's see if I can, all right. So you can see the illumination with the UV light and the color coming from, so the emission coming from the iridium, which is exactly conveyed to the edge. And consider that in the edge, you will find a solar cell just coupled to the LSC. So, as I said, one goal is going to deep red, and we took inspiration from our work in which we had going to modulate both the tetrazolate ligand or tetrazole ligand and the ancillary ligands, okay? So in this way. And we could obtain actually further members of the color palette, including something approaching the red. And Eleonora has played a big work in trying to keep this, what we have learned, into her polymers, okay? And we could see that in one case, we have a near infrared emitting polymer that on going to solid state provides a red emission. Okay, while in this specific case, okay, we have a red emitting solution which still maintains a red color in the solid state. And the results about the devices based on this kind of metallopolymer will be soon available. All right, the other kind of the other study combining luminescent and luminescent iridium complexes and polymers is related to the visible light assister formation of polymers, in particular with the atom transfer radical polymerization. Just a few, this kind of process works, okay, and there's a radical process, of course, and the visible light assisted ATRP is made with the basically one iridium complex, which is the archetypal of iridium complexes. So that's iridium trisphenyl pyridine that with continuous fluorescence lamp provides good control of the polymerization over time and over the growing of the molecular weight of the polymer by keeping a good polydispersity. And that's it. I mean, that's the only compound with iridium among the iridium complexes that provides this kind of control over polymerization with a mechanism which has been rationalized in this way. So photo excitation of the iridium complexes, oxidation at the excited state, then polymerization starts, and the growing chain, okay, is going to reduce the iridium 4 complex and start back the whole process. So why, since heteroleptic complexes were not so used in this kind of things, we had plenty of tetrasolate complexes, and we wanted to try that. We wanted to try that by using both LED stripes and continuous fluorescent lamp. All of this is homemade, okay? And in the beginning, it was that, okay, if the anionic complex just didn't work, the other complexes we tried were just able to photo-initiate the process, but no control was allowed, so was observed. So free radical polymerization rather than proper ATRP. So we were just afraid, no, tetrasolate, we just could see that they couldn't work. I was going to give up, but Valentina said, okay, no, I want to get through that. And so we had to say bye to tetrazole and tetrazolates, and we started to design a complex, okay, that could actually have some characteristic that could make this kind of complex very similar to iridium phenylpyridine. So we introduced an electron donor group inspired by some work of Matiaszewski with the copper-assisted ATRP. And in the other things, since most of the iridium cationic complex are a PF6 salts, we introduced the bromide, okay, to make it, more to increase the affinity in consideration of the catalytic cycle that it was claimed for this kind of process. So after Valentina Fiorini, my coworker, and Giulia Vigarani as well started to work on that, and we could isolate the excellent candidate for this kind of stuff. So we have actually amine substituent, okay, in this position of this iridium complex, cationic complex, and the bromide one. And I must say you that this comes at the end of a screen of about 30 complexes, but we were quite happy to see that actually these complexes, so the pyrrolidine 1 and the dimethylpyridine 1 substituted, did work. We could have a nice control over 4 hours, okay, good polydispersity, okay, and a quite good control also of the increasing molecular weight. All of these data have been compared for sure to iridium phenylpyridine used in the same condition. So we could actually give an opportunity, okay, to iridium cyclomethylated complex and under the form of their heteroleptic species, following a mechanism that in collaboration with Edoardo Marchini and Stefano Caramori of the University of Ferrara, they could actually study the mechanism of all this stuff by experimental techniques and theoretical calculation, and we could see that actually it works in that way. So excitation, okay, excited state, we lose, or the complex lose 1 electron, so the chain starts growing, okay, and the growing chain gets the bromide from the iridium oxidized complex to form the active species and then start again. And all of these steps are consistent, okay, with a good control achieved with our complexes. All right, this was the last thing. I'm sorry to have been running a bit. I wish to thank you, all the people that have been with me for all of these years. Eleonora Previati, you can see all the things with metallopolymer poster 90. Valentina Fiorini, Giulia Vigarani, and Anna De Carloni, so the FAB4. All people in University of Bologna, my mate Massimiliano Massi in Curtin. the University of Pisa, and of course my group, the Inorganic Chemistry group in Bologna, for having supported me in this kind of opportunity. Last but not least, Professor Antonio Palazzi. And over these years, I have been so lucky to have had beside me so many people. And one of which I would like to dedicate this kind of work, this in particular, this presentation. Sorry for shaking my hand. And in the loving memory of Stefania Torella. Okay, and thank you for your attention, for sure.
Okay, thank you, Stefano, for the very nice talk. I think we have time for a couple of quick questions. There's one there.
Yes, I'm a little bit intrigued by this effect of the iridium in the ATRP, in the photo ATRP, because of many of these constituents didn't work, but then you found one that works, and you said that you have supported it with DFT calculations.
Yes.
So this iridium 4, is it 7 coordinate?
No. We didn't actually isolate the iridium 4.
No, but you did calculations.
Yeah, no, the calculation were actually aided to see which was the form of the photo-oxidized species, okay? The point is that from this kind of mechanistic study, comparing these complexes with the iridium trisphenol pyridine, seems that, why are they working? Because the lifetime, okay, of the excited form of iridium phenol pyridine lives for, the lifetime is quite long.
Okay.
And among all the screening that we have had, this kind of complexes seems to show a lifetime long enough. Long enough that's to do it. And that seems to be the most critical point for getting this kind of and then for closing, let's say, the catalytic cycle, I think that the bromide that we have used as a counterion has a special effect, because in a way it increases the affinity of the oxidized species with the whole catalytic cycle and the chain coming there.
Okay, if there are no urgent questions, I think we can close the session. We thank Stefano and Angela, and we reconvene after the coffee break.
Good afternoon for the afternoon session. So the first speaker of today is Barbara Chiavarino from the Sapienza University of Roma. And she will talk about naringenin and naringenin chalcone structural characterization of metal complexes by IR ion spectroscopy and tandem mass spectrometry. Please.
Good afternoon to everybody. Thank you to the scientific committee to give me the possibility to have this talk. First of all, I want to introduce myself. I am a mass spectrometrist. I have a ion spectroscopist. And of course, I am an inorganic chemistry. With this talk, I would like to illustrate why I put together these three different skills to answer some open questions about flavonoids. Flavonoids are secondary metabolite of plant. They are widely diffused in plant kingdoms, and they contain the pigment that give color of flower and flower and fruit. And they are also protective agent against insect, against ultraviolet radiation. Moreover, they can act also as chelator from a dangerous anoxic metal for plant. Moreover, flavonoids are recognized to be to have a beneficial effect also to the human health. The most important activity is the this one is the the antioxidant activity of the flavonoids. It was recognized also that flavonoids, the bioactivity of flavonoids depends strongly on their structure, and there are more than 6,000 species in nature until now recognized from flavonoid. So many studies are done to recognize the structure of flavonoid extract from plant. Many of these studies are conducted by mass spectrometry. CID spectra are very significant to distinguish between different isomers of flavonoid of different family. And it was recognized that is the searing of the that break to give the different fragment. But unfortunately, CID spectrometry is not able to distinguish between chalcone and flavanone isomer. For this reason, we decided to study the two species, naringenin and naringenin chalcone, that are taken as example of flavanone and chalcone family. Naringenin is mainly present in the in the albedo, that is the blank part of the citrus fruit. Naringenin chalcone is mainly present in the tomato peel. Here I present the CID spectra of both species recorded in protonated and deprotonated deprotonated form, but you can see that the both spectra are identical. For this reason, many studios, researchers have supposed that a fast equilibrium occurs in solution when we put naringenin and naringenin chalcone, or during the ionization process occurring in the acid source. To verify this hypothesis, we decided to investigate the two species by infrared multiphoton dissociation action spectroscopy. Here I report our experimental spectra obtained from a solution of naringenin in blue and naringenin chalcone in red, protonated, so with Ase positive. As you can well observe, the second part of our spectra is very characteristic to distinguish the two isomers. In fact, naringenin chalcone show only one important band at 1550 wavelengths, wave number, where protonated naringenin showed 4 different peaks. The most intense is 1623. Comparing the experimental spectra with those of obtained by DFT calculation, we can say that both species maintain the structure of the original precursor, was protonated on the keto-enol group, and the 2-hydroxy group have anti-clockwise configuration. We decide also to investigate, to apply this technique to discriminate between ion 2073, so the protonated species, obtained directly by natural extract of grapefruit abedo or of tomato peel. As you can see, the extract of tomato peel is the black one, is a perfect fit with the experimental spectra of the chalcone do in the same experiment, in the same way. And the extract of abedo of grapefruit certainly contain naringenin, but we cannot exclude also the presence of naringenin chalcone inside this extract. The second step of our study regards was involved the protonated species. In a previous study, Cheng observing different CAD of a series of flavanone and chalcone, have supposed that in the ASI source operating in negative mode, when the deprotonation was done, they catalyzed a quick equilibrium between flavanone and chalcone. And the position of the equilibrium is strongly affected by the nature of the substituent present in the two positions of the B ring. If this substituent is an hydroxy group, in this case, the main fragment was due to the cleavage of bond 1 and 4 of the C ring, and they supposed that the equilibrium was direct toward chalcone. But if the substituent was an hydrogen or a methoxy group, in this case, the fragment was obtained from the cleavage of bond 1 and bond 3 of the C ring, and the equilibrium was direct toward the flavon structure. To verify this second hypothesis, we perform IRM-PD spectroscopy on the deprotonated species obtained from a solution of naringenin and naringenin chalcone. As you can see here, I report the spectra obtained from the ion 2071 from the solution of naringenin, and we have a perfect fit with the calculated spectra of a structure that maintained the species that have maintained the structure of naringenin and was deprotonated in the 7th position in the hydroxy group of let's say in 7th position of naringenin. But when we do the same experiment from a solution of naringenin chalcone, we have hardly found correspondence with the calculated spectra of the different isomers deprotonated that maintain the structure of naringenin chalcone. Moreover, when we compare the two different species, the experimental spectra of the two different solutions, we can see that they are very, very similar. And so we can affirm, we have demonstrate experimentally the the supposition of Chang, and so that deprotonation that occur in Lacey cell during the ionization process in negative mode catalyze the isomerization of naringenin chalcone into naringenin. But we can see also that there are two bands that are remain that are different from the spectra of naringenin chalcone to the one obtained from the deprotonated naringenin that can be attributed to a little contribute of deprotonated naringenin chalcone. The last part of my talk regards the complexes with metal. In this case, we study copper-2, we have chosen as metal, copper-2 and zinc-2 for the biological activity, the important biological activity. We focus our attention on the complexes contain one copper or a zinc ion and the protonated naringenin. The spectra that I will show now is the same obtained also for the complex containing naringenin chalcone. Here you see our experimental IMPD spectra from the solution, from the complex isolated containing copper and deprotonated naringenin, and the comparison with the calculated spectra tell us that we have mainly only the naringenin structure that was deprotonated in this case on the catoenol group and where the copper is chelate this group. The spectra with zinc is more beautiful for me and also more indicative. In this case, the comparison with the calculated spectra tell us that certainly we have a species that contain the structure of naringenin deprotonated again on the catoenol group with the copper, with the zinc that chelate this group, but we have also two different absorptions that are pertaining to the open structure. So in this case, with zinc, we can say that we have the two species, naringenin and naringenin chalcone, both from the solution with only naringenin, that the one that contained initially only naringenin chalcone. The last, very last experiment is this one. During the photofragmentation study, we observed one fragment that was very important, and we observed this fragment also during the CAD experiment. It's the fragment 271 that formally is indicative to the antioxidant activity of naringenin because it loses neutral copper from the cell that contain copper-2. And the product, the fragment what we observe is formally the oxidated form of naringenin that can be seen as naringenin that lose H2 and was protonated. For many studios or researchers, the protonated form of naringenin is apigenin. So we decided to investigate by aerial spectroscopy this ion and compare with the experimental spectra of protonated apigenin. Here we see our result. This is the spectra of apigenin. This is the spectra obtained from the fragment 271 mass isolate from the solution of the CAD spectra from salt with the copper or with zinc. And what we can see that, yes, perhaps this ion contain protonated apigenin, but not only this species. What are the other species? We don't know at the moment. We try to understand, this is currently under study. So in conclusion, with this study, we have demonstrated that no isomerization reaction occur in solution between the two species or during the ionization process in the source operating in positive mode. The when the substance are deprotonated, we have a fast interconversion reaction between the two species. We have identified the coordination site of metal and observe also the antioxidant activity of this flavonoid. Finally, thank you for your attention.
Thank you very much. Maybe we have time for one question. If there isn't anyone from the public, I have just a curiosity. If this seems to be a very general method you can apply maybe on other substances.
Yes, okay. Exactly. All the substances that we can IMPD, I can apply all the substances that can put in the gas phase with acid. Yes, we study a lot of complexes, metal complexes, also from cisplatin and so on.
Very interesting. If there are any other questions?
If you have some intermediate to analyze, you can give me. We can done.
If you want to talk with the speakers, there is the poster section after. We thank again Barbara. The next speaker is Cosimo Ricci from University of Roma Tor Vergata. And he will talk about quantitative PET depolymerization using ethylene, glycol-based eutectic solvents. Please, thank you.
Thanks to the chair for introducing me, and thanks to the audience for listening to my talk about quantitative PET depolymerization using ethylene glycol-based eutectic solvent. Why is there a need for the depolymerization of the PET plastic of water bottle? Well, this plastic is synthesized from ethylene glycol and terephthalic acid, and after its lifetime, most of it ends up in landfill or is incinerated. 19% of it is lost. That means that will build up in the environment, causing ecological problem, and only 16% of it is recycled, usually through mechanical recycling that lead to lower quality materials such as polyester fiber. What is missing from this picture is an economical way of reobtaining that monomer from which new virgin plastic can be resynthesized. Currently, exists some chemical process for the depolymerization of PET, such as hydrolysis, ethanolysis, or glycolysis. All these processes produce different monomer from which new PET can be synthesized, and of the proposed monomer, the bis-hydroxyethylene terephthalate derived from glycolysis is the most valuable one, as it can be used for the synthesis of PET without the use of additional ethylene glycol. All these reactions can also be carried out enzymatically, but this approach requires reaction times that are too long for an industrial application. And even the chemical process require relatively high temperature and long time, making them energetically demanding and so expensive. What is needed is a novel catalyst that can lower this energy demand for an industrial application. A possible catalytic species is the glycolate Ag- ion. It was recently described in a green chemistry paper by Zhu et al., in which they prepare a 10% solution by weight of sodium hydroxide in ethylene glycol. And according to NMR data and simulation, the Eg- glycolate ion is present. This ion can attack the PET, leading to the formation of terephthalic acid and novel Ag- that will then continue the cycle catalytically. These were good results, but the employed conditions are quite harsh, especially considering that the inorganic base will promote the hydrolysis of the valuable BHAT ester monomer. So this cannot be extracted from this reaction. Given this, we looked in literature for an alternate source of the glycolate ion, and we found it in a paper by Gigo et al. On the stability of diazonium salts in the eutectic solvent. In this, they firstly synthesized the potassium halide ethylene glycol 1:6 molar ratio DS. According to their simulation, the Ag- ion is present in this DS. So we attempted the DS depolymerization reaction in the solvent with the aim to identify the product and propose a possible mechanism. For it, we firstly studied the thermal stability of this DS because the ethylene glycol can incur oxidation. So we studied through UV visible spectroscopy. We screened all the DS prepared with different halogen salts for the most efficient one in this context through the consumption yields of the PET flakes or the weight loss. And having found the most efficient one, we studied the depolymerization with an eye for a possible industrial application. So we employed two different heating mechanisms, first conventional classical heating, but also microwave heating, because it can drastically lower the reaction time and so the energetic demand. But we also considered that the ethylene glycol is highly hygroscopic, so and the water content in the DS will affect the outcome of the reaction. So we varied the water content in our starting DS. In this context, we studied the polymerization efficiency through the consumption yield, but also the catalytic nature of the employed DS by measuring the halogen consumption. And to have an idea of the proposed reaction mechanism, we studied the product identification through NMR spectroscopy. Starting from the optimizing of the reaction temperature, we considered that PET glycolysis required 200 degrees Celsius and 1 hour. So we treated our DS for 1 hour and recorded the UV spectra. We observed a rise in the 260 nanometer absorbance for DS treated at 160 degrees and above. That indicate clear sign of degradation. So 1 hour at 150 degrees Celsius was chosen for further depolymerization experiment, such as the screening of the DS prepared with different salts. We observed depolymerization, a consumption of the PET flakes with potassium DS prepared with potassium bromide iodide, and general trend of increased efficiency with the increase of the radius of the halogen. But as is common with halogen involving reaction, the fluoride has a different behavior. In our case, it works substantially better. We obtained a PET consumption of 24% and the easy separable powder product. So the potassium fluoride ethylene glycol 1:6 molar ratio DS was chosen for further experiment. We first studied the effect on water content on the PET consumption reaction with conventional heating. And indeed, we observed that with the increase of water, we have an increase of efficiency from 24 to 30%. But by measuring the fluoride consumption, we observed that if in an anhydrous condition, no fluoride consumption is recorded, so fluoride is a catalytic species that is not consumed in the reaction, upon a water addition, we have a fluoride consumption that is dependent on water content. This can be explained to some parasitic reactions, such as fluoride hydrolysis, that will lead to the formation of hydrofluoric acid, that at the 150-degree reaction temperature is gaseous and leave the reaction vessel. Also, the hydrofluoric acid is known to etch glassware, and indeed we observed some etching of the employed glassware confirming this hypothesis. When we employed microwave heating, we obtained a complete consumption of the PET flakes with 3 minutes of irradiation of only 90 watts. But in this case, the water content has a negative effect on the yields. Probably this can be easily explained by the microwave absorption capability of ethylene glycol and water that is measured by the tan delta parameter. Ethylene glycol is the solvent that better absorbs the microwave energy, and water have a tan delta parameter that is 1 order of magnitude lower. So by mixing more water in our reaction solvent, its capability to absorb microwave energy and the energy available to the reaction is lower and lower, as is the yield. When measuring the fluoride consumption, we observed a fluoride consumption that is still dependent upon water content, but in this case, there is always some Fourier consumption due to some other parasitic reaction. Having obtained these results, we recorded the NMR spectra of all the product and Sornato reaction, especially at the aromatic part of the NMR spectrum, from which we were able to distinguish, identify, and quantify the terephthalic acid, bis-hydroxyethylene terephthalate, and monohydroxyethylene terephthalate. These are all monomer derived from the PET depolymerization, confirming its depolymerization. We also recorded a recovery of 100%, indicating that any weight loss of the PET flakes can be easily attributed to a depolymerization reaction. And we were able to calculate a product balance that is still affected by water content. With conventional heating, in anhydrous condition, we recorded a mixture of all the three recorded monomer. But the addition of water will promote the formation of only terephthalic acid. In microwave heating, instead, we observe a mixture of all the three recorded monomer in all the recorded water percentage, but the water content still affects the product balance as it boosts the formation of terephthalic acid. Given these results, we were then able to propose some possible reaction mechanism, starting from the formation of BH8T. We consider that the Eg- ion is negatively charged and render possible an attack, a nucleophilic attack on the carbonyl of PET that lead to the formation of a tetrahedral intermediate and the subsequent removal of the monomer from the polymer chain. This is the reverse ester Fischer esterification. That is the classical mechanism for the PET glycolysis. But the problem of this mechanism is that it will lead only to the formation of the bis-hydroxyethylene terephthalate. And in our product balance, we have a considerable fraction of the mono-hydroxyethylene terephthalate, the monoester species. To consider its presence, a possible reaction mechanism is considering that the fact that the position of attack will lead to a different monomer. And if we have continuous terminal attack of the Eg-, we'll have the continuous regeneration and formation of MHAT in a similar fashion to the PETase enzyme. This will indicate that the DS structure with the potassium ion or some other coordination will favor the attack of the Eg- ion in this specific position. That's what we are currently investigating. To explain the formation of the terephthalic acid, we consider the simple fact that ethylene glycol is really highly hygroscopic, and even in a strictly controlled reaction, some water will enter the reaction. And even a small amount of water in this condition will promote the hydrolysis of the ester monomer BHAT and MHAT. So we propose that the formation of the terephthalic acid is a subsequent secondary step after the formation of the first two monomer, especially considering that its fraction is always dependent upon the water content in the reaction mixture. So in conclusion, we developed a novel process for the depolymerization of PET using the potassium fluoride ethylene glycol 1:6 molar ratio DS. This reaction will lead to the formation of terephthalic acid, bis-hydroxyethylene terephthalate, and monohydroxyethylene terephthalate monomer. It's a fully catalytic reaction in anhydrous condition. We were able to obtain high purity terephthalic acid with water addition and a complete depolymerization with 3 minutes of microwave heating. In the future, we are carrying out study on the recyclability of the DS in anhydrous condition. We are investigating some solid proof of the presence of the Eg- ion in our specific DS that don't require some experimental proof. And we are carrying out some molecular dynamic simulation to support the mechanism with a specific favorated site. Thank you again for listening. Thanks to the scientific committee to allow me to talk to you, and my research group, the Starnetic Research Group.
thank you very much for your presentation. Is there any question, please?
Nice talk. Thank you. Did you compare the behavior of your catalytic system with the catalyst that used industrially, zinc acetate in the same
Zinc acetate, yes, but at 150 degrees, we were in our system, we were not able to obtain any product. We did the blank, but
even with microwave.
With microwave radiation, we haven't tried. We are intended to try, and it's still a work in progress, but it's still needed, an experiment that is needed to be done.
Okay,
thank you.
Congratulations, Cosimo. Very nice chemistry. I really enjoyed your talk. So I have
Thank you.
plenty of questions. I just probably make you just two of them. So when you finish the radiation with the microwave, by naked eye, you can see any change in your dipolaritic solvent. So the irradiation from the microwave also disrupts your dipolaritic solvent.
Thank you for the question. Yes, we sometime indeed observe some changes with the anhydrous DS. We employed a commercial microwave that was modified, and we observed the boiling of ethylene glycol in some preliminary studies. That's why the power was the lowest possible. But even when the DS boiled, the ethylene glycol was fully evaporated. That make a lot of smoke. We were able to reconstitute the DS with the addition of novel ethylene glycol. But when carrying out the experiment with not ethylene glycol but glycerol, we observed that a complete degradation of and polymerization of the DS.
And a quick question, if I may.
Yes.
So just the other question, you are degrading things, but you are producing like a Bronsted acid. So you're thinking that your system can also be used to promote Bronsted acidic reactions or typical organic reactions that can be promoted by just H+?
Yeah, probably, yes. Right now, the aim of the project.
Cyclo suberization, something like that. Typical reactions of H+.
Yes, but to be honest, right now, just in the future, we are thinking about a lot of possible stuff. But right now, we only tested with the PET. Thank you.
So thank you very much again, Cosimo.
Thank you.
So the next speaker, it is Eliano Diana from University of Turin. Oh. So he will talk to us about metallophilicity as a supramolecular tool from concept to application. Please.
It's a crash.
Dear fellows, good afternoon. Sorry for the delay. In this short talk, it's a pleasure to present you some results of one of the research team of inorganic group of the chemistry department of my university that concerns the preparation of crystalline material based on metal complexes with a specific structure. As you know, if you want to obtain a sort of a crystal architecture, is compulsory to employ all the tools of supramolecular chemistry. And in the last year, we are studying a peculiar behavior of the last in the order of the symptoms, that is metallophilic bonding. That is exactly at the end of the energy of the chemical bonds involving metal and metal. It's not exactly in the forefront of the... I'm not lucky. Sorry. Metallophilic bonding is not exactly in the forefront of the chemical research. In fact, in the last 70s, three masters of the chemical research defined this kind of interaction, and especially there is a very, very beautiful work of Rod Hoffman and a lot of experimental work done by Martin Jansen and Hubert Schmidbauer. And especially Hubert Schmidbauer prepared a lot of complexes where this kind of interaction is active. Also, if their approach wasn't not exactly supramolecular, they were most interested, in fact, into the defining this kind of interaction and how to govern it. And a good definition of one of the most strong metallophilic interaction that concerns gold and gold atoms has been done by one of the most nice inorganic colleagues, Pierre Bronstein, that all of you probably remember very well, that in fact studied a lot of complexes where this interaction is active. And especially, he was able to discriminate all factors that in the solid state can permit exactly this kind of interaction or contrast this kind of interaction. Because, in fact, aurophilic interaction has an energy that is comparable to hydrogen bond, a strong hydrogen bond. But Bronstein told us that if there are strong steric effects acting inside the three-dimensional structures, sometimes this kind of interaction cannot be governed. A lot of theoretical work has been done also in order to explain the origin, and the main work for sure are the work of Pekka Pikko, that a nice name in fact, and also a great, one of the most great theoretical chemists, that did a lot of study and also put the right theoretical approach, able to explain why, for example, two atoms that are inside a complex with exactly the same charges, so we expect that they are not attracting each other, in fact, are able to establish a sort of chemical bond. But And Pekka Pikko also did a lot of systematic work in order to explain exactly all kind of geometrical possibility that you can see in this beautiful picture. But what about us? We were interested, in fact, into going deep into in order to understand when, in fact, we are able to govern this kind of interaction in order to obtain exactly a three-dimensional architecture. And in this picture, I show you the starting point for us. That is exactly the cyanoacrylate of potassium, that in the solid state structure you can see is able. I'm doubtful to touch this object. I try. Well, I try there. Well, you can see all the gold atoms that interact strongly. The distances are lower than van der Waals radium. What have we done? Well, we chose a model system. We tried to prepare a very, very simple complex done based on zinc with several bidentate ligands. You can see the 5 that we explored. You can also probably understand why we choose this kind of ligands with this shape. We tried to modify, in fact, the steric requirement, and also the bond angles, the bite angles of the ligands. Not only, but we explored also all the conditions that were able to give us a crystal compounds. So we did all synthesis by changing the solvents, temperature, gradient of solvents in order to evaluate deeply all aspects that can influence it. And in fact, the next figure reports the 2 main features of the complex that we obtained. In fact, the gold complex with the cyanide ligands enters into the coordination sphere of the zinc in 2 main different positions. One is on the right, it is a classical octahedral coordination, and on the left, we have just one cyanide into the coordination sphere with a water. Obviously, water, what does it mean? Possibility to do hydrogen bond. So another symptoms that can completely modify your results. And in fact, here I'll show you the different architectures that we were able to obtain. In fact, according to the presence or not of a strong hydrogen bond and mixed with the steric requirement of the ligands, sometimes we obtain a sort of expression of the metallophilic interaction, especially here, you can appreciate it here, sometimes not. The control is not so easy, in fact, because sometimes it means just to change the polarity of the solvents. I'm talking methanol or acetonitrile. And in one case, we change completely the crystal phases. But when the metallophilic interaction appear, in fact, the behavior is exactly similar to that has been shown by Pekka Pikko in his review report. Another question that was very, very interesting for us was, but this kind of interaction is a sort of problem, egg and chicken problem. When does it start? It's a typical interaction that concern mainly the solid states, or does it start in solution? For this reason, we decided to do solution studies by employing a lot of techniques, NMR, mass spectroscopy, electronic spectroscopy, and I report just for I don't have enough time, just the results obtained with the X-ray absorption that, as you know, is able to give you an idea of the coordination sphere in solution. And on the left here, I report the results obtained for the complex one, that with the bipyridine, with the water coordinated at one cyanide in the coordination sphere, and the red and the black trace are related to the solution compound and to the solid state compound. As you can see, are absolutely identical. And so does it mean that in fact this kind of interaction starts from the solution? Obviously, we run the experiments in a concentration that not favor absolutely the aggregation in solution. With this kind of answers from this set of experiments, we tried also to change with another kind of ligands. And more or less, we were able to reproduce exactly the kind of patterns that we obtained before. In this case, we tried also to do a sort of heterometallic metallophilic interaction by employing silver and gold. And as you can see, I'm very, very passionate about this kind of architecture. I found it very, very nice. As you can see, here we are able to perceive exactly the metallophilic interaction with the gold cyanide, and also metallophilic interaction between the two silvers in the complexes. Are we really able to govern this kind of interaction? Obviously, we obtain this kind of results with this specific. Our work is going on, obviously, but we are confident that with a strict control of all the conditions, in fact, we are able to obtain a sort of architecture. And you can ask, but why you want exactly this kind of architecture? Other history, because obviously a specific architecture favor specific properties of the final materials. Just to prevent your question, obviously is not very cheap material because we are employing very, very expensive metals. But in fact, this kind of system can serve as model systems. In the first table, I'll show you that, in fact, metallophilic interactions are possible with a lot of metals. I go just quickly to the end. We tried also to do a sort of calculation of the energy concerned in this kind of interaction. Pekka Pikko, in the very, very old world, employed the computational tools available at that time. Now we have the possibility to employ also DFT, including dispersion energy. And so it's possible to do on the solid states very, very quickly, because the problem is try to modelize solid state. So with the DFT, including dispersion, and by employing especially the quantum theory of atoms and molecules, we are able, in fact, to evaluate the interaction energy, and as you can see in this picture, also a sort of orbital interaction among the donor atoms in the donor orbital of the gold and in acceptor orbitals of the silver. So in fact, metallophilic interaction can be justified with this kind of approach as a sort of wake bonds, in fact. Well, I think that is all. Thank you very much for kind attention. And sorry for the troubles. So.
Your presentation, if there is a question there. Okay. Just one quick, then we go to the next speaker.
So thank you very much for your talk. Very, very interesting stuff. I wanted to ask you about the solution stuff.
Right.
So, yes, do you expect this interaction to change when you change the solvent, for example?
Yes.
For example, from, I don't know, ethanol to dichloromethane?
Yes. Yes. In fact, I didn't report because there was otherwise a lot of pictures, but in fact it's very, very sensible to the choice of the solvents, unfortunately. So this is one of the aspect, very, very delicate aspects of the kind of chemistry, because we have to exactly do a systematic work by changing, if I remember, changing the 5 to 6 solvents in order to repeat all kind of measurements, and in fact just one allowed us to obtain the results that I show you.
Thank you.
You're welcome.
Point between a neutral quantum double complex salt and diacarbonate. Please.
Good afternoon, everyone, and thank you, Chairman, for your kind introduction. I would like to start my talks focusing on some keywords contained in my presentation title. The first keyword is coin, and coin in my mind is associated to metal, not metal, but metal, and then gold. So gold medal, and it's 5 p.m. So I would like to exploit the occasion to celebrate the fact that a few days ago, we won the gold medal at the Volleyball World Championship. But now, let's focus on scientific matters, issues. So again, the keyword gold, and the other keyword is the dithiocarbamate. And dithiocarbamates are sulfur-containing ligands. Their common acronym is DTC. And are chelating ligands able to stabilize a lot of oxidation state of different D-block transition metals. And here I've reported some resonance forms. They find a wide use in many fields, including agriculture, analytical chemistry, material science, and of course the biomedical field. So the talk is mainly focused on this class of compounds associated with a one-to-one metal-to-ligand stoichiometry. So we have one gold-free and dithiocarbamate ligand, chelating ligand, and 2 chloride ligands, mimicking the structure of the famous cisplatin. In fact, both complexes share the 8 electronic configuration, and both show promising oncological properties. These are considered quite old complexes, even if in the last years and months, the field of gold and dithiocarbamates is a still hot topic, as shown by this very recent paper published by the group of David Pugh a few months ago on data transactions. Here in the abstract, you can see that they mention the fact that when you try to obtain this type of compound, neutral compound with a one-to-one metal-to-ligand stoichiometry, you always obtain a mixture of complexes, the neutral compound and also an ionic derivative that I will show you in a few seconds. And then the scientific community discovered recently that there is also an equilibrium in solution between these two derivatives. So this is the neutral derivative. We want one metal to ligand stoichiometry, I mean diphencyl ligand stoichiometry. And the other derivative, the ionic one, it contains a cation, a homolectic complex, homolectic complex cation contains two diphencyl and the anion is another homolectic complex containing a gold-free center bound to 4 chloride ligands. So we have these two species always present in all synthetic procedure reporting literature, but present both in the powder after synthesis, but also in solution. So today I would like to clarify the scenario in this field, and the same author recently published another paper, and in this regard he mentioned the fact that for this class of compounds we cannot use the technique of elemental analysis because of course they share the same empirical formula. And as a reference he put this one, which is actually a patent that I personally wrote some years ago and where I mentioned these aspects. So let's sum up. We have two species present both in the powder after the synthesis and two species present into solution that could potentially convert each other. The neutral species on the left and the ionic species on the right. The ionic species on the right is referred to as a double complex salt. And today I would like to answer some questions. The first one is it possible to synthesize each of them in a pure way, so to isolate a pure form of each compound? And the answer is yes. I don't have the time to show the synthetic procedure, but I will publish them as soon as possible. The second question is it possible to manage to handle this interconversion process, so to find the right conditions wherein we so to exploit them to convert the neutral derivative to the ionic one and vice versa? The answer is yes, and then now I will show you how to do that. I don't know what happened here. So as a model ligand, we exploited the piperidine dithiocarbamate, abbreviated as PIPE-DTC. We obtained for these complexes also, we solved also the crystal structure for both the neutral and the ionic derivative. And now let's start considering these equilibrium. So the equilibrium started from the ionic derivative as a reagent to obtain the neutral derivative as a product. I would like to underline that the reagent is a yellow powder. Conversely, the product is an orange powder. Here you can see the typical absorption of the two compounds recorded by visible spectrophotometry in chloroform. For example, in the case of the ionic derivative, we can observe the typical double amp camel profile here. So let's consider, first of all, the equilibrium connected the ionic derivative to the neutral compound. And as you can see over time, so over 3 days, the visible profile spectrum changes progressively, and the band recorded set at 319 nanometers decreases progressively in terms of intensity, whilst the other one increases in terms of intensity, achieving a final profile, the red one, which is the same recorded for the pure compound independently synthesized. We studied also this phenomenon by NMR analysis, and we confirmed what we detected by UV visible spectrophotometry. So we recorded different spectra over time in deuterated chloroform. Let's consider now the other equilibrium, so the one starting from the neutral derivative and achieving the double complex salt as a product. In this case, you can see that the The starting wavelength maximum is 250 nanometers, which is a different value compared to 265 nanometers. This is a clue for you, and with this I mean that in this case, of course, we consider a different solvent, a different medium to dissolve the neutral compound. In fact, in this case, we used a mixture, the MSO-water mixture. And only in this way, we obtained, over time, the ionic derivative. And of course, in the end, we obtained the double profile, camel profile, typical of the double complex salt. But now I have another question. Is it possible to obtain the double complex salt just dissolving the neutral compound in a polar solvent, such as DMSO, mixed DMSO water? The answer is no. The light exposure is a condition sine qua non for the formation of the ionic derivative. In fact, we need to expose the sample to light. We confirmed also this phenomenon by NMR spectroscopy in the same solvent, a mixture of water and MSO. So to sum up, here we can observe the red spectrum associated to a sample of a DMSO solution of the neutral derivative, abbreviated as 1-to-1 with a chloride as ligands, kept in the dark. So the spectrum resembles the spectrum of the original, the initial product, the neutral one here reported. So the red spectrum is associated to this compound kept in the dark and which is stable under these conditions. Then let's consider the dark spectrum, the black spectrum, which is basically the one associated to the ionic derivative. In fact, this spectrum is overlappable to the blue spectrum, or visible spectrum, associated to the same compound independently synthesized. So this confirms that under our condition, we can obtain the ionic derivative starting from the neutral derivative, the neutral complex. In the case of the formation of the neutral derivative from the double complex salt, it is enough to dissolve the ionic compound in a polar solvent such as acetone, chloroform, dichloromethanes, and the light is not necessary. I would like to underline that I started this work some years ago when I was affiliated to the University of Padua. In that period, I founded a startup company, Itan Pharma, which was a spin-off company of the University of Padua. Then I moved to the University of Verona, and then it's almost 3 years that I was appointed associate professor, and I would like to finalize this work, this paper, as soon as possible. So to sum up, this compound could appear very old, but they are very promising anti-cancer agents on the one hand, and on the other hand, they could be used in many fields. For example, what I described today could be used in catalysis or material science for new applications. So we were able to synthesize both the neutral and the ionic derivatives in a pool, achieving pool compounds, but I don't have the time to show the synthesis. And we were able to define how to obtain each compound in a reversible way. And I would like to underline that this is one of the few rare examples of a dynamic inorganic system. Usually, systems similar to this involving gold contain gold and oxidation state +1, and usually the interconversion occurs within the nuclear derivatives, so it is an intramolecular rearrangement. In our case, it's a case containing gold-free and, let's say, an intermolecular rearrangement. In this regard, I just mentioned an example reported in 2007 by Coetzee and co-workers, and in this case, they discovered that in solution, this neutral compound can convert into this double complex salt where the anion contains 4 pentafluorophenyl ligands and the cation contains 2 pentafluorophenyl ligands and 2 tetrahydroterpene ligands. So a case similar to ours. So coming back to the title and the field of application of these complexes, in my case, so the pharmaceutical field, I would like to underline that it's always important to consider the stability and the speciation of the coordination compounds that we are studying, especially in the biomedical field, in my case, in oncology. As the scientific community did many years ago in the 70s for the famous cisplatin. And I would like to remind also another concept introduced more than 1 century ago by Paul Ehrlich, so the famous concept of the magic bullet. So we need, of course, to balance the anti-cancer activity, or more generally, the bioactivity and the toxicological profile. And in the case of coordination compounds, it's also important to well know the stability and the speciation of the compound. So I would like to update you with the most recent data published by the World Health Organization regarding the cancer incidence, and the data state that in 2040 there will be about 30 million new cases. So there is still a lot of work to do, fortunately, in this field, many steps to overcome. Coming back to the keyword gold, present in the title, and the concept of coin, I would like to focus our attention on the coinage metals, the so-called coinage metals, so copper, silver, and gold. And I would like to exploit this occasion to, let's say, advertise a paper which was accepted a few days ago based on a work carried out in collaboration with Professor Oliveri at the University of Catania. In this work, we mainly focused on bioinorganic aspects, for instance, on in vivo testing, for example, on zebrafish embryos. So I would like to conclude thanking my research group, recently established research group, the technician Erika Viviani, and of course, all of you for your kind attention.
Thank you very much. I think we have time just for one question. If there are no questions, we move on because we are a bit late. But thank you very much. So the next speaker is Vincenzo Forlini from University of Padova. He will talk us about extraction of metals from industrial wastewater sludge with depth eutectic solvents, a proof of concept. Thank you.
Se ci mettiamo la chiave, se proviamo a funzionare. Oh, guarda, facciamo questa dopo. Allora, Vincenzo.
So, good evening, everybody. I'm Vincenzo. I'm first year PhD student from University of Padova, and I'm really excited to be here to show the tasks that we carried out during our first year of PhD. So this is an industrial project that is co-funded by a wastewater company based in Thiene, Vicenza. And so since they deal with the wastewater treatment, the focus of this presentation will be on recovering nickel from this underrated urban mine. So our starting point will be the definition of critical raw material. So it's a raw material of high importance to the European Union and of high risk associated with its supply. So if you've been following the latest news, you probably see how this race for critical materials is really shaping current geopolitics in terms of conflicts. So the conversation about circular economy and closing the loop is not really just about waste management or cleaning the environment. It's really about strategic defense and building resilience for our continent. So historically, metals, of course, have come from mines, but the concentration of metals inside the ores is really low. And as we need more and more materials for our technological transition, we should look at more varied sources of metals, including urban mines. So when you think about, for example, at electronic waste, it's most popular source of metals and they're highly refined. But I would like to bring your attention to a different source of metals, so industrial wastewater sludges. Well, it's really hard to give a general definition because it's really just a byproduct of wastewater treatment. So we call it as a more of an umbrella term. And in our project, we'll be focusing on electroplating sludges. So a byproduct that contains a lot of nickel coming from electroplating processes. And as you can see from the graph on the right side, there's been quite a growing interest in the topic. But since it's very confined to the industrial area, it's really hard to find a lot of literature about it. So that's why also the project is co-funded by a company. So in this scheme, you can see how our goal is to kind of close the loop on the wastewater produced by electroplating. So we start on the top with the electroplating solution. Of course, it got used, we need to treat it, and our company has specific technology called the supercritical water process, which at 400 degrees and 25 megapascals is able to precipitate all of the metals inside the wastewater. So the result is a sort of purified water that needs further treatment, of course. And then we have our product, the sludge, which is really a big mixture of metal oxides, some organic content, some water. It's a pretty complex matrix, and it's really hard to, let's say, give a general definition. It really depends on the batch. If the galvanic company changes the recipe, then of course also the recipe of the sludge will change at the end. So our goal is to use deep eutectic solvents to recover nickel from the sludge. And there has been other talks about deep eutectic solvents this afternoon. So I would like to focus on the advantages they have over more conventional ways of recovering metals. On one side, pyrometallurgy is pretty energy intensive, associated to a lot of emissions. And hydrometallurgy, they use very hazardous chemicals. Again, the wastewater volumes. So we have the issue of wastewater, and we are producing more wastewater, so maybe we could think about something else. Deep eutectic solvents are also called designer solvents in a way, because you change the components and you can change and tune the properties. I wrote that they're low toxicity and low flammability because, again, it depends on the components that you use. So it would be really incorrect to just say they're non-toxic. In this work, we're focusing on betaine, glucosamine, and histidine as the hydrogen bond acceptors, and formic acid and citric acid as the donors. So the project is divided in 3 steps. We have a characterization of the sludge. We have different deep eutectic solvents. We're comparing efficiency to see how they perform with the material. And then at the end, the parameter optimization. Again, challenges, heterogeneity, complexity of the matrix, and lack of literature. So we'll start with characterization. Again, this is a composition from last year, so it doesn't necessarily reflect what we see today, if I were to analyze it today. But you can see it's mostly nickel oxide. There's some iron as the most representative impurity. We have calcium and sodium, especially sodium because the original process is alkaline. It uses a lot of soda, so the sodium comes from there. And phosphate and some organic components. And the technology provider for the supercritical water process assumes that in the sludge, all of the metals are in the highest oxidized forms. So my assumption for the form of nickel is that it will be found as nickel oxide because of the conditions of the process. But on the surface, some of that nickel will be converted into carbonate and hydroxide. When I performed the thermogravimetric analysis on the feedstock, the main finding was that around 10% is organic matter and around 6% is carbon. And this is consistent with other elemental analysis that we performed. Again, carbon is around 6. Nitrogen, there's some traces of nitrogen, probably because they use ammonia in the electroplating, and also, of course, sulfur as a sulfate, because the original solution is a nickel sulfate solution. And this slide illustrates a very brief analysis with infrared, and I see very sharp peaks, very signals of carbonate, possibly confirming that on the surface, some of the nickel oxide becomes carbonate. But we can see other signals. Some of the elements are not really analyzed, for example, silicon, because there's no real limit to the discharge in the environment. So companies don't really analyze that. They analyze what has a specific threshold for the legislation. But there's probably going to be some silicon and some other elements that you don't really see. Now, let's go to the dipiotactic solvents. We decided to test 4 systems. And the experimental procedure is really straightforward. You just take 0.1 grams, you add 5 grams of DES, 80 degrees for 3 hours, you filter and you analyze. And our goal was to compare which system allowed the highest recovery of nickel with the lowest co-extraction of iron. This is the list of experiments. And these results show that glucosamine and betaine show the highest recovery, while the system based on histidine performs poorly. In this graph, in this plot, you can see 2 feedstocks because we tested the sludge and also the ash. The ash is the same material, but it's calcined at 600 degrees because we thought, well, maybe if we remove the organic component, maybe it's better. But according to this plot, it's actually worse. We actually create a matrix that's more impenetrable to the dipiotactic solvent, except for histidine. So based on these results, I decided to continue forward with betaine and citric acid because it was very clear, transparent, so you could really see if it extracted the nickel or not, because the resulting solution is sort of emerald green, while glucosamine has a high affinity, but it was not really transparent, and it was prone to very strange caramelization and other phenomena. So the approach for parameter optimization is based on the design of experiments with the software Minitab. I decided to test 2 different temperatures, 2 different durations, and 3 different solid-liquid ratios. So I decided to divide the experiments in 3 batches, one with very little solvent, one with middle, and one with a lot more, to see if it could be a significant change. And the results highlight how adding more dipiotactic solvent actually decreases the efficiency of the extraction. But on the other side, it makes the resulting leachate less viscous, so I can recover it fully. While on the other side, putting less DES makes concentration higher, but then it's really viscous and it gets stuck in the vial, in the filter, everywhere. So I decided to kind of find a trade-off between the efficiency and also the practicality, because of course, if I can't recover it, I can't really make a product out of it. And this is exemplified by the viscosity measurements that we did. A clean deep eutectic solvent has a viscosity of around 0.08 Pascal per second. And as we decrease the amount of deep eutectic solvent, the viscosity increases a lot. So we have a 75 reduction when we put more DES in the vial. Of course, at this point, it's not really clear if the viscosity is due to stronger chemical interactions between feedstock and deep eutectic solvent, or just physical effects. So we have to, this is still an open question. And so the conclusion for this project so far is that this sludge, which is currently treated as waste and it's really just stored in the warehouse of the company, instead can be used as a valuable secondary source of nickel. So it allows to comply with the goals of the urban mining and the EU critical raw materials that was enacted last year. Of course, the heterogeneity of the feedstock remains a significant challenge. Also, we're changing from batch to batch, so we're still trying to figure out a way to really standardize the analysis and the experiments. And of course, the DES demonstrated a high efficiency and selectivity for nickel, so we're talking about over 90%, 95% of the nickel with limited co-extraction. So they are a potentially sustainable alternative to conventional methods. Of course, the scale-up remains an open question for now. In the future, I would like to focus on electrodeposition to recover the nickel from the DES in order to deposit, and of course, evaluate the recyclability and regeneration, because the DES are quite expensive compared to conventional solvents, but if you're able to recycle it, it makes them way more cost-effective than traditional solvents. And at the end, I would like to really compare what, even on environmental impact level, what's the impact between a conventional route and a more green route. So for now, I focused on the more green route, but I'm also exploring other valorization routes, because at the end, the goal is really to bring the nickel out of the warehouse and putting it back to the market and closing the loop. Thank you very much. I would like to acknowledge my research group, my PhD companion, my professor Silvia Gross and Mauro Carraro, and the staff at Tintes, especially Francesco, who is my supervisor, and of course the PNRR, and thank you for the attention. If you have any questions, I'm here.
Thank you very much. We have maybe time for one question.
Yes.
Congratulations, Vincenzo. Great chemistry. It's difficult to collaborate with the industry, I know it. So you're trying to close the loop. So, and you can have nickel species already in solution. And you said that you can control even the concentration that you have. So I was speaking about this before. Nickel is also considered a good catalyst. So I was wondering if you can use this reservoir of possible nickel compounds to try to replicate any typical transition metacatalysis that is reported. I know that you have different feedstocks, so it's going to be difficult to replicate it, but that will be a very nice proof of concept. You can take something that comes from the land, just treat it, and you make a catalyst.
So we were thinking about this idea also with my companion Andrea. My focus was really to make a marketable product. So I was focusing either on metallic nickel or maybe hydroxide or sulfate, because at this moment the material is classified as waste. And in order to remove the label of waste and making it a product, you have to show that it's very comparable to what you find in the market. And I'm working with really, really large volumes of waste. There's an entire warehouse full of this, let's say, green sludge. So my goal was really to work in bulk and focus on replicating the technical constraints of the products in the market so that they are able to sell it. But yeah, I know Andrea is working on trying to make sulfites because again the DES environment is really acidic, so you can't really do precipitation. It's an obstacle. So it's you have to find different ways to valorize.
Yeah, but you can also remember that you can do pyrolysis of the eutectic solvent. So you just can just go very high temperature. You have a carbonous surface and your nickel will be there. So I think it's something that has been done before. So you just burn at very high temperatures. You have like a black thing that contains, because you have carbons on the starting products. So you can do pyrolysis and you can have the nickel probably there, and you can just move to heterogeneous catalysis and deal with like high volumes of this.
I think at that point it becomes a question of economics, because in the context of working with an industry, they are looking for something that's viable to just scale up and carry it out. So it does feel a bit like a waste to burn the deep eutectic solvent. I would rather try and recycle it as much as possible. But it's an interesting idea. Thank you for that.
Well, I think this closes the afternoon session. Now there is a poster. Please thanks again all the speakers for today. Thank you.
Perfetto.